Professor Deshpande, this my talk seems to be in Hall A. I don't know if this is probably Hall. This is probably Hall D. Hello. Yes, I realize that is in Hall A, so I'm just logging out of Hall D and I'm just joining in Hall A in a minute. Yeah, but so I did not realize it was in Hall. Yeah, okay, I'm just joining. Yeah, okay. I've also told Professor Deshpande. Yes, Hall A. Yes, yeah.
Happy to see you all in the morning, sir.
Yeah, why not?
Okay.
Morning, Professor Rao. Yes. Hi, Somesh. Yes. Morning, Professor Malik.
Good morning. Good morning.
Yeah.
So, good morning.
Morning, Professor Balakrishna.
Good morning, sir. Good morning.
Professor Srinivas.
Good morning, Professor.
Good morning.
Yes, good morning. Good morning, Professor Sumesh Kumar. Good morning,
Yes.
Boss.
Good
Yeah,
morning.
good morning. Good morning.
Good morning to all, professors.
Yeah, good morning to all.
Wow.
Yeah.
Namaskar, brother
Namaskar.
Malik.
Namaskar.
I think the Namaskar has a better attraction than good morning.
Yeah.
Okay. We can do it one more. Yes.
Yes. In COVID-19 situation, it is much better.
Yeah.
Yeah. Everybody.
Exactly.
So,
Yeah,
can
even I
you
think,
hear me? This is
someone
Jayant
we saw
Deshpande.
they were doing-
Right. Yes.
Can you
right.
hear me?
That's right.
Hello, can you hear
Sir, you are
me?
from Cochin?
Yeah, I'm from Cochin, yes.
Yeah.
I studied in Cochin, sir. Girinagar Central School. Long
With,
back. 60s and
No, which
73.
subject?
I was in school at that time.
Oh, okay. Central school, maybe. Yeah.
Yeah. But
Yeah.
many people from Cochin University used to be in our neighborhood. Some of them even taught me, particularly oceanography department.
Oh, yeah, that is in Maran campus. Yes.
Yes, sir.
Hello?
You know Malayalam, sir?
Oh, yeah, very well.
Okay. I do still keep looking at the movies. I used to write Malayalam also. Okay.
Yeah, good.
Hello, can you hear me?
Yes, sir.
Yeah, because in the email, I think the
can.
first link
Good.
was given for Hall D. That was
So,
the
should we start the meeting?
Yes.
Yeah.
Yes.
Hello? Hello?
Sir, you please leave the meeting here, sir. Deshpande, sir.
Yeah?
You click the leave meeting from here
Uh-huh.
and then click on the Hall A link. There is one more link on the email. Hall A.
Okay. I'm in hall A now. So you can hear me?
Yes, sir.
Yeah, I can hear you. Can you hear me?
You again joining the Hall D only.
Yes, sir.
Yeah, you can hear me. So I'm in hall A now.
Shall I call sir once again? JV Deshpande sir.
Well, I'm in
You will
hall
call,
A
please,
now.
Sir, sir,
tell him that the
you are
second
again
link
joining
is
the
the
Hall D only.
Yes, sir.
second link in the latest email.
Okay, I'll see.
Sir is joining
There
it.
is a link in WhatsApp. Check it.
Yes, spoken. Double it.
Sir, on the email, you see Hall A link on the email.
I haven't got
You
any
just
email
open-
at all. I've got only the
Yeah, in the email, sir.
WhatsApp.
Yeah, sir, Nanda Kumar, sir, do you have the Hall B link with you? Can you please forward it to Dr. Deshpande, sir?
I think that order change in the email created some confusion.
Yeah, generally the tendency is to click the first link. So
Yeah.
But all the links,
Deshpande, sir, I think you're still in
That is
Hall
what,
D.
yeah, that is what we were
Yeah,
doing.
I'm in hall D, but what should I do? I mean, I haven't got any other link.
That's, but I think that did not work today.
Sir,
that is not working.
what you do, I'll just give you a number, sir. You just note down this number once.
Okay. What is the number?
Madam, did you talk to him recently?
What is the number?
Yeah,
Yes, sir. One of our person
883
contacted sir, and sir
Double
said
83
that he will be joining.
883
I will also
22.
call sir once.
No, don't call very frequently. So.
No, from beginning
Yes, sir.
883
Sir might get
Yes.
confused.
2217
883 2287
1241
2287 12.
No, I'm telling you from the beginning, sir. I'm telling you from the beginning. 883
Yeah. 883
and 2217
2217
1241.
1241.
And the password will be
So-
123.
Okay. So I
Password will be
should,
123.
yeah. So on Zoom, I should,
You should leave this meeting. Then
yeah.
it will ask for passcode and meeting ID. No, there you click
Yeah.
the 883 as the ID
Okay.
and password as 123.
Okay.
You will come to Hall A.
Yeah, will do.
Okay, sir?
Yeah.
We are waiting, sir. Thank you, sir.
Jayashree madam. Professor Jayashree.
Madam is talking to sir again, Deshpande sir. So Jayashree madam is talking to Deshpande sir.
Jayashree madam, can you hear me?
Jayant 921.
So ma'am is talking to Deshpande sir on mobile.
Deshpande sir is connecting to
No, I think if he gives his consent, I think we could start the session. Already 9:43. Sir, shall we start the session? You can join in between.
Yeah, I think it may be better to start.
Yeah, so I just talked to him and asked took his permission to start. So he may join in between. Shall we do that, Professor Bose? I think you are muted, sir, Professor Arubus.
Yeah, okay.
Yeah,
we can start.
So I think let me just start the program and he will join in between.
Okay.
So,
Okay, sir.
So very good morning and welcome to the first session of the day, that is plenary talk by Professor Arup Bose. Professor Arup Bose is a professor at Indian Statistical Institute, Kolkata. And I leave the remaining details to Professor Deshpande to say afterwards. So now I request Professor Bose to start his talk.
Okay, let me share my screen. It is
Sure, yes, sir.
always a pleasure and an honor to be a speaker at ISPS, and I thank all of you who are instrumental in allowing me to talk here. My screen sharing is disabled. That's what it says. Host disabled participant screen sharing. So somebody has to give me permission.
Yeah. Please permit Professor Bose to share his slides.
Yes, sir.
Yeah? Sure.
Now you can, sir.
Yeah, okay.
So just try once.
Okay. Can you see my screen now?
Yes, sir.
Very good.
Yeah, it is
Alright.
visible. Yeah.
Okay. So if you recall, I gave a talk in the previous ISPS conference that was in September, where I had given some introduction. And so I will try to build on that. I wanted to add something lot more, but I could not because I got bogged down with several other commitments. Anyway, so there'll be something new in this talk compared to the previous one, and there'll be something old also. So where do articles on random matrices appeared? I had mentioned this earlier also. So there is a journal completely devoted to random matrices theory and applications from 2012. So it's celebrating its 10th anniversary. Articles on high dimensional random matrices, also, which is where I work, also appear in computer science, life science, physical science, mathematical science, engineering science, etc. I mean, of course, matrices are everywhere, but random matrices, including the high dimensional ones, have been finding applications in so many other areas. There's a huge explosion of articles on random matrices. So what is a random matrix? A matrix, all whose entries are random variables. Or you can think of a collection of matrices from where you pick according to some probability law. Irrespective of what, you can think of that matrix as having entries which are random variables. And of course, classical statistics is full of examples of such random matrices. For example, you can think of the contingency table, R by S contingency table, or the data matrix, or the random design matrix, the sample covariance matrix, or the Wishart matrix when you assume that the entries are Gaussian. Started way back in 1928. That was one of the earliest non-trivial examples of random matrices. I put that in bolds because this is something that I'll discuss a little bit in this talk. And then there is this Wigner matrix, which came up in nuclear physics in 1955. The Topli's matrix with IID entries, or the Hankel matrix with IID entries, they're very well studied in operator theory. And then the IID matrix, where all the entries are assumed to be independent and identically distributed. And there are beta matrices, which are very important in particle physics. So they are sort of a generalization of the sample
power. It was.
Yes, madam.
The joint distribution of the eigenvalues. And then I'll talk quite a bit about the autocovariance matrices in high dimensional time series. So as we all know, the unadjusted P by P sample covariance matrix is S, which is XX star by N. So this vector, so there are N observations. So you can think of X as P by N matrix, and each column is the data on the P-dimensional vector, and you look at XX transpose, and then you have to average scale it by N. So this is of course a key matrix in multivariate analysis. And we also know that when the entries are Gaussian, then S is called a Wishart matrix, and the joint density of the eigenvalues can be calculated explicitly, and they are of course used in statistical inference, for example, principal component and other multivariate methods. When P is fixed and N is large, the subtle limit theorem arguments can be used to study the large sample properties of S. So remember that X is P by N, so that P is the dimension of the vectors of the, so if P is fixed, then the dimension of the vectors is fixed. Then of course, as N goes to infinity, you are in the repeated sampling situation, and one can prove that the joint distribution of the eigenvalues is asymptotically normal. So this is what is used for inference purposes. But when P is also large, the standard tests will break down. So this hotel NT square and other things, they will not have enough power. And the behavior of the matrix is very different in these cases. And I'm going to mention what how the behavior changes. So next matrix that I want to say is the autocovariance matrix. So suppose x1, x2, xn is a mean zero stationary stochastic process. And then the autocovariance sequence is defined as gamma h, which is expected value of xt plus h. Remember, x is real valued, so you look at the lag difference. So xt and xt plus h, you take the covariance of that. I've assumed that the mean is zero, so there is no centering needed. And then one can consider the dispersion matrix of x1, x2, xn, as you can realize that the covariance between any xi and xj will depend on the lag, on the difference I minus j. And hence the dispersion matrix sigma n will look like the following that I've displayed here. So all the diagonal values will be same, namely gamma 0, and then the first diagonal will be gamma 1, and so on. So these kinds of matrices which are constant along specific diagonals, they are known as Toeplitz matrices. One can then think about the sample autocovariance matrix. So this was in the population because you have put expectations everywhere. So you can think of the corresponding estimates. So of course, the hth order autocovariance will be estimated by the sample average of the lag products. So xt plus h, j equal to 1 to n minus h, and then you average it. And you divide by n minus 1 so that you stay positive semi-definite. If you divide by the number of terms that you have, namely n minus 1, then the corresponding autocovariance, sample autocovariance matrix may not remain positive semi-definite. So then we get this sample autocovariance matrix gamma n x, which is you put the estimated values in the original matrix. So then that becomes the sample autocovariance matrix. Of course, this is a symmetric random matrix because it depends on the observations xt's. Now, in this talk, I'm going to focus more on the high dimensional case, namely where the dimension p becomes large, and the mathematical formulation is that p goes to infinity together with n also going to infinity, and then you can have some assumptions on the relative rates at which p and n go to infinity.
Sorry to disturb you, sir.
Yes.
Good morning, Deshpande, sir.
Okay, he's here.
Welcome you,
Right.
sir, into the session.
Yeah, I am here, and I'm sorry that there was some problem initially. Please, Dr. Bose, please continue.
No problem. Okay.
Please continue, sir. Sorry
Okay.
for this inconvenience, sir.
Okay,
Thank
no
you,
problem.
sir.
No problem.
Thank you, sir.
No problem. So high dimensional matrices come up naturally in high dimensional models. So I assume that xt's are p dimensional observations, and there are n many observations. So the sample size is n, and the dimension of the observations is p, and both p and n are assumed to be large. And then the sample covariance matrix is high dimensional because it's a p by p matrix. And as I mentioned, that the usual formulation is that both p and converge to infinity, and there might be some assumptions about the relative rates at which p and n go to infinity. And as I had mentioned earlier, that the usual procedures do not perform well in high dimensions. Namely, if p becomes large, then either your standard procedures are not going to work. So from that point of view, understanding the properties of high dimensional random matrices is important, specifically the sample covariance matrix also. To understand the reasons for failure of the standard procedures and to devise new methods for statistical analysis. So let me move to the main matrix that I'm going to discuss here, which is the autocovariance matrix sequence. Now, earlier I had mentioned the one-dimensional observation. So x1, x2, xn was a real valued time series, and we talked about this autocovariance matrix and its corresponding sample version gamma n x. Now I'm assuming that the xt's are p-dimensional vector value time series. So earlier we had the real value time series, and so we had a sequence of autocovariances. Now for every I, we get a p by p matrix gamma I, because if I take xt, which is a vector, and then I take its transport at lag I, and then you multiply, then you get a p by p matrix. So and you take the expectation, that is the ith order autocovariance matrix. And each of these autocovariance matrices, of course, of dimension p. And as you change n, you're a host of different autocovariance matrices. The sample autocovariance matrix of order I is the corresponding sample version. Namely, so you take xt and you take the lag value at t minus I, and you take a transpose. So xt prime for every t is a matrix, and you take an average of those matrices to get your gamma hat I. Now also note that unlike the gamma hat 0 that I had mentioned earlier, all these matrices are non-symmetric matrices, because they do not appear in the xt and the xt prime values do not appear in a symmetric way in the construction of the matrix. And it is known to people who work in large dimensional random matrices that non-symmetric random matrices are notoriously hard to analyze. And one way out is to resort to some kind of symmetrization. For example, you can take a matrix A and you take these transpose and add them to make it a symmetric matrix, or you look at its singular value, namely you look at A star and consider its eigenvalues and so on. So this is just a way out, and of course there is a loss of information if you do that. But non-symmetric matrices are very, very difficult to find their properties, especially in this random matrix context. There are very few results known. I'll mention one or two as I go. So then for these matrices, which are high dimensional matrices, what should we study? Of course, matrices are linear transformation, and its features are captured by its eigenvalues. So we could study the eigenvalues in some way. We'll give a brief glimpse only into the behavior of the bulk of eigenvalues of sample covariance and sample autocovariance matrices, and I'll very briefly mention some applications. Of course, there are other aspects that people have worked on, and as I mentioned, it's a huge literature, and there are many important developments in this area. So for example, one could look at the joint behavior of random matrices. You might have more than one sequence of matrices. For example, as we have different autocovariance matrices of different orders. So we can think about how they behave jointly, and that gives rise to a concept known as the free independence. Or one can look at the behavior of the extreme eigenvalues. Again, some results are known for very specific matrices, and almost nothing is known for the autocovariance matrices as far as the extreme eigenvalues is concerned. I think there is some noise here, so please mute yourself as I speak.
Yes, I request all others to mute the mic so that the speaker will not.
Thank you. Yeah, because others cannot hear otherwise. Yeah. Okay. So one can think about the behavior of the extreme eigenvalues. That's a very difficult area. And there are very few results known, say, for example, the Wigner matrix or the IID matrix. And so you can get very new types of limit distributions. And some of them are not even known in any explicit forms. One could also study the behavior of the gaps between eigenvalues, and that is linked to what are known as determinantal point processes. And of course, once you do the studies, then you use this knowledge of these aspects to develop statistical procedures to analyze high dimensional data. And as I mentioned, even the basic results on extreme eigenvalues, there are not too many. So one needs more tools and techniques to develop this area and put them into applications. I'll be more interested in what is known as the bulk of the spectral of the eigenvalues. So this is how it is defined. So suppose I have a p by p random matrix with eigenvalues lambda1 to lambda p. Then the empirical distribution of Rp is the probability distribution that puts probability 1 over p at each of these eigenvalues. So this is very similar to the empirical distribution function. You take these values instead of the observations, you take the eigenvalues, and you think of them as having equal probability to come in your sample. So this probability distribution varies from sample to sample. So it is of course a random probability distribution, just like the usual empirical distribution function is. and it's a cumulative form. I will just define it because in one couple of slides I'm going to use this definition. So if all the eigenvalues are real, then you can take the cumulative version of this probability, and that is usually called the empirical cumulative distribution function. We can also consider the histogram of these eigenvalues, and the limit results that I'm going to mention, you can view them as results on the histogram of these the eigenvalues. And so once you have this empirical spectral distribution, then you can talk about its limit. So just like we have any sequence of distribution functions, we understand what we mean by the limit of that sequence of distributions. The only difference here is that the sequence of distributions that are under consideration, they're all random probability distributions. So that is known as the idea of LSD. If as p goes to infinity, this empirical spectral distribution converges weakly. And for our purposes, these are random distributions, so we must be specific about in what sense. So for our purposes, almost surely, pure probability distribution, then the limit is called the limiting spectral distribution. Loosely speaking, if the histogram stabilizes as p goes to infinity, then the limit curve defines the limiting spectral distribution, if you don't want to be very formal in your mathematically precise. This is called the convergence in the bulk, since any finite number of individual eigenvalues do not matter in the limit. So you're putting all the eigenvalues in one box and you're trying to see what happens overall instead of looking at the maximum or the minimum or the other eigenvalues. Okay, so here is what happens. For example, if you can simulate this very easily yourself. So this is what happens for the sample covariance matrix. So I have taken this X matrix, which is the IID matrix, this is a P by N matrix, and I have looked at XX star. And so that is the sample covariance matrix, and you scale it by N. And as you can realize here, the distribution depends on the ratio P by N. So the first graph P by N is 0.25, and this next one P by N is half. And so the nature of the curve changes as P by N changes. And of course, if P by N is bigger than 1, then realize what happens. Then the dimension P is, so X was P by N, so the dimension P is bigger than N, and of course the S matrix will have a maximum rank of N, so there will be a lot of zero eigenvalues because S is P by P, and so a mass will appear when P by N bigger than 1, which I have not given in this simulations. So this is very easy to simulate, and you can check it. All right, so having done that, let's go back to the autocovariance matrix that I had introduced. So recall that XT was a real valued mean zero stationary process, and gamma H is the autocovariance, and the sample autocovariance was the sample version of the dispersion matrix of X1, X2, Xn. As we had realized, it has a Topi structure, but the entries are dependent. And it's very interesting to see what will happen to this matrix. This is now an N by N matrix, because I have N observations. So I have gamma hat 0 and then gamma hat 1 and so on. So this is an N by N matrix. I have very few observations in the corners of the matrix, but as N goes to infinity, all of these diagonals are going to contribute in some way or the other. And it's not clear what is going to happen to the empirical distribution function as I increase my dimension N. But on the other hand, we know that the sequence XT is a mean zero stationary time series. So under suitable assumptions, it also has a spectral density. And it is quite imaginable that the spectral density will come up in the limiting spectral distribution. So this is what happens. I'm not going to give you a precise theorem. It's a little complicated. The limiting spectral distribution of this autocovariance matrix exists, and the properties of the limiting spectral distribution are not known in closed form, unfortunately. And the limiting spectral distribution is connected to the spectral density of the process, and the distribution is unbounded. But what is also very interesting is that you cannot recover the density from this limiting spectral distribution. In other words, two different spectral densities can give you the same limit. Okay. So this was my first limit result that I wanted to mention. But remember, this was when the dimension P is equal to 1. What I'm doing is I'm looking at the autocovariance matrix and looking at its sample estimate, and then trying to study its properties. Okay, now let's move to the high dimensional case. So in the high dimensional case, I'll need to introduce some assumptions. So I assume that Xt, which is a p dimensional vector time series, p is going to go to infinity eventually. I assume that that's a linear time series. And we know that all these moving average ARMA models, etc., they're all linear time series. So, so I take this linear time series. So here, the psi j's are matrices. These are called the coefficient matrices. So like, for example, in the autoregressive, usual autoregressive case, so these are parameters. So psi j's can be thought of as parameters. And the epsilons are vectors. So they are all p-dimensional vectors. I'll assume that the epsilon t's are IID with mean 0 and variance covariance matrix IP. Now you can have a non-identity variance covariance matrix. The results will remain, but they'll start getting more complicated to state. And we assume that P and N both are going to infinity, and you can think of N as being a function of P, such that P by N goes to Y, which is between 0 and infinity. And Y equal to 0 is left out of this talk. I'll maybe make a brief mention at the end about what happens when Y is equal to 0. So that is the case where the dimension P is relatively small compared to N, but both are going to infinity, remember. And the other case, of course, will be that when the dimension P is too large with respect to N. So, and these are sort of complementary to each other, because the non-zero eigenvalues of x star and x star x, they are the same always. So, the specific case in equation 1, where all the psi's are 0 except for the first one, namely the psi 0, I will call that the MA0 process. So the autocovariance matrix sequence, as we had defined, the P by P sample autocovariance matrix of order I of xt equals gamma hat I, which is equal to 1 by n xt plus 1, xt plus I transpose. Remember that each xt is a vector, so each xt plus I transpose is a matrix of order P. So gamma I hat is a matrix of order P. Also note that as I had mentioned earlier, if I is equal to 0, then this matrix is symmetric, which is the really the essentially the sample variance of the xt's. And the autocovariance is when I is not equal to 0, all of these matrices are not symmetric. And for the most part, we shall resort to additive and multiplicative symmetrization, such as gamma I star, etc. So in general, I can take these matrices gamma I, finitely many of them, and take any kinds of combinations of these matrices so that I can get a polynomial of these matrices. And usually that polynomial will be assumed to be symmetric. So here is my second limit result. Again, I'm not going to give you any mathematics here. Those who are interested can go and check the references that I will mention at the end of the talk. So this was done by one of my students, Monica, and myself. There are a series of papers, and I'm going to give you in a nutshell what happened in these articles. The limiting spectral distribution of any symmetrized matrix polynomial of the sample autocovariance matrices exists, but it is not possible to write the limiting spectral distributions explicitly. These LSDs can be described in terms of what are known as free variables in a non-commutative probability space. So that's a very technical result, and one has to have a lot of machinery to understand really these limits. But free variables are roughly like independent random variables. But realize that for the matrix, there is no commutativity. So the usual notions of independence do not apply for matrices. So there is a notion of independence in the non-commutative objects like matrices. And this freeness is the corresponding notion of independence for non-commutative objects. So that's a very, very technical thing. But unfortunately, without that, you cannot really, just like in many statistics limit distributions, you can express the limit in terms of further independent random variables. For example, the Kramer-Von Mises statistics, the limit is a sum of independent random variables with some weights. So here also the limits can be expressed in terms of within quotes independent random variables, which are called free variables. So when P by N goes to 0, then something different happens. You cannot look at the gamma I hats itself. You need a different centering and different scaling. And with that, one can still look at the polynomials, the symmetric polynomials, and prove the same kinds of results. So that's slightly more harder than the P by N going to Y, which is not 0 case. The limits can be used, of course, for statistical inference, and I'll spend a couple of slides on just giving a very brief glimpse of how they can be used. And as I had mentioned, very limited results are known for the non-symmetrized autocovariance matrices. That's a very wide open area to find, very challenging to find the limiting spectral distribution of any symmetric, non-symmetric autocovariance matrix. Okay, so because there are no general results for non-symmetric matrices, let me give you one simulation at least, and maybe mention a couple of results that are known. So the empirical spectral distribution of gamma 1 hat for MA0 case. So what have I done here? So I have taken epsilon t to be p by 1 IID random variables. You can take any distribution that you like. The limit distributions are all going to be independent of the underlying probability distribution, just like in the center limit theorem. So the limit distribution does not depend on what parent distribution you choose. So this is gamma 1 hat, which is 1 by n summation epsilon t minus 1 star. Of course, as you can realize, this is a non-symmetric matrix. And if you simulate with n equal to 500, and the errors to be maybe, as I mentioned, whether you can take normal or Bernoulli or whatever, they are all standardized entries. So you get these two pictures here. The one of them is for p equal to 250 and the other is for p equal to 500, and n is 500 in both cases. So the p by n ratio y is half in the first case and p by n is equal to 1 in the second case. So it's clear that the limit, if at all, is going to depend on this y. And it's also clear that there is some kind of limit there. So the points are very systematically, symmetrically distributed around it. Note also that this is a bivariate plot, because the eigenvalues of this matrix are going to be complex numbers, because the matrix is non-symmetric. So here is the result for this matrix gamma 1 hat, but only in this special case where the epsilon t's are where the xt's are white noise, namely that I'm not looking at the general moving average process. I'm looking at this specific case where all the other coefficients are 0. So suppose we have a complex valued time series with a non-trivial real and complex part, and suppose p by n goes to suppose p and n both go to infinity, such that p by n goes to y, which is non-zero. Then the LSD of gamma 1 hat 0 for this process exists in the complex plane, and as we have seen in the picture, it is rotationally invariant. The proof of this is highly non-trivial, and some description of the limiting spectral distribution is available. One can write down a reasonable formula for the limiting distribution, and the limiting distribution will have a density, except for the case where p by n is bigger than 1, where you have a point mass at 0. But other than that, and so you can look at this reference if you are interested. And the same LSD holds for any gamma I for the moving average of order 0. The limiting spectral distribution of gamma 1 hat for the moving average order 1 has been developed in Bose and Hachem, and it's not like for order 0 you have a paper, and for order 1 you have another paper, and so on. The point is that these problems are extremely hard, and as soon as you change the nature of the matrix a little bit, then it becomes a completely different problem. I hope at someday enough progress will be made where you can have a general theorem, but until then, these are the two results that are currently available. And finally, the final result on asymptotic normality of the trace. Remember that I had said that for any matrix polynomial, you can find the limiting spectral, you can show that the limiting spectral distribution exists. And the way those results are proved is by looking at these matrices and calculating their trace and try to study the behavior of the trace of these matrices. And so while doing that, one can also show that if you take any matrix polynomial, if you take a trace of that, then asymptotically, after proper centering and scaling, asymptotically, all of these traces will have asymptotic normal distribution. Of course, what normal distribution will depend on what polynomial you take and what are these coefficient matrices, Scheij's. So these ideas can also be used to show that trace of any polynomial after centering and scaling of the sample autocovariance matrices is asymptotically normal. Okay, so as I mentioned, as I promised, I'll give a very quick glimpse of applications. First of all, for graphical inference, you can do, for example, you can do white noise testing, or you can test other hypotheses. So let me show that with some plots. So if I had actually my process is moving average of order 0, and if I look at gamma hat 0, then of course I have the Marchenko-Pastur law. This we have already seen, and this is the cumulative version of that plot that I had shown you earlier. And if I start with the moving average process of order 0, and I look at this this matrix here, namely the singular values of gamma u star, and no matter what you take, the order of your autocovariance, you are going to get the same plot. So this curve that you see here are actually 4 different plots, 4 different curves, and they are really coming one on top of the other. So in other words, the spectral distribution in this case, for each of these gamma hat u star, for every u they are going to be same. So this is happening because you have a moving average of order 0. Now I'll take 2 more minutes. I'm almost done. I'll finish more or less in time. Okay, so this is what happens when you have a moving average of order 0. Now let us see what happens when you have a moving average of order 1. So in this case, I again look at this same matrices, namely this gamma hat u star. But now you can see that 3 of these processes, namely gamma 2, gamma 3, gamma 4, u equal to 2, 3, 4, they will be different, and they are all they are all different in the sense that they are different from u equal to 1, but they are all going to be the same with respect to each other. So in other words, you can very quickly pick up the order of your model by looking at these plots. So because the order is 1, you see only 1 curve shifting out, and if the order is 2, you will see the first 2 curves shifting out, and so on. Okay, so that you can see here. So if I have a model of order 2, then the first 2 curves will shift out, and the other 2, namely the u equal to 3 and 4, they will be superimposed. They will remain the same for each other, and they will be different from the first. Okay, similar patterns if you use other combinations. So you can choose your own matrix combinations. You get the same kinds of patterns or same kind of deviations, and they will pick up the order of the model very easily. Applications too. This is very commonly used in high dimensional time series in many different areas. Spectral distributions might be harder to get results on that, but traces are easier to tackle. So people have looked at very specific matrices and very specific trace, and they have done the testing with respect to those traces. But what our result will tell you that no matter what polynomial you choose of these autocovariance matrices, the trace is always asymptotically normal. And you can find out reasonable formulas for the asymptotic variances. They of course depend on the matrices, unknown parameters, and so on. So significant testing of suitable simple versus simple hypothesis involving the coefficient matrices can be done by using the asymptotic normality of traces of these polynomials. All right. So with that, I sort of end. I have 2 more slides. In one, I'm giving you the journal references, and in the other. So if I pause for 20 seconds for you to have a quick look if you want to make a note, or I can make the slides available to all of you. If you request, I can send it to you. So this is the paper that I was mentioning that does the gamma 1 case for moving average of order 1, and this is still not published. And the works with Monica, these are all appeared in Annals and IJPM and Random Matrix RMPA. So these deal with all kinds of polynomials and the traces of these polynomials. And if you're interested to get into this area, right now there are a lot of books available, and one of them was written by myself and Monica, which deals with the main topic of this talk today, namely the covariance and the autocovariance matrices. Okay, thank you very much.
Well, thank you, Professor Bose.
Thank you.
For
you are Professor Deshpande, you are muted. Yes.
We have got a gist of the area, and apparently one can have some reason for testing the null trace of these matrices. Could you please elaborate on that?
Yeah, it's right now it is only for white noise testing, and Some people have used it for other kinds of testing also. So you have two competing models, and and usually finding out the limiting spectral distributions are hard as soon as you go to the non-null case. But what usually people do is take the autocovariance of order 1 or 2 or something similar, something simple, and then look at their trace. And so the behavior of the trace under the null and the alternate will be different, but both of them will be asymptotically normal. So that's the way out that people have been taking.
Okay, so even the non-null distribution would be
for the
normal,
trace. For the trace, it will be normal. For the trace,
with changes in the parameter value.
Yes, with changes in the parameter values.
Yeah. So, are there any other questions from the audience? Please open your microphone and ask.
I just want to make.
I'd like to compliment both sir for this. Like my background is statistics, all right, but from image processing point of view, where I've spent all my life, you have got testing with respect to eigenvalues, which you have mentioned well. But what happens is the rotation comes from the eigenvectors.
Yes.
So is there any mechanism by virtue of which you would advise us to test our rotation matrices? For example, in Nader viewing, a tolerance of plus or minus 2.74 degrees is acceptable. But when that tilt angle changes, the game changes again. So can you advise with respect to vector testing?
Yes.
Another point also I would like to compliment you is you're working on random circulant matrices. In digital image restoration, we use it extensively, but we use a little more complicated version called block circulant matrices. Here again, because of the vehicle-induced motion, a lot of random noise steps in. So now I leave the floor to you to advise me, sir.
Okay, so first of all, I have not worked on the random vector problems. They are much harder than the eigenvalue problems. But there are some articles on random vectors, which I am not an expert to comment on those. But there are works by both statisticians, probabilists, and also people who are from the engineering sciences, especially computer science. So there are some works, but I'm not too aware of those things.
Appreciate.
Yeah, very difficult problems. And
I appreciate it.
For the block circulants, there are some results on the block circulants, but again, I don't have the results right now with me. Yes, the
Andrews and Hunt is a great book, sir. You can refer to it because you already have spent so much time there. I'm sure you'll get phenomenal lead.
Okay,
I really enjoyed programming it there.
Okay, thank you very much.
Okay, any other question?
No, I just want to make a comment. Professor Arubo's talk is an excellent talk, and I should also mention, probably he didn't mention in his slide. He is also an editor for the Random Matrices Journal, and it shows his contributions. And I just want to comment. Yesterday, I gave this talk on big data and high dimensional data. And I told at that time that high dimensional data need new techniques to analysis. Old techniques do not apply anymore when P is much larger than N and so on. So this is an example where new techniques are being developed for high dimensional data analysis. So this is just a comment for all of our statistical friends who are attending these lectures. So this is what I mentioned yesterday. For high dimensional data, classical methods do not help. And of course, big data, they don't help at all. And this is an example where new techniques and matrices and random matrices are very useful. And I congratulate Professor Arup Bose for an excellent talk and his great contributions to this area. Thank you.
Thank you very much, Professor Prakash Rao. Any other comment or question to the speaker? Well, if not, let me take this opportunity of thanking Professor Arup Bose for the very thought-provoking and knowledgeable talk that he just gave. I'm sure it will lead a lot of people to the latest work in this area, particularly if you read his books. I'm sorry that I was late in joining the meeting. I don't know what went wrong because, in fact, before the meeting started, I and Arup Bose were chatting exactly on the same channel for half an hour. And then when the time for the meeting to start came, we just couldn't do that anymore. And I wonder what happened. But anyway, all that ends well is good. So we are very happy to have him here. And I thank the organizers of the conference. I thank the organizers of the conference for bringing such distinguished researchers like Professor Prakash Rao and Professor Arup Bose together on this platform so that the younger people can hear their multifarious contributions and important contributions. Thank you very much.
Thank you, Professor. Thank you, Professor Deshpande.
Thank you very much, sir. We are grateful to Professor.
Thank you. Bye. Bye, Arup.
Is this hall D?
Yes, sir.
Yes. Okay. So I think Professor Shankar is supposed to chair the session, I believe.
Yeah, Shankaran sir is the chair.
Sudesh, can you call him?
Hello, sir.
Hello, Dr. Satish.
Yeah.
Yeah, but where is Professor Shankaran?
Let us wait. Yeah, he will join soon. We hope to join.
But I hope he remembers.
Yeah. Whether we need to call him?
Yeah, if you can call him, I think it will be good.
Yeah, I shall try.
Okay.
And now he
Sir,
another.
Sir, I just called him.
Yeah. Okay.
Yeah, he actually out of station. He already informed the organizers. That's what he told me.
Okay, I think then Professor Srinivas Rao can take over the chair position. Yeah, just you have to tell me some timing. That's all. Nothing else.
Yeah. Shall we start or we have to wait?
No, I think we can start. It's only 10:30 now. Why to wait?
Yeah, we can start. Professor Balakrishna is very much well known to everyone in this ICSDS conference. He is a well-known statistician in India, and he has published a lot of papers, and also he has done a great work in particularly in time series analysis and the stochastic processes. He hails all the stochastic process knowledge from Professor Adike, I can think, because he is the student of Adike. Whenever I see Balakrishna, I remember Adike, because such a great people. He is the student of Adike, and he has visited abroad several times, and he has published a lot of papers, and also he has been associated our ISPS as a president at present, and he has taken several initiatives, and also he is a distinguished statistician awardee, and he got several other awards. He is a senior professor in QSAT. And with this brief introduction, I think that all the people does not require any introduction of Balakrishna. We young people as well as the elder people, we both know Balakrishna is a great statistician. And now I request Balakrishna to deliver his talk on this non-Gaussian part of the thing, which we are eagerly looking for his lecture. Sir, Balakrishna.
Okay, thank you. Thank you very much for your, what is that, generous introduction. So let me just. Can you see my screen now?
Yeah.
Yeah. Okay.
Yeah.
Okay. So, so this is on non-Gaussian autoregressive type models. In fact, I mean, I don't claim any new research in this talk. This is actually because recently I have published a book on non-Gaussian autoregressive type time series. It's published by Springer in 2021. I just want to give a brief overview of that particular book here. So that is what my idea in this talk is. So
sir, can you make it full screen?
Okay,
better view. Yeah.
Okay now?
Yes.
Yeah. So this is the outline, a brief introduction, models with the specified marginals. So when you talk about non-Gaussian time series, there are several considerations one has to take. Either you can study the properties in terms of the marginal distributions or joint distributions, or in terms of the properties as a consequence of specific error distribution. And there are several other structures which are used to specify the non-normal, non-Gaussian time series. And this is just a brief overview of that. Okay. So time series, I think after hearing an advanced talk by Professor Bose, I don't think I need to give any elementary introduction. So time series is, one can think it as a realization of a discrete parameter stochastic process. Okay, for an elementary level, it could be any sequence of observations collected at equally spaced time parts. I specify equally here. One could also think about unequal time series. Okay, so now, say time series basically is a sequence of dependent random variables or observations. And we can use the dependent structure of time series to forecast its future behavior. If they are totally random, I don't think that will help us in forecasting. But because they are dependent, by exploring the structure of dependencies at time point t in terms of the previous observations, we could study the dependent structure and try to put it in a mathematical form, and then use this mathematical equations to forecast the future behavior, subject to, of course, some random errors. Okay, so one of the simplest models which you could think of in time series is the autoregressive model of order P, which resembles the structure of the classical regression model, the multiple linear regression, with an error term AT here. The only difference is that in the regression context, we use some any arbitrary or other related independent variables. But in time series, the role of regressors are taken over by the past observation of the same time series. Okay. To be more simpler, I will just focus on AR1 model. That is, the observation at time point t depends only on its previous value xt minus 1, and I need this condition on phi for stationarity. So I mainly focus here on the strictly stationary time series. Okay. So if you assume that AT follows a normal distribution, then of course all random variables also be marginally normal, as well as all finite dimensional distribution will be multivariate normal. But when you deviate from this normality, there are several things one has to consider. One can always ask, why do you so particular about the marginal distribution or the error distribution? Of course, one can ask several questions, but when I talk about non-Gaussian time series, I'm not only worried about just AT as an error term, because in the analysis of point processes, there are problems where the sequences of successive intervals are not independent. They could be dependent, so that one can also study the properties of counting processes induced by a stationary Markov sequence that is known as the WOLD process, WOLD. Okay. These are several laws in our counting processes. So now here if I want, because in the counting process context, we mainly focus on the marginal distribution. If I want xt to have a specified marginal distribution on the non-negative support, what will be the corresponding distribution of AT, which gives me a stationary sequence of xt? Okay, so for a specified marginal distribution of xt, if you are able to provide or identify a suitable distribution of AT, which meets our requirement, then we say that the model has a solution. Okay, to verify that, one has to study the distribution properties. One tool which one can use is the generative functions. Okay, suppose that the distribution of xt has characteristic function, say this psi x of s, then using this equation and independence of this xt minus AT, I could write the characteristic function of xt in this form, and that will give me the characteristic function of the error random variable as psi x s by psi x of phi s, where mod phi is between 0 and 1. Now, in general, the ratio of two characteristic functions need not give you a suitable characteristic function of a random variable. But if you are able to show that there exists a solution to this, that means the ratio is a proper characteristic function for all values of phi in between 0 and 1, then there exists a well-defined error distribution for A. In that case, we say that the family of random variables belong to self-decomposable family. That is a self-decomposable class. In this, if this is true, then we say that the random variable belongs to self-decomposable class, and that provides a suitable distribution for error. Standard distribution like normal, Laplace, symmetric alpha Laplace and all, they are all members of random variables which belong to self-decomposable class on a real line. In the class of non-negative random variables like exponential, gamma, inverse Gaussian, log normal, these are all self-decomposable random variables on the non-negative support. And with respect to this specific class of distribution, one can always define well-defined autorecursive processes. If you are assuming normality for x, of course, the distribution of error epsilon t also normal, or AT is also normal. That is a characterization of class of stable distributions. Right? That means in an AR1 model, xt equal to phi xt minus 1 plus AT. If you assume that xt is normal, then AT is also normal. Or if AT is normal, xt is also normal, they are equivalent. They belong to the same class. But that doesn't happen in several other cases, non-normal cases. Okay. So these are all the elementary properties of AR1 model with the Gaussian marginals, which is a Markov sequence. It has nice transition density functions, which can be used to obtain the MLEs of the parameters and so on. Everything is nice for a normal distribution. Okay. Now, if you are interested in studying the consequences of assuming non-normal distribution for the random variable x or AT, then there are several considerations and has to consider. Okay. Suppose to illustrate this problem, I'll just consider this is an old problem. It's a not new one. This was discussed by Gower and Lewis in 1980. If you want your xt to have an exponential distribution, the question is, does there exist a suitable distribution for AT? which gives you the marginal distribution. If I use the earlier computation of finding the solution of the ratio of two characteristic function, that becomes, for an exponential case, it is lambda minus I phi x by lambda minus is. I can write this as phi plus 1 minus phi into lambda by lambda minus is. The second term, this is the characteristic function of an exponential distribution with the mean 1 by lambda. So if you want extend to have an exponential distribution and it is stationary, then your error must have this form. This is actually a mixture of two random variables. One is degenerate at 0 with probability phi, and the other one is exponential with probability 1 minus phi. So this is the case of in the case of exponential. Of course, all other things will follow similarly. And now, for a gamma distribution, also this is a generalization of exponential. We simply have this, the error distribution of epsilon t in the case of gamma AR1 model is phi plus 1 minus phi into lambda by lambda minus is to the power p. Of course, if p is an integer, I'm sorry, just I think there is some problem with my power system. Okay, so here I have this, the error distribution for gamma random variable is phi plus 1 minus phi into this one. Of course, if p is an integer, this can be viewed as the sum of p random variables corresponding to the earlier exponential. And if it is not p also, one can identify the distribution because that's the property of an infinitely reducible distribution of property of gamma distribution, which is stated in this theorem, which was proved by A.J. Lawrence in 1982. Of course, this has a complicated form, but this can be used to simulate the required sequence of random variables. Okay. And another example is over the real line, it is Laplace distribution. In this case also, the computation follows very similarly. That is, the error distribution becomes 1 minus phi square plus lambda square by lambda square plus square. This second component, this is the characteristic function of Laplace distribution. So this is again a mixture of two random variables. One is degenerate at 0, other one is Laplace. Okay, these are some of the examples I thought of illustrating. Now, in these cases, we have the model like xt equal to phi xt minus 1 plus an error term, where error is a mixture. But when error is a mixture, studying the inference property becomes complicated because of the jump in the error distribution. And as an alternative, people have introduced the random coefficient autoregressive models. Right? So this is the general form of random coefficient autoregressive model. These are the conditions for stationarity and existence of the model. Which the details can be found in the book by Nicholson Quinn. And the simplest random coefficient ARN model, which provides you the sequence with the exponential marginals, is given by this one, that is known as near one, the new exponential autoregressive model, where xt is the random coefficient into xt minus 1 plus at, where at is determined based on the condition that xt should have an exponential distribution. So if you do the algebra like solving the characteristic function, you get the solution given here, at. That is, it is distributed as exponentially with this probability, and otherwise it is like this. So it is again a mixture of two exponential. Now the degeneracy has removed now. Degeneracy has been removed. Whenever you have mixture distribution, with obtaining inference is also not as difficult as the previous one. Okay. Now, of course, one can generalize that to near one, that is exponential of order 2. See, these AR2 models are not as straightforward as the classical linear AR2 models of Box and Jenkins. Here we have to bear with the non-standard structures, because we are insisting that the sequence should have marginal stationary distribution of specified nature. That is the reason why we get all these complications. Now, here this gives a set of conditions for the existence of stationary distribution for this xt, which takes near 2 form here. Okay, this requires a lot of conditions among the parameters of this model that are summarized in this theorem. Okay. And of course, when these are different structures, and these structures are useful for me to build the estimative functions or other procedure for inference at the later stage. And now this is a generalization to the near P model. This is actually a the random coefficient autoregressive model of order P, which provides me xt as an exponential distribution with the parameter 1 by lambda, mean 1 by lambda. Okay. This is in the standard form RC model, that is random coefficient model, but not as nice as the one which I introduced earlier. So these are all this is the structure of the corresponding error distribution. I mean, this is for AR near P model with different parameters. Now that's about the autoregressive models with the marginally stationary distribution or the positive half of the real line. Now parallel theory is developed for the autoregressive models with the specified marginal distribution which are over the whole real line. And these are in fact good for the modeling the time series data in the non-standard situations. So here the model is similar to that, but only thing is the error distributions have this structure. So this with probability 1 minus q1, it is Laplace. With probability q1, this has again Laplace with the different scale. So this is again a mixture of two Laplace distributions. Okay, this is the generalization to and similar theorem for second order, etc. And also it can be generalized to Laplace of order P. Laplace autoregressive of order P. This is the corresponding error distribution. Okay, this is the okay. Now, so what I discussed so far is that we have an ARP model like xt equal to phi 1 xt minus 1 plus phi 2 xt minus 2 plus etc. phi p xt minus p plus an error term. So far, I have assumed that I want the stationary marginal distribution of xt defined by these models have specified distributions, specified marginal distributions, and then determine the structure of error distribution. But in the normal case or in the stable case, if you assume specific distribution for xt, then distribution of at will also belong to the same class. But in non-normal case, it is not. Okay. So now I will focus on another parallel development, that is, you have the model. Now you assume a specific distribution for at, that is error distribution, error variable. Then see what happens to the corresponding marginal distribution. Okay. So that is what we discuss now. That is, this is the ARP model. Assume that xt is weakly stationary. The distribution of at is specified, and we are not concerned about the stationary distribution of course, it has to be stationary, but we are not worried about the specific structure of the distribution of the stationary process. Okay. So in certain cases, like stationary distribution is a member of the family of error distribution, for example, normal, symmetric, stable, and so on. Okay, and in this case, the inference methods are developed just based on the error distribution, not worried about the marginal distribution. Of course, it will have its own positive aspect as well as negative aspects. And I suggest that for more details, if somebody is interested, can refer my book. And in this book, actually, my main focus is to provide different inference procedures for non-Gaussian time series. And if some of my colleagues who are present here who are working in non-Gaussian time series, we have come across a lot of literature on the development of non-Gaussian time series models, where people are mainly focusing on defining the model and then establishing its existence, then focusing on the second order properties like ACF, PSF and all, then some simulation, and that's all. And no serious work is available for inference purpose. Unless we develop inference procedures, it's very difficult to check the validity of these models in real life situations. Of course, there are difficulties. You cannot put all the non-Gaussian time series model in one bucket and give a single procedure. That is not possible in this case because it depends on the distribution structure as well as the model structure. So different models demand different type of inference structure. So So that is why I mean about 3-4 chapters are developed based on the different inference methods. So now I will just describe some of the method of estimation. Professor Srinivasa Rao, how much time do I have? Please unmute yourself.
Yeah, you may have another just 5 minutes.
Okay, I think I'll manage with that.
Yeah.
Thank you. So, of course, the simplest method which one can apply always whenever there is finite variance is the Yule-Walker method. And this doesn't need any specific distribution assumption, either stationary distribution or error distribution, other than the existence of moments. Okay, so one can always go for the, even for the normal, I mean, non-Gaussian case, one can apply that. MLE, of course, if you have a nice error distribution, then by using the conditioning property of this autoregressive processes, one can write the joint density function and then apply the maximum likelihood method. For non-normal cases, writing the structure of ML is very complicated in most of the cases, but still there are some numerical methods developed to obtain the MLEs. And of course, one has to verify different conditions like Billingsley conditions and so on for applying the asymptotic theory of Billingsley. And Professor VLS or Prakash has done a lot of work in the area of estimation and testing procedure for stochastic process. And in fact, that even though it's early in one of his oldest books, that is Inference for Stochastic Process by Basava and Prakash Rao, I still always keep that book on my table. It's always helpful to me. Of course, he has written several other books after that. Now, conditional likelihood is another method. I mean, all these methods, likelihood-based method, work very well if you have nice structure for error distributions. Okay, so these are the another one is the modified maximum likelihood method, which was proposed by Professor Tico. And in this case, they propose conditional likelihood method. If the conditional likelihood function contains a very complicated structure, then approximate the complicated part of that using a Taylor series expansion, and then linearize the term, and then apply the maximum likelihood method. And asymptotically, these are as efficient as the ordinary likelihood-based methods. These are the results related to that. Properties are almost similar to the properties of maximum likelihood estimators. Of course, conditional likelihood is another method. All these methods are applicable to all the time series models which I have introduced in my book, as well as available in the literature. But different models require different separate kind of treatments. Okay. So the CLSC can be applied to all models where we can estimate all the parameters which appear in the conditional expectation of xt given the past. Okay. Then to estimate the remaining parameters, one can use the second stage CLSC. This is actually by estimating the regression parameters by the first stage. Then using that, you compute the residuals. Using those residuals, estimate the remaining parameters. Okay, they are also consistent and asymptotical normal. The another method which I proposed is the Godam-based estimating functions. Most of these estimating functions behave similar to the conditional likelihood method and the generalized method of movements. And another method is the quasi-likelihood method proposed by recently developed by Huang and Basava, and also Tavanesh and et al. They call it as combined linear estimating function, linear quantity estimating functions. Okay, and all these have properties similar to the this one earlier, the estimating function methods. Okay, these are the asymptotic properties. Okay, that means in brief, the estimating function method gives you a function which is a function of parameters and observations, and then using that solve for the unknown parameters and as a function of observations. Of course, it needs a lot of other conditions to be verified, but this is the brief procedure. Now I'm just illustrating. I think I have only one model using estimating function method or QMLE method quickly. Okay, I'm applying this Basava's Huang and Basava method on QMLE for AR models with the symmetric innovations. Okay, so I assume that the fourth moment of the error distribution is finite, and then establish the properties by verifying the conditions under which the properties of QMLE are established. Okay. For that, it needs some computations. Mainly, it is based on the conditional expectation. That is, this is expectation of XT given the previous sigma field. And similarly, this is the difference between XT and the conditional expectation. This MT and ST are the main components of the estimative functions. Then form a suitable estimative function using martingale theory. And for that, we need to compute all these partial derivatives. And my estimative function takes this form. That is Gn star of theta equal to this summation. Now equate this to 0 and solve for unknown parameters theta. It needs the numerical methods, and of course, one can solve it using the computer algorithms. Okay. And these are the final solution for that model, that is ARP model, symmetric alpha Laplace symmetric alpha distribution. And these most part of this look like Mueller-Walker equations, but it has to be solved. And the final expressions are given here. These are not very explicit, but need to be solved iteratively. Okay. Now, this is the estimate obtained in that by QMLE method is asymptotical normal with the mean 0 and dispersal matrix given here, where gamma is the autocovariance matrix of the ARP process. Okay. So this is, and similarly, one can try it for other examples, and lot of things are discussed in the book with the more details for different identified models. Okay. And okay, so this here. So further details one can refer this book. And with that, I conclude. Thank you.
So thank you, Balakrishna, for a very nice lecture. And it is really thought-provoking and it will be very helpful. Any clarifications required? One or two we can quickly. Any audience?
Professor Rao, I was unable to I'm Shankaran. I could not open this earlier. I'm out of Cochin. I'm using mobile phone. I could not get this link, this site earlier. So I'm sorry that anyway you made the session very well. Sorry, Balakrishna. Sorry, Balakrishna.
No problem.
Yeah,
we can always manage because we have friends around. We can always manage because I know that there was some difficulty.
No problem. In fact, it is my. I feel that I am very happy to chair the session of Balakrishna. Because being the presidential part of the thing, and really I enjoyed the lecture also.
I heard his lecture. Mostly 70% of lecture I could hear. First part I could not.
Sir, Prakash Rao sir, this is my first attempt to present a book. So,
well, in fact, I want to congratulate you on bringing out this book with a non-Gaussian autoregressive time series. It looks like it's very well written. I'll purchase one in the next few days. But what I want to say is there is also, you can try this martingale estimating functions.
In a way, the Basov and Huang's work, they actually use martingale estimating functions.
I see.
Yeah, but they also established this asymptotic property. That is what I have used, but it is not in a consolidated form. I used here and there as of my requirement.
Yeah, that's fine. That's fine. So this is a very well written. It looks like, and I again congratulate you. Your talk is excellent talk, and we are very happy to hear that. Thank you.
Thank you, sir. Thank you. Thank you very much.
Thank you, Professor Prakash Rao Garu, for your very nice words to Balakrishna. In fact, you are the inspiration for all the people who are working in stochastic processes for this generation. Inferences in stochastic processes. You and Professor Adike, you both are the people who have done a significant work in this area, sir. We never, whoever will be doing. Thank you for in this session. And I once again thank Professor Balakrishna for a nice lecture and thought-provoking. In fact, the young people will definitely get benefited by this. Thank you, sir. Thank you.
Thank you. Thank you.
Now over to the organizers.
Shankaran, are you traveling? Mic mute on. Sharada madam.
Sir, namaste.
Namaste.
How are you, sir?
I'm good, fine.
Yeah, fine.
Hello.
Madam, good morning.
Sir, namaste. Kaviyar
Namaste, sir.
Sharda Bhatt from Dharwad.
Namaste.
Sir, good morning, sir.
Good morning. Yeah, good morning. So, who is chairing Sharda Bhatt Society? Professor Vittal.
Yes, sir. Professor Vittal, I think he had to join.
Yeah.
So, we're waiting for him.
Yeah.
Sir, yesterday I could not able to make it for the inaugural because our governor has visited our university. There was a function is going.
Acha.
Yes, sir. All Vice Chancellors meet was here. South Indian all VCs, nearly 70 Vice Chancellors are in Bharatiya University.
I see. Okay.
Today also the program is going.
VC's
meet is going.
Okay.
Yes, sir.
So I hope somebody will contact Professor Vittal and find out.
I think the organizer, anybody is there?
Yeah, I don't have a contact. Maybe Jayashree madam or
Srinivas sir, namaste.
No, but Srinivas Rao,
Namaste, madam.
How are you,
Good
sir?
morning, sir.
I'm fine.
Good morning.
I'm fine. Yeah. After a long time, we are seeing online at least.
Yeah.
Yeah, in fact, I think if this was the situation, we could have organized offline also, but we did not know this.
Yeah.
So when is your seminar, Professor Srinivas Rao?
It is in July.
July, okay. July is fine because
Yeah.
in May and June, I think I will be traveling sometimes.
You can come here.
Yeah, in July, I think I can manage.
Our people will. Yeah. They are our department people are thinking of having in July.
Okay.
And the brochure is almost ready, they told me.
Acha, okay.
Yeah.
Let me just find out from...
offline, it is a blended mode. It is offline and online. They want to have it. So some people at least can come here who have, at least by that time, no COVID will be there. I hope.
Hope so.
Let us hope for that.
Yeah, but China, yesterday I read in the newspaper that China is again put to the lockdown.
That means they are bringing a new virus.
Uh,
So tomorrow we have a function at 12 o'clock.
yeah.
Good morning, madam. Do you have contact details of Professor Vittal? But he is supposed to chair a session in Hall D. Oh. Yeah, otherwise, I think because the speaker is ready here. Okay. The problem is he is speaking in another session. So I think I did not know. Otherwise, we could have changed it because immediately after a session, it is difficult to chair another session.
Yeah.
Because sometimes the timings may be.
Yeah.
This seems to be yesterday's schedule.
Yeah, they are displaying yesterday's schedule at APS.
Yeah.
Pandit Memorial Lecture.
Yeah, this was over yesterday.
Over. If this hall is delayed, we can shift to another hall.
Yeah, that. Or I think we will
listen somebody.
No, we will join Vittal sir's session. That is Hall C. Let me just see there.
Hall C.
Madam, I think that sir is yet to complete his talk. That's what. Actually, your mic is muted. Mic is muted.
Okay, I had muted my mic.
Yes.
Should we mute both video and audio? I think sir is in hall number 3.
Okay, I think that's what Balasa told. He's yet to complete the session. So once he complete only, we can join here. Ma'am, it's muted.
Shall we start the session, sir?
Yes, yeah. See, just now I finished my talk at the other back, and now I'm coming to Madam.
Yes, sir.
Thank you very much. You see, my talk was just over, and now I'm shifting from all C to all D virtually.
Shall I start, sir?
Yes, yes, we can start.
Yes. So, respected Chair, Professor Pierre Vittel and other professors present in this hall, and Professor Kaviyarasu, next speaker, and all the delegates. At the outset, I thank the organizers of International Virtual Conference.
Are you able to hear?
Sir, I think the ma'am got stuck. Network connection issues, I think. So.
Oh. Professor Sarda Bhatt from Karnataka, I think.
Yes, sir. Yes, sir.
Professor Jayashree, are you able to hear me? Kaviyarasu is able to hear, right?
Yes, sir. Yes, sir. I'm able to hear, sir. It's audible, sir.
Yeah, it is audible. But Jayashree, Professor Jayashree, I saw.
Yes, sir.
Yeah, you are able to hear. Was it any problem with internet?
Yes, sir.
Yes.
No, sir.
Now,
The problem is with Professor
Sharda Bhatt. Yeah.
So let us wait a few minutes for her, so that she will join. Yeah, immediately. So, madam, please contact her.
Sharda Bhatt, Madam Sharda Bhatt, are you able to hear us?
Yeah, I am here. I will share the screen now, sir. There is some internet fluctuation here, so maybe it was in problem. Shall I share the screen now?
Oh yes, oh yes.
Can you please see my screen?
Yes, yeah, now coming.
Yeah. Okay. So, yes, I will
be able to see the screen.
You are able to see the screen, no?
Yes, ma'am. Yes, ma'am. It's visible.
Yes.
It's visible.
Okay.
It's better to make it full screen.
I will share my thoughts on posterior control charts for process variation. When I mean process variation, it is for process standard deviation as well as process variance. This is the work that I carried out with two of my students, Dr. Kailash and Mr. Chetan Malgavi. I will be proceeding with introduction about posterior control charts in the beginning, then basis for posterior control charts, the motivation and basis for going in for Bayesian control charts, some review of literature. We will discuss with S and S square posterior control charts. Mainly in this talk, I want to highlight the difference between range-based posterior control charts and posterior control charts for variation. The relationship between standard deviation and range-based posterior S and S square control charts, and we will evaluate the proposed posterior control charts and give our conclusions. In an ongoing manufacturing process, control chart that uses sampling and graphical scheme is practical technique to monitor the quality of a product. Control charts form the basis for taking decision about whether the process being out of control is due to the assignable cause or not. The adequacy of control chart is gauged on how early it gives alarms whenever the process goes out of control. The technique or measures are like power, average run length, standard deviation of the run length, coefficient of variation of run length, and process capability ratio. They reveal the performance of the control charts, and we have taken all these measures to compare the control charts. We know that Shewhart's control charts are based on the assumption of normal distribution and 3 sigma concepts, and this was the first of its kind in control charts. The control charts can be constructed using various approaches. They have parametric approach, non-parametric approach, and Bayesian approach. Parametric approach is when the observations are coming from a certain model, say normal distribution. We speak about parametric control charts. If it is not for to construct outlier resistant control charts, we use non-parametric methods, and Bayesian control charts or Bayesian approach is mainly when we want to take the idea of prior information, what was already happening in the process, production process, and what has to be done in future. So that is why we take Bayesian approach. To construct posterior control charts, we need to know some basis for that or some basics for that. So Bayesian approach to control charts, it is depending on prior information about process characteristic under consideration. Bayesian approach is mainly based on subjective probability. The assumption is that sample data has a specific distribution whose parameters are assumed to have prior distribution with hyperparameters. Hyperparameters means known parameters. The prior information in the form of prior distribution is combined with the sample information to get posterior distribution using Bayes principle. The central result that governs Bayesian inference in Bayes theorem is the probability of A given B. This is, we can treat this probability of A given B as posterior information, wherein we are using probability of B given A as prior information. So probability of A given B is equal to probability of B given A into probability of A divided by probability of B. When we construct Bayesian control charts, or when we have the approach of Bayesian, we have two kinds of charts that can be constructed, that is depending on posterior distribution and predictive distribution. Basically, we had seen the predictive distribution also for the average process variable, but we found that the Bayesian control charts based on posterior distribution is working better than the predictive distribution. Hence, we started constructing and analyzing the control charts depending on posterior distribution. So then what is posterior distribution? It is, suppose x1 to xn follow f of x given theta as a sample distribution. Then if we have pi of theta as a prior distribution, then posterior distribution is given by pi of theta given x is equal to pi of theta f of x given theta divided by integration of pi of theta f into x given theta into d theta. So we see that the posterior distribution is proportional to the prior and sample distribution. So capturing prior information in the form of probability distribution is one of the important factors in Bayesian approach. So one of the usual Bayesian choices is mean of the posterior distribution. And predictive distribution is actually given by a density for future observation of x Weigel, that is given by x pi of x Weigel given x, which is depending on posterior distribution. So now the motivation and basis for constructing or proposing the posterior distribution that we have done is because the prior information is available through historical data, random experiments, experience of the researcher, market survey, etc. It gives some potential information about the parameter of interest. Prior information about parameters of interest in a proposed model has to be represented through a suitable probability density function, which is helpful in obtaining posterior distribution of the parameter. I think there is some disturbance somewhere. Am I clear from this end?
Yes, ma'am. Now it's okay.
Yes.
So someone has unmuted. So please ask them to
unmuted their mic. Yeah. Okay. So 3 common choices for priors that a researcher can select is conjugate prior, non-conjugate prior, and non-informative prior. There is some improper prior also. We have not considered that. Conjugate prior and conjugate prior means if it's a class of sampling distributions, then f of x of theta given theta and p is a class of prior distributions for theta, then pi of theta, then p is said to be conjugate for f if pi of theta given x belongs to p. That means whatever the prior distribution I have taken, so whether it is binomial or Poisson, when I get the posterior distribution with the present sample information, if that is only the updated version or the posterior distribution also belongs to family of prior distribution, with some kind of reparameterization, then we call such a distribution as conjugate prior distribution. That is, the prior and posterior distributions of the parameter have same form with different parameters. Conjugacy is a closure property. The merit of conjugate priors is that it simplifies the computations. So then the very important thing that we have to use in Bayesian inference is the loss function. L of theta comma a is the cost of action A under parameter theta. So this is the loss function. This is a random quantity that depends on outcome of the random variable x. That means that is the difference between the action taken and the parameter of interest. So we see that the optimal action for the that minimizes the expected loss is called as Bayes rule and is given by expectation of L theta A. So 3 broadly used loss functions in Bayesian control charts is usually, or Bayesian analysis is usually squared error loss function, or which is also called as quadratic error loss function, absolute error loss function, and binary loss function, or we call it as 0-1 loss function. So the squared error loss function is given by C into theta minus a whole square, where C is a positive arbitrary constant. So we quickly brush through the literature review. 1931, Shewhart initiated the theory of control charts. 1952, the cost of modeling of quality control systems was devised by Gershik and Rubin. In 1996, Montgomery has given an exhaustive literature survey. Shewhart's S control chart based on which I will be addressing as S1 control chart here for process standard deviation, and Shewhart's S square control chart based on probability limits for sigma square. And in 2000, Rand developed the probability limits for Shewhart's S control chart. That is what I call as S2 control chart here. The question is, I should go for station chart as well as S square control chart when we are studying. Is there any meaning for that? So we have already seen the standard deviation actually speaks about infinitesimal measure of variation, whereas in many of the manufacturing processes, they like to have a control in terms of variation itself. So this is one point. Secondly, we have S control chart there is all the chance that even the variation is usually greater, is usually positive. Control meaningful sometimes. So after that, when they are discussing, he is about the probability limits for the deviation chart. So I have considered three kinds of charts here. The standard deviation chart based on control limits, standard deviation chart based on probability limits, and S-square control chart based on variance. So
Excuse me, sir. Can you unmute your? Sir, unmute your mic, sir. Because
And it is not audible. Professor Sarada Bhatt, it is not audible to me.
Yeah, Professor, it is not audible.
It's audible?
Not audible. Not.
Not audible. No, I don't know why.
I think she has some network issues. I think.
Something wrong with their internet connection thing. Madam. I'm unable to hear you. Your network is working?
Yes, sir. Yes, sir. Yeah, it is not working a bit. Wait. Screen share.
We are unable to hear anything.
Wait. Yes. Sir, now look at the thing.
Yeah, I'm able to hear you, but your screenshot is not there.
You are unable to hear me?
Now I am able to hear you, but the screen is, screen is not there.
Oh, screen is visible?
Yeah, the screen is not visible.
Not visible. Yeah, I will try. Now?
No, screen is not visible.
No screen?
Yeah, no screen is not visible. Only 5 minutes more.
Wait, sir. I will just see what is happening.
Yeah, it is started. Wait.
Now it is visible.
See, screen has not come to me. Started sharing.
Sir, screen is not shared. Huh?
Yeah.
Wait, sir. Wait. That screen. It has closed.
At least you will summarize so that the
Sir, I will just yeah. Okay, screen now.
The screen is now visible.
Okay. There is some internet problem here in the office. I'm very sorry, all the participants. And I will quickly through the posterior S and S square control charts. We see all the preliminary of
Start
and
moving
S
the
square.
screen. Yes, yes.
Yeah. Screen is visible, sir.
Screen is visible. You can. Yes, just move.
Can you hear me?
Already you have come to the introduction and P away given B posterior and prior probabilities.
Yes.
All these were over. Yes, these are all over.
As I said, time short, I will just.
Just about 3 minutes more. I understand there's some internet problem. Understand there is. Javier, so are you ready with your topic?
Yes, sir, I'm ready, sir.
Javier, so yes. We'll wait for 3 minutes and then start, right?
Okay, Professor. Thank you, Professor.
I think there is some internet problem from the side of Professor Sarda, and I personally thank on behalf of the ISPS and Usmania University, Professor Sardar Bhatt, for giving excellent introduction. Unfortunately, we are unable to see the complete picture of the talk. Therefore, I thank Professor Sardar Bhatt for making all the necessary arrangements and giving a very fine introduction to the topic. And now I go into Professor Kaviyarasu for the first talk. Professor Kaviyarasu, you introduce yourself because the data was not given to me. I'm sorry. I know Kaviyarasu well, but personally I cannot introduce him. Therefore, I'd like to request Professor Kaviyarasu to introduce himself and then present his talk.
Thank you very much, Professor. I feel really honored to be present in front of you, my research article. And I also thank the organizer for giving an opportunity to share my research in this today's forum. I'm just share my screen. Is my screen visible, sir?
Yes, screen is visible, perfectly visible.
Okay, sir. Thank you. So myself, Dr. Kaviyarasu, working in Bharatiya University, Coimbatore, Tamil Nadu. And today I'm going to talk about certain quality evaluation methods in quick stitching system under zero inflated Poisson model. So today, quality control is one of the important pioneering area, especially the quality control is broadly classified as product control and process control. So early, Sharda Bhatt madam was talking about the process control, and now I'm going to talk about the product control. So to improve the quality of products and services, it is customary to describe a set of statistical tools used by quality professionals. So manufacturing is an engineering aspect, but still statistics plays an important role in the quality evaluation method. So in that, the process control and product control are the two important statistical techniques which are applied in industries. So especially the product control and process control are two sides of a coin, like head or tail. So one without other cannot be exist. So quality improvement is defined as the reduction of variability in the process and products where variation is measured in by statistical methods. So today, the quality improvement we talk about, early we talked about 1 sigma, 2 sigma, today we talk about 6 sigma. And the quality improvement is getting enhancing from day to year with new advanced techniques and tools are coming for the evaluation of quality strategies. So an efficient quality improvement program can be instrumental, which increases the productivity at a fewer cost. So when the quality improvement is increased, so that the productivity increases and the cost will be reduced. So as a result of increasing customer quality requirements and the development, the new product technology, many existing quality assurance practice and techniques need to be modified. So early there are many statistical techniques on quality controls are available in the literature, but still it need to have some modifications and updations to be done in every aspect of the quality control which are need of the cover. So the need of statistical and analytical techniques in quality assurance is rapidly increasing owing to stiff competitions in the industry. So the quality control concepts was emerging during World War II was due to the mass production. So it is a procedure where in between the 100% inspection and no inspection at all. So it's a middle path in between 100% and no inspection. So these techniques are developed based on the theory of probability, sampling, and inference, being extensively used in almost all small-scale industries, in many manufacturing industries like textiles, electrical equipment, plastic, electronics, chemical industry, petroleum industry, transport industry, medicines, and many more, where the quality checking has been principally followed. So in statistical quality control, Madam was talking about process control. Sharda Bhatt Madam was talking about process control. And here I'm focusing on product control. It is also called as an acceptance sampling plan. So acceptance sampling plan can be done with the traditional method, and the acceptance sampling plan for live test methods can be studied widely by many researchers. So sampling plans are invariably used in industries to quality maintenance, assurance. Acceptance sampling is a statistical technique in which a small part or a fraction of units or items can be selected randomly from a lot and inspected to detect whether the lot have any defective items or not on the basis of the information provided by the sample. So we take a sample of items and we inspect the items and we check whether the items is good or meet the standards or not standards. So that is what we say S is equal to D minus A. S is the specification and A is the actual. The difference between the S minus A is the difference. That is what we specify to check in the random sample what we take X1, X2, etc., Xn. So the main objective in mole sum sampling is to design a satisfactory sum sampling technique or commonly select a system which already developed with the new modifications can be implemented to propose with the new techniques and development. So the risk of sum sampling plans are always there with producer risk and consumer risk. With the based on the OC curve of a particular plan can be plotted. It is appropriate to give a careful OC curve for the selection of the plan to meet the requirements of producer as well as the consumer. So whenever we talk about the initial aspects of sampling plans, so according to Dodge, Professor Dodge in 1969 has said that the major area of action sampling can be classified as lot by lot action sampling by method of attributes, then lot by lot sampling by method of variables, continuous flow of sample method of attributes, and special purpose plans like chain sampling plans, skip plot sampling plans, and etc. Many plans are available, which can be studied in the nature of the samples. They may be measurable or non-measurable. That is, the quality characteristics are variable in nature. Sometimes it's attribute in nature. So when we talk about the sampling plans, and we should know what are the designing methodologies are available in the literature. According to Case and Keats, the designing methodology of some sampling can be categorized as risk-based and economically based, with the Bayesian and non-Bayesian approach. And my work comes in the fold of risk-based Bayesian approach. So this is the area. So far, there are a wide number of distributions has been studied in quality control. Especially we talk about Poisson distribution, binomial distribution, and inverse rail. That is, and many distributions can be widely studied. But my research is research work along with my research scholar Parimala. We joined together and work on the zero inflated Poisson distribution and its importance in the quality control environment. So today the world stiff competitions in the world, every manufacturing company strictly follows quality procedures to maintain the quality. So in count data, when excess number of zeros are present, how it can hold to a Poisson variable. So there is a need is required. We need an alternative to study about the zero inflated Poisson distribution. Let us see an example. The number of insurance claims received in two-wheeler insurance, the number of cigarettes smoked by students in a college, the number of defective items occurred in the continuous production of items, all are situations where the inflation of zeros are much and many more. So in such situation, the occurrence of defective items are rare phenomena. That is, the non-conformist lots would be more in numbers with excess number of zeros or occur. So using these methods, one can identify a defective list item, or the inspector or the quality control, the quality manager who accept the products early can go for a zero inflated Poisson distribution. So due to a random fluctuation of some unavoidable reasons in manufacturing process, there is situations occur, any defective may occur. So within a batch of perfectly functioning a production system, we require to go for an alternative with the Poisson distribution. So the sampling plan based on Poisson distribution is often used to monitor the number of defects of non-conforming sampling units. However, the major problem in evaluating the zeros is a statistical viewpoint. So the zip distribution can be studied in such scenario, which helps the management to take a precise decision and can certainly reduce the error rather than the regular Poisson model. So when manufacturing equipments are properly aligned in the order and the number of defects and impossibles are in a probability P, and the occurrence of defect follows lambda. So here we also consider the Bayesian approach, as already said by the Madam Sharda Bhatnam, given the Bayesian introduction to Bayesian, why the Bayesian is required and how the Bayes theory are applied in the control chart techniques. So here the same Bayesian concepts is considered for the product control techniques. So the assumptions underlying the theory of control sampling plan by attribute is that the larger fraction non-conforming is a constant, and which implies the production process is stable. However, in reality, the lots are from the process that will have a quality variation that occur due to random fluctuations. So generally, two types of quality variations are occurred. That is within lot variation and between lot variations are occur. So nowadays, Bayesian methodologies become widely used in almost all field in statistics. So here also we consider the Bayesian methodology for implementing the quality control procedure and the zero infinite Poisson distribution through Bayesian approach. Today, Bayesian approach is widely used in machine learning techniques, especially that what we call as an statistical intelligence techniques can be applied through your machine learning. So these methodologies can be used when the quality engineer have some prior information of the production process to make a decision about the disposition of the lot. So now coming to our the sampling system, what we are proposing here is a quick switching system. So this quick switching system was introduced by Rombosky. Before that, Dodge 1967 has initiated the two-plant system with normal and Titan inspection procedures can be implemented separately by the m consecutive lots. Whereas Rombosky 1969 has extensively given the applications of quick switching system with the switching between normal and Titan. Whenever the inspection process is continued, an item can be switched from normal. When the defective comes, we switch to Titan inspection, and the continuous lot is accepted, then we switch to normal inspection. So due to switching between normal and Titan, this system is referred as a quick switching system. So Soundarajan et al. 1988 have further elaborated the importance of QSS with the modified results of the OC curve with cases 1, and cases 1 is more efficient than other methods of cases 2 and cases 3. So the modified system with the single sampling plan and with as a reference plan have proposed two types of procedures in QSS was set by Rombosky in 1969. So he elaborated that there are two types. One is QSS with NCNCT and QSS NK and CNAT. The first case we have one acceptance number, two acceptance number with one sample size, and in second case we have two sample size with one acceptance number, which are elaborated with NKN, CNCT, and CNAT are given for the two procedures. But here, this is the graphical representation of how the QSS1 is functioning for the probability function P of P equal to PT by 1 minus Pn plus Pt. And the cases 2 is given here. This can be given under the condition of P of P is equal to Pn Pt square plus Pt into 1 minus Pn plus into 1 minus 1 plus Pt. So I think Pt square plus 1 minus Pn plus into 1 minus Pt. And cases 3 is explained in the input diagram with the procedure of cases 2 with Pn and Pt cube. Then coming to the some basic review of literatures which are available in the zero infinite Poisson distribution. So Lambert 1992 has given the application of defects in manufacturing process under zero infinite Poisson model.
From the organizers, please mute the others. Only speaker is allowed to unmute.
Thank you, Professor. Thank you, Satish.
Okay, please continue.
Then Reid et al. In 1998 discussed some models for count data with occurrence of excess number of zeros. Boeing et al. 1999 has discussed the zip distribution is better than Poisson in epidemiology research to measure the dental health. Then later in 2003, Rodriguez and Nayal et al. 2008, Muzida et al. In 2013, Loganathan and Shalini in 2013, and Srinivasa Rao in 2017, and myself and my scholar Asif and Sivakumar has developed some sampling plans related to the zero infinite Poisson model. Later, Hall 1960 has given the Bayesian importance of Bayesian outcome sampling plan for studies, and Brush 1986, Calvin 1990, Suresh and Lata in 2001, Loganathan in 2007, Muzida 2011, myself and Sivakumar and Parimla has developed the Bayesian methodologies in quality control, especially in the zero infinite Poisson model is concerned. Then coming to the equation system, Soundararajan and Armanagam 1988 constructed the cases one type with their construction of tables are given with the operating procedures, with the corresponding OC curves are illustrated. Then Armanagam in 1991 has given for the RGS plan as a reference plan. Suresh 1993 has given the studied the cases one with the AQL and LQL procedures. Jayalakshmi, Kaviyarasu, Umal, et al. All are given some contributions toward phase switching system. So why we want to model the zero input Poisson situation? The zip model, the zip distribution is used for count data to exhibit over dispersion and with the excess number of zeros in such a way that the mixture distribution that includes the extra zeros and the Poisson models according to Lambert 1992 has given the elaboration why we wanted how to take the mixture model of distributions. So here, let x be a non-negative integer and a random variable with the Poisson distribution is usually takes x by x 0 with high probability and modified with the zip and takes a random variable with the density function, and the corresponding p of x is given with the following equation which are given when x is equal to 0. The first case omega plus 1 minus omega equal minus lambda, and x takes other values, this will be occur. So the omega range is 0 to 1, and here the omega is called by the weighted parameter and the lambda is the Poisson parameter. And here when you talk about the Bayesian as concerned, the fraction unconforming as given with the P of P expression where lambda is always greater than 0 and this lambda is greater than NP. So the OC function of zip distribution on the Bayesian perspective is given with T is a scale parameter and S is the shape parameter. So due to want of time, I'm just running a little bit fast with the cases 1, 2, and 3 can be studied. So here, the operating procedures of the quick switching systems can be studied with the operating ratio values with respect to when you fix the various alpha and beta with the P1 alpha, P1 comma alpha, comma P2 and beta, the planned parameters can be executed with the following procedures. So we can compute the operating ratio by P2 by P1, and we can determine the accent number C and the corresponding values of alpha, beta, and the OR, we can take the nearest value from the corresponding table. So in step 3, we can determine the unity values of NP1 and NP2 from table 1 to 3, calculating the sample size n. Then the quick switching system can be executed with the normal and tightened procedures can be evolved. So here, whenever we talk about the designing methodologies, we talk about acceptable quality level and limiting quality level are the two important quality levels we can study. That is the based on the 2 point of AQL quality levels of AQL and LQL, or consider here with the corresponding relative slopes also can be studied with respect to P0, P1 and P2 what we call as H0, H1 and H2 can be fine. So later we can design a sampling plan with what we call as a minimum sum of risk, which was proposed by Golub, has given the minimum sum of risk for acceptance number C for a single sampling plan for the corresponding AQL and LQL. Then also we can study the minimum angle method can be designed with Norman Bush et al. 1953 has proposed this method with respect to the following the triangle of we can find the tan theta. The formula for tan theta is opposite side by adjacent side, where theta equal to tan inverse of n tan theta by n, and we can find the minimum angle method. These are the design methodologies where I can define. We can study for various sampling plans. So this is the OC curve. What we given here for the conditional RGS plan for the gamma zip distribution and zip distribution and gamma Poisson distribution has been compared, and we can say that from the corresponding probability value, we can say the gamma zip distribution is giving a better shape than the zip and gamma Poisson distribution. So we say that the sample size may be further reduced more than if you study Poisson or zip or separately gamma Poisson. So here a comparator is also extended based on the various distribution with respect to various sampling plan systems what available for the QSS, that is quick switching Bayesian single sampling system, what we designated as. So with the corresponding NCM and CT. So here we can see the OC curve for cases 1, 2, and 3, and we can say the cases 3 is the better plan when compared to 1 and 2 because the Titan rule is more when compared to cases 1 or cases 2. So the cases 3 plan system can give a better sample size when compared to 1 and 2. So the general plan involves the cumulative results of the under Bayesian perspective. So under current law design, decision is based on the more samples making the decision regarding the acceptance or rejection of the respective lots. So normally the quality inspector, when they inspecting the quality of lot is good or not, so they need some evidence by the acceptance number successively lots with starts with the normal procedure and it switches to Titan inspection procedure whenever there is a rejection occurs. So the 3-stage quick switching Bayesian single sampling system is indicated by the OC curve and the corresponding probability acceptance, the values are given here. So here I take a simple example for small scale industry as concerned. So any small scale organization are supposed to execute this procedure. Let us take in Coimbatore, there are many brick manufacturing industries are available, so small scale industries. Suppose they want to implement this quick switching system in their production of the units. So they can apply this procedure. How it is, the quality is not a one-time achievement, but it's a necessary part of the planning, preparation, and execution of the production in all days, in all steps. So we cannot say that quality is not a one-time achievement. It is a continuous process. When there's a continuous production, every situation, every circumstance, we have to check whether the items manufactured are quality or not. Suppose the big manufacturer appoints a quality engineer who runs the experiment to take a decision on their product, either to accept or reject a lot, assuming that the quality of the brick product follows a gamma zip distribution with the period production, the past production is taking S is equal to previous 5 lots, and he wants to find the strength of the plan of SSP, that is single sampling plan under Bayesian cases 1 for the corresponding AQL and LQL. We fix P1 is 0.05 and P2 is 0.10 with a producer and consumer risk and the omega value we fix as 0.05. Then we find the sample size for the NP1 is 143.252 and NP2 is 143.1213. So we consider the sample system should have the sample size of 143 with normal level is 2 and Titan level is 1 acceptance. Suppose the brick manufacturer produce a lot of 3,000 bricks in a single production. So they have to take a sample size of 143 samples for inspection, and they can allow 2 defectives in the normal level and 1 defectives they can allow in the Titan level. Otherwise, they should go for the Titan level or they go for the rejection, the lot. So now coming to the conclusion part. So from this illustration, when the omega becomes larger and larger, the sampling plan under Bayesian zip distribution, which gives a better results when compared to the classical sampling plan than the gamma Poisson distribution or the zip distribution. It also be noted that the production process is zero defect manufacturing environment. The proposed plan will give a significant reduction in terms of producer risk as well as the consumer risk together. It was further observed that this proposed system, cases 1, 2, 3, with various sampling plan as a reference plan, can be studied in the gamma zip environment under the Bayesian perspective. However, the risk of producer and consumer of rejecting the good lots also reduced, and also we have to safeguard both the consumer against the poor quality levels and assigned risk or given with the suitable OC curves. So with this, I conclude my talk, and also I thank the organizer. I thank Professor Vichal sir for chairing the session and giving time for me to share my present research in this forum. Thank you very much, Professor.
Thank you, Professor Javier. Any question or 1 or 2 questions you can allow? In the absence of more question, I thank Professor Javier for his excellent talk, starting from the basic idea of quality sample, attribute sampling, variable sampling, and leading into OC curve function, and finally touching application of brick manufacturing, particularly in the area of time control. A very good application to quality control system. A nice talk, very practical application still today. I'm quite sure Javier and his team in Coimbatore, Bharatiyar University are very active, especially my own student Saktival is also there. Right? Therefore, I'm quite sure they will be able to pursue a lot of work useful to the statistical society. Thank you, Professor Javier. So I know I like to make one other arrangement. Now that since the network problem is there, Professor Sarada Bhatt, she would like to conclude in 5 minutes now. Professor Sarada Bhatt can join us and she can conclude, giving the conclusion in 5 minutes. Professor Sarada Bhatt, now you can join the session and give your conclusion.
Sir, thank you, sir. Thank you very much. I have just shared the screen. I will continue my talk. Vital sir, thank you very much for giving me an opportunity to share. So now I will just share the final conclusions and remarks that about the control charts we have done. So depending on the relationship of standard deviation and range, we have constructed 3 more control charts, and these are the control limits given by our control charts. We have compared the control charts based on range, then Shewhart control charts and posterior control charts for standard deviation and variance. So when we have evaluated these control charts, we have evaluated it in terms of power, ARL, SDRL, CVRL, and process capability. These are the graphs about the control charts for Shewart's posterior control chart and range-based control chart. This is for standard deviation and standard deviation control charts based on control limits. This is about the standard deviation control charts based on posterior limits. This is the control charts, comparison of control charts for variation based on posterior limits, S-square control charts. Then we have proceeded with the control. We found that the control charts based on range were performing better. So what we did is we carried out the comparison among the range-based control charts. And with all the observations, we conclude that R1 control chart outperforms S1, PS1 control charts, R2 control charts excels PS2 control chart for copious shifts in sigma and performs better than S2 control chart for relatively larger shifts in sigma. That means the range-based control charts are outperforming Shewhart's control chart and posterior control chart. R-star control chart is better than S-square and PS-square control charts in terms of all the performance measures for smaller shifts in sigma square and smaller values of n. You can hear me, no, sir?
Yes, yes. Yeah,
yes. Among R1, R2, and R-star, that is the control charts based on the range, it is found that R1 control chart is superior to other two in terms of performance measures. That means the range-based control chart that has control limits is better than the other two control charts for variation. When variance follows inverted gamma prior with shape parameter eta and scale parameter delta, power of R1 and R2 control charts is higher for lower values of delta, that is for the scale parameter, when eta is fixed, and higher values of eta when delta is fixed. That means the control charts are performing better for higher values of the shift and lower values of the scale. Using lesser specification limits, our posterior control charts yield higher PCR than Shewhart's control charts, that is process capability ratio, and posterior control charts based on standard deviation and variance, with R1 control chart having the highest PCR among them. So we suggest to use R1 control charts for the process standard deviation and R-star control chart for process variance whenever the process stimulates fewer samples. And this is a better thing because even range is a very simple measure of variation. So this is what I wanted to share with you all. These are all the references.
Thank you very much, Professor.
Sir Vikram sir, thank you very much for giving me an opportunity to share the conclusion. Because of too much fluctuations of the current and as well as the signals here, I was unable to cope up in between. Thank you very much for giving the opportunity, and I'm very sorry for all the audience for the random phenomena, the random problems I had here. Thank you, one and all.
Thank you. See, I prepared 2 hours for the lecture and 10 hours prayer to the God that it has to go through correctly, you know, because it is, no, we cannot depend on all these situations. Anyhow, you have presented very nicely. I thank you very much.
Yeah, thank you.
I must also thank Professor Jayshree for permitting me to continue this permission to you, because the next session, Professor Kaviyarasu has to take the chair, I think, is what she told me. So both the speakers have done their justification, and I thank once again Professor Kaviyarasu and Professor Sarada Bhatt for their presentation, and I hand over the chair to the Osmania University team and the next session to continue. Thank you very much.
Okay, sir, thank you. I am unable to open the camera. That's why from here only I salute you all. Thank you.
Yes, I can visualize.
Yes.
Madam, kindly stop sharing your screen, ma'am. Yeah.
Yes, Mr. Kaviyarasu, I hope you are going to chair the session.
Yes, sir, I'm going to chair the session.
Thank you. I will be leaving, sorry, because I have a next work.
Okay, sir. Thank you, sir. Thank you. So now
Shall we start the session, sir?
Yes, ma'am. Shall we start the session?
Yes, sir.
Okay, so I welcome you all for the contributory session on behalf of the organization committee. I welcome all. First I check who are the speakers are presented now, going to present now. I think there are nearly 7 contributed papers are there. First one with Asif T. Totatil is there. Asif Totatil? No. Then second, Magendra Shaga is there. Say yes or no. So I think there is no. Then the third contributed paper by Chetan. Chetan is there. Chetan Malagavi. I think she is not there. We go for the next person. R.A. Kapse and V.B. Gute. Is there?
I'm present, sir.
Estimation of change point in high process in SPC applications.
Yes, sir.
I think there is no response from that end. So we move to the next one. Deshpande is there?
Yes, sir. Am I audible?
Yeah, Deshpande. So now I call Deshpande to present his talk on interval estimation of process capability indices for autocorrelation observations. So I think we give 15 minutes time for Deshpande to present his work and 5 minutes for discussion. So now I hand over to Deshpande.
Okay, sir. I will share my screen.
Kindly turn on your camera so that who is presenting is able to visible by all the audience. Since it's online, you need to turn on the camera while presenting.
Okay. Just a second. I think I am visible and is my screen visible?
Yes, visible, visible.
Okay. First, I would like to thank organizer for giving me opportunity to present my work. Good afternoon all. Today, I'm going to present my work on interval estimation of process capability indices for autocorrelated data. This is joint work with my supervisor, Professor V.B. Gute, sir. So let's start with the introduction. Process capability analysis is one of the most important statistical process control tool. It assumes that the observations are independent and normally distributed from an in-control process. The processes from chemical industries, manufacturing industries, where continuous measurement of output characteristic is ongoing, reflects the dependencies between the observations. We call it as autocorrelation. These processes has to be studied with special attention to get the process capability index value. We see some basic indices. The basic process capability index was introduced by Giron in 1971, known as process performance index. It is defined by taking the ratio of allowable process dispersion to the actual process dispersion, given by the index CP. In this index, we see that USL minus LSL upon 6 sigma, where sigma is the process standard deviation. Then there are first generation, second generation, and third generation index developed by Kane in 1986, Hessing and Taguchi in 1988, and Fern et al. In 1992, respectively. These index are modified for certain reasons. In the first basic index CP, only sigma process standard deviation was considered, but the process mean mu was not considered. So the index CPK was developed by considering the process mean. In the index CPM, both mean and standard deviation was considered simultaneously, in addition to the target value of the process. So these indices were unified by Weinman in 1995, and it is given by the equation CPU. Yes. Hello. Can I continue, sir?
Yes, you can continue.
Okay. So the unified process capability index was given by this equation, where U and V can be set to 0 or 1, which reduces to the indexes like, if we take U and V both 0, then it reduces to CP. If we take U as 1 and V as 0, it reduces to CPK, and for U equal to 0 and V equal to 1, it reduces to CPM. These are the parameters specified: mu as process mean, sigma process standard deviation, USL is upper specification limit, LSL is lower specification limit, and D is defined as USL minus LSL upon 2, and T is the target value for the process. Now we see, as I am studying the process capability indices for interpolated data, it is necessary to
Sir.
Who's calling?
Just a second. I will.
Myself, Asif.
Yeah, you can wait, pa.
Okay.
Okay. So for the study, we need to discuss stationary Gaussian process. Actually, these are known as time series process. So the XT process such that it has finite variance, and where T belongs to W, which is subset of R, a real set of real numbers. The autocovariance function for the process XT is defined by gamma R comma S equal to covariance of XR comma XS. Then a stochastic process XT is said to be stationary if it has finite variance. Just a second, sir. Okay, sorry for interruption. So a stochastic process said to be a stationary process if it has finite second order movement and a mean is equal to constant value m. It means it is independent of the time point t. And the main property is gamma, which is autocovariance function, is equal to gamma rs equal to gamma r plus t comma s plus t. It means that the gamma autocovariance function is does not depend on the t value, because it is same for gamma r comma s equal to gamma r plus t s plus t. Next, a stationary process is said to be a Gaussian if all of its joint distributions are multivariate normal, and we consider a sample from a stationary Gaussian process and define sample mean and variance by using x bar and s square. Now, in earlier we have defined the capability indices. The usual estimates where we replace the process standard deviation sigma by s and process mean mu by x bar are given by this CP hat and CPK hat. In whole this study, we just consider the two indices for our study. Next, we have studied the confidence interval for the process capability indices under the stationary Gaussian process. We consider, let us assume mu as a process mean 40, sigma process standard deviation 7, USL and LSL are defined as 61 and 19 respectively. And for different sample sizes, 10, 25, 50, and 100, the AR1, which is autoregressive of order 1, and the property that for 5, 0.25, 0.50, and 0.75, it is a stationary process. the confidence interval CP hat plus K sigma CP, sigma hat CP plus minus for CP and CPK, we obtain for different values of K. We call it the 2 sigma and 3 sigma limits. So we have considered the simulations for the values for 10,000 values. The results were presented in the next tables. First, we considered the results for without autoregressive process of order 1, and we can see that here for sample size 10 and k equal to 2, the lower limit and upper limit are 0.492 and 1.704. For as we see that as sample size increases, the confidence interval is observed in this table for CP and CPK. And in next, we have considered for the auto-regressive of order 1, what will be the effect of the autocorrelated process on these capability indices. So, for example, if we see for this sample size 25 and k equal to 2, the confidence interval is 0.72, 1.34. And for the same parameter in the autocorrelated process, we see that for CP 0.25 and k equal to 2, the confidence interval is 0.778, 1.21. So we can see that easily the length of the confidence interval, we define it as the difference between upper limit and lower limit, which reduces when we have the observations from an autocorrelated process. The same effect was observed in the CPK also. So this is the description of above tables. From above results, we can say that the length of confidence interval is decreased due to autocorrelation, because there is effect of autocorrelation on process standard deviation, which was studied earlier by Guevara in 2007. Now, the objective of our study is to reduce, to at least reduce the effect of autocorrelation. We done by using some modified sampling procedures such as skip sampling and mixed sampling procedures. So we shortly define this skipped and mixed sampling techniques. These are remedial measures available for reducing the effect of autocorrelation on process capability indices. Other procedures like linear regression and residual control charts are also useful. The proposed methodology, that is skipped sampling methodology, is based on skipping the S observations before taking the next observation. This actually needs more than n observations for having sample of size n. For example, if we want sample of size 15, then we have to take 30 observations for by using one skip sampling, and then but we can utilize the remaining observations also, as we can imagine that if there are 30 observations and 15 observations are obtained by using one skip, then remaining 15 will be obviously the one skip sample, and we can utilize that sample also. In the mixed sampling procedure, it was proposed by Franklin 2014. This technique is based on collection of 2 consecutive samples of same size from, in this case, AR1 process. If we consider a sample at time point I and at time point I minus 1, then the mixed sample at time I can be obtained by using the combination of the sample at time I and at I minus 1. So if you have even sample size to be obtained, then we have to take this x1i comma x2i minus 1. That is, first we take observation from current sample, and then next observation will be from past sample. Then again observation from current sample, and from past, next is observation from past sample, so on. And similarly for sample size, if sample size is odd, the mixed sample can be obtained. Now, before going to study the effect of this using this sampling procedure for the confidence interval, we just studied the effect of this sampling procedure on the standard deviation of the capability indices. So here first in this graph we see that this is without skipping sampling, and we have different levels of autocorrelation 0.25, 0.5 and 0.75. So we can easily see that as sample size increases, the standard deviation decreases. For example, for the middle line for autocorrelation level 0.5 and sample size 20, this is around 0.35. But when we use one skip sample, that for 0.5, from 0.35 it reduces, the standard deviation reduces to 0.06 or 0.07 around. So here we see easily that the one skip sample improves the estimate of process standard deviation. And also we have used for two skip sampling. And the same study was carried out for the index CPK. Now, here one more thing we observe in the CP and CPK is there is means for CPK this skip sampling and that is one skip sampling and two skip sampling gives more accurate result or more good results than in CP. Okay, now we study this effect of skip sampling and mixed sampling on the confidence interval. So again, here we see for k equal to 2 and 3 for different sample sizes. This table represents the results for the index CP, and this table represents for the index CPK. Now, to understand the effect, we can see that again in the same situation for k equal to 2 and sample size 25, the confidence interval was 0.702 to 1.306 for one skip sample, and for two skip sample it is 0.694 and 1.306. So again in this skip sampling also the confidence interval is improved in comparison with the for autocorrelated process. And for CPK also this confidence interval is improved for CPK for different sample sizes and k equal to 2 and 3. We studied the confidence interval using mixed sampling for different parameter space for different autocorrelation level 0.25, 0.5 and 0.75. Lastly, I would like to conclude our work. The process capability analysis get affected under autocorrelated process. Moreover, they are negatively biased. Standard deviation of process decreases as sample size increases. Length of the confidence interval reduces under autocorrelated process. Using skip sampling and mixed sampling strategy, the effect due to autocorrelation can be reduced at certain level. Mixed sampling outperforms skip sampling strategy, and further investigation can be made to the effect of autocorrelation on confidence interval of the process capability indices. So these are some of the references which I have used. I would like to thank if there are any questions. Am I audible, sir?
Yes, Mahesh Deshpande. So now the forum is open for one or two questions. You can stop sharing now, Mahesh.
Okay.
Yes, Mahesh, you worked on interval estimation of process capability sets, right? Is it possible to have any literature reviews there for point estimation? For PCB
Yes.
autocorrelation fluctuation?
Yes. We made the point estimation study also, and for autocorrelated, when we try to find the distribution of that estimate that CP hat and CPK hat, actually it does not give the exact distribution. So again, there we have to use some alternative to find the distribution and then the properties for point estimate.
Okay, as a researcher, what would you suggest, whether you prefer point estimation or interval estimation?
The interval estimation is always better. Means if we have interval estimate there, then we can prefer that.
Okay.
With certain level of confidence. Okay. Thank you, sir.
Okay, Mahesh. So any more questions? If there is no questions, we move to the next speaker. So early we call upon the contributed papers. Many people are absent and few have given in the chat box. So I start from the first person. Asif Thotatil, are you there?
Yes, sir. Am I audible?
Yes, audible. So now I request Asif Thotatil to talk on designing and characteristics optimization of double sampling plan using interval Poisson distribution. Now the forum is open to Asif.
Thank you, sir. Good afternoon to all respected professors and audience. Myself, Asif T. Thotatil, research scholar under the guidance of Dr. K. Pradhiba Veerakumari, Department of Statistics, Bharathiar University, Coimbatore, Tamil Nadu. Here I am going to present our work under the title of Designing and Characteristics Optimization of Double Sampling Plan using Interval Poisson Distributions. The overview of our work is that we are included introduction, review of literature, and implementation of double sampling plan under the conditions of interval Poisson distributions, and observation and findings, and next conclusions. Earlier, as Professor V. Kavir sir mentioned, the acceptance sampling plan is a vital tool in statistical quality control. Is in the place of 100% inspection. In industrial field and business sector, when a large amount of products is producing, then we have to inspect whether there is a defect items included before it's sending to the commodity. At the time, we have to inspect every items to inspect whether it is defect or not. But many times or many situations with the constraints of time, manpower, and cost, 100% inspection is not that much appropriate. In such situation, acceptance sampling plan is the best. It is a method. It is a method of statistical sampling test to inspect or test a random sample for determining whether the quality of a batch of products or services is acceptable. In acceptance sampling plan, there are many sampling plan available, in which I am working with a double sampling plan. The easiest and simplest sampling plan in the acceptance sampling plan is single sampling plan. The single sampling plan is the process of deciding on a lot based on defective items in a single sample collected from the lot. Similar, the double sampling plan will make a decision about the population of or lots by using the defect items at most 2 samples taken from the same lots. My work for constructing the double sampling plan. First one, acceptable quality level. This is a quality or percent defective that is a baseline requirement for the quality of the producer's product. The before the if the population or lot has the quality level less than or up to AQL, then the lot should be acceptable with a high probability. The limiting quality level. The limiting quality level is the bad quality level, which will specified by the consumer. If the lot has the quality level more than or equal to LQL, the lot should be rejected with a high probability. And the producer risk is that rejecting the lot when the quality level of the lot is at AQL, and the consumer is the accepting the lot with the LQL quality level. Associated with each sampling plan, there is an OC curve which will portray the performance of the sampling plan against the good and poor quality. The probability that the lot will be accepted under a given sampling plan is denoted by PFP, and plots of PFP against the given value of the lot or process called TP will yield the OC curves. Here the black curve is the ideal curve, and the red one is the typical OC curve. When we are constructing when we are constructing any sampling plan, we will focus to approach our OC curve to the ideal curve. Many literature is available regarding this work, and some of the important literature is given here. With respect to the single sampling plan, Peach-and literature provided a single sampling plan by using the percentile of chi-square distribution, and Dodge and Romick provided a wonderful table for selecting the single sampling plan. Cameron used a unit value approach for constructing the single sampling plan, and Haldis used a Bayesian approach in single sampling plan. Schilling and Neuber also provided a matched single and double and multiple sampling plan. And also in double sampling plan, Duncan worked with a double sampling plan in 1974. Schilling and Johnson and Soundararajan Arumanayagam also constructed a double sampling plan by using AOQ and AOQL values. Here, traditionally, the sampling plan are created by using or constructed by using the count model like hypergeometric distributions and binomial distribution, Poisson distributions. But there are many situations arrived or has arisen because of the technological improvement. And interval Poisson distribution is also one of the appropriate situation, which is described in Shanmugam R in 1985, and Hong and Feng's calling Dhanavanthan also worked with the interval Poisson distribution. Pradip and Azaruddin constructed a single sampling plan by using the interval Poisson distribution 2016. And many, the Lognathan and Shalini constructed a single sampling plan by using zero inflated distributions. Kavirisu and Asif constructed a special type double sampling plan by using zero inflated Poisson distributions, and Kavirisu and Devika also used generalized Poisson distribution for constructing single sampling plan. The interval Poisson distribution is described well by Shanmugam in 1985 and Shibu and Sadish and in their research work. And this is the PM of probability mass function of the interval Poisson distribution. The interval Poisson distribution is applicable whenever the process has any problem is arisen by due to some random chances, and after the products are produced with some defect items. In such cases, in the lots, if you are taking any sample, there will not be a no defect situations. In such cases, zero will be deleted in that model. So either we can use zero truncated Poisson distribution or positive Poisson distribution. But if we are intervening any technically and with the intention of to providing good quality items, and the results, it will be the Poisson distribution with the model rho theta. And the sum of these zero truncated Poisson distribution and the Poisson model distribution will be results the interval Poisson distributions. And in the implement of double sampling plan under the interval Poisson distribution, here we are given that probability of acceptance of the double sampling plan. The plan parameters of double sampling plan are determined in the objective and given below. That is P of P1 greater than or equal to 1 minus alpha and P of P2 less than or equal to alpha beta. Under the IPD, under the interval Poisson distribution, the probability of acceptance are given. And to study the impact of the intervention parameter in the intervention Poisson distribution, we compared the double sampling plan with the help of zero truncated Poisson distribution, in which a zero truncated Poisson distribution doesn't describe anything regarding the intervention parameters. After developing the double sampling plan under the IPD, we illustrated with the help of some examples. Suppose there is a 1% intervention, that is rho equal to 0.01 made in the production process, and consider P1, P2 0.01 and 0.05, and alpha is equal to 0.05 and beta equal to 0.1. Then by using the operating ratio and unity value tables, which
As if last 2 minutes.
Okay, sir. Unit value approach, we can get the sample size. Here the sample size are provided for the double sampling plan is 76 and 152. The acceptance number 1 and the second acceptance number 5. Here the corresponding the operating characteristic value for the double sampling plan. And the OC curve. Sir, screen is visible, sir?
Nope, not visible. It was closed. Can I come for conclusion?
Yes, sir.
No, it's okay.
And after that, we compared with the second acceptance number and with the different values of intervention parameter, and we constructed the OC curve, and we constructed the ASN values also. In the ASN curve, we can understood that if the values of intervention parameter is increasing, the ASN will be reduces. If you are using the zero truncated Poisson distribution in the situations of intervention Poisson distribution, the more sample size should have to taken for the appropriate situations. The conclusion: the proposed sampling plan is constructed by tabulating the minimum sample size and operating characteristic value satisfying consumers and producers. The ASN value for DSP are tabulated for different intervention parameter under the IPD and GTPD. The impact of the intervention parameter is studied and concluded that when using zero truncated Poisson distribution instead of IPD in a proportion to the risk involved, more sample has to be taken. Therefore, IPD can be used as an excellent model to optimize the parameter of DSP. And these are the table unity value providing unity values and operating ratio, and these are my references.
Okay, Asif, any questions now to Asif? Okay, that's no questions. But Asif, you are taken a good work for intervention Poisson distribution. So, under what situation the intervention taken place in any sampling inspection procedures?
Yes, sir. In a normal production process, if anything happen by random chances, then there will be
what are the anything? What are the situations you say?
Suppose if you are producing with a constant voltage,
okay,
by the random chance of there will be a fluctuation will become in the voltage. At the time, there will be a defect items will be produced. But after rectifying this voltage infection and the mechanics is reducing that fluctuation, and then it will be normal cases. In these situations, here some barrier will become once that whenever the fluctuation is coming, the lot of defect items will be produced, and after rectifying this fluctuation, the normal situation will be arising. There will be two situations: one's zero truncated Poisson distribution, the second one normal Poisson distribution. But we are counting the total number of this number of defects. In such cases, we are assuming that if we are taking any sample, there will be at least one defect. In such assumption, we can use the invariant Poisson distribution in our acceptance sampling plan.
Okay, Asif.
Okay, sir. Thank you.
Okay. Any questions? So there's no questions, so we can go for the next speaker.
Sir, excuse me, sir.
Yes.
Sir, myself, Lokesh Maran.
Yes, Lokesh, you are the last person I told, no?
Okay. Thank you, sir. Thank you.
You are in the list. Your name is there, but you are the last person.
Okay, sir. I'll wait. Thank you, sir.
May I stop, sir?
Yes, stop sharing and.
Okay, sir.
So next I call upon entitled Estimation and Confidence Interval of a New Loss-Based Process Capability Index as Application by Mahendra Saga, Anuj Devya, Abhimanyu Singh Yadav. Anybody is there? The second call and last call for this person. Okay. The next Chetan Malgavi is there. Chetan Malgavi. Are Kapse?
Yes, sir.
Are you there?
Yes, sir.
Are Kapse?
I'm present, sir.
Second last call for Kapse.
Hello.
So then next we call the next contributor, monitoring process variability using auxiliary information with runs rules. S.A. Pawar and B.B. Gute. S.A. Pawar is there?
Yes, sir. Am I audible?
Yes, ma. Can you turn on your camera?
Yes, sir.
15 minutes time for you.
Okay, sir.
Hello, sir.
Yes, ma. Yes.
This is Ari Kapse, madam, sir. She wanted to talk to you.
Who?
Kapse Ari.
I'm Are Kapse. Can you hear me, sir?
Your voice is low, ma. Can you talk a bit loud?
Hello, sir.
Yeah, tell me, ma.
Can you hear me, sir?
Yes, ma.
You announced my name recently.
I called you twice or thrice, but there is no response from
I'm
that side.
replying, but I think there is some audio problem.
Okay, you present it later. Okay, in the last.
Okay, sir.
Shall I start presentation, sir?
Yes, yeah. Yes, say Pawar.
Yes, sir.
Sharika Pawar.
Yes.
Share your screen. Turn on your camera.
Yes, sir. Is my screen visible, sir?
Not yet, ma.
Not yet. Okay, sir. Wait a minute. Just a minute, sir. Now, is it visible?
No, ma.
Okay.
Make it fast. Other speakers are waiting.
Yes, sir. Sorry, sir. I think there are network issues, sir. So up to that, may I start my presentation? So or speaking?
I couldn't get you.
My screen is not visible.
Yes. So go to screen share.
Yes, sir.
There's a green button there, no? Screen share. Yeah, now it's visible. Now it's
Okay,
visible.
sir. Okay.
Sharika, you can start. Yes.
Yes, sir.
Turn on your camera.
Yes, sir. Turning on it.
Next speaker is
Wait a
Lokesh
minute, sir.
Maran.
Okay.
Be ready.
Sorry, sir. Okay. Good afternoon to everyone. I am
Okay.
Sarika Pawar. I am presenting my paper titled as Monitoring Process Variability Using the Auxiliary Information with Runs Rules. Am I visible,
Camera
sir?
is not visible.
Yes, sir.
How
There
would we
are.
know this Sarika Power or not? Who is presenting? We want to record.
Yes,
Right?
sir. I am struggling to on it, but it is not opened yet.
Okay, proceed.
Okay. Okay, sorry for interruption. I am Sarika Pawar from Punyashlok Ahilari River Solapur.
Sarika, any issues there? You're not audible. Sharika, would you be able to hear me? Sharika, are you there? Sarika? Rupali, कब से?
Hello, sir.
Are you ready now?
Yes, sir.
Yeah, share your screen and present now. Turn on your camera also. Visible, ma, proceed.
Yes, sir. I'm just turning on the camera.
Rupali, कब से?
Yes, sir. Can you see my presentation, sir?
Is visible, ma.
Yes. So I will start my presentation. The title of my topic is Estimation of the Change Point in High Yield Processes in SPC Applications. I'm from Punyashlok Ahilari Holkar, Solapur University, Solapur, and the work is under the guidance of Dr. V.B. Kute, sir. So this is the outline: introduction, objectives, literature review, geometry custom control chart, process, step change model, performance of the estimator, conclusion, and some references. So control charts are a standard statistical process control technique to distinguish between the special cause and assignable common causes in the process. So to identify the shifts in the process parameters, the control charts used in a industry. So the basic control charts, Shewart, EWMA, Kusum control charts are used to monitoring the process of upsets. But while using these control charts, the investigator do not exactly know at what point the change is started to occur. So there is another approach which identify with the help of control chart is the change point model. So here the objective is identify the time of change in process, non-conformity proportion in high yield process, and to detect process shifts quickly, and it will help to improve the quality of the process. So these are some literature review who worked in the identifying the step change in the high yield process. So Nurosana identified the period of a step change in high yield processes. Miyagi in 2013 estimated the change point of high yield processes experiencing monotonic disturbances. In 2011, Perry estimated the time of step change with Poisson, Kusum, and EWMA. Again, they considered the change point estimation of the process fraction non-conforming in SPC applications. In 2013, Nyaki considered change estimation of high yield processes with linear trend disturbances, and Amiri identified time of a monotonic change in the fraction non-conforming of a high yield processes. So here the geometry control chart. So to monitoring of non-conformity proportion in high yield processes, P is based on the geometric count. So the upper sided Kusum chart for detecting an increase in P plots is given in equation 1. So here this xt is the tith geometric count, and the starting value, the head start h0 is set to initially to equals to 0, and this real signal is issued at the first t for which that Kusum statistic ht is greater than or equals to decision interval h. Similarly, the lower sided Kusum chart is given by LT equation 2, and the reference values kh and kl are calculated by using the equation 3. So a two-sided Kusum chart is obtained by running the two one-sided Kusum charts simultaneously. So here the value of P1 is the given out of control process non-conformity level value for which to design the Kusum. So here the process step change model to identify the change in the non-conformity level proportion. So here consider a process that is initially under statistical control, and the observations are generated from the geometric distribution with fraction non-conformity P0. So suppose that an unknown point in period T referred to as process change point, process non-conformity level changes from P0 to P1, which is equals to delta P0, and delta is the magnitude of change. So when a delta is greater than 1, represent deterioration in the non-conformity level, and delta less than 1, it represents improvement in the non-conformity level. So we assume that once the process shifts in control state P0 to an out of control state P1, it will remain at the same new level until the special cause is identified and eliminated from the process. So we consider the control chart signals at subgroup T or observation T. The process is no longer in the statistical control. So this is the point at which the quality engineers practitioners must initiate a search for there is a special cause of variation is present in the process, and to identify that point. So we denote that point tau, the last observation from the in control processes. So from observation 1 to tau, x1, x2, xt are the observations with from the in control fraction non-conformity. The remaining x tau plus 1 up to xt, where the control chart gives signals, are the observations belong to the process with a fraction non-conformity level P1, which is the changed fraction non-conformity level. So here we consider the derivation of MLE of tau, the process fraction non-conformity change point. So we will denote the MLE of tau change point tau as tau hat. So the MLE is calculated in this. So the likelihood function for the change point problem is given by equation 5. So first observations are from the in control processes, that is j equals to 1 to tau, and the remaining observations are from j equals to tau plus 1 to t. So by calculating log likelihood function in this equation 6, the value of P1 that maximizes the likelihood function is P1 hat tau. It is given by the equation 7. Then by substituting equation 7, value of P1 hat tau in equation 6 in the log likelihood function, we will get the MLE of the change point tau is tau hat ergmax LT, and LT is given by the equation 8. So to perform the study of this estimator, we use the simulation study to evaluate the accuracy and precision performance of the change point estimator following when the geometric Kusum control chart gives the signal. So here first we consider the 100 observations are from the in control processes, that is having the non-conformity proportion P naught. Independent observations were randomly generated from a geometric distribution with P equals to P naught, and following observations from observations 101, the independent observations randomly generated from a geometric distribution with P equals to P1 until the Kusum chart produced a signal. The estimate of the process change point tau was computed at that point. So this procedure is repeated total 10,000 times for each P1 value investigated. So here the average average of the change point estimates obtained from the 10,000 simulation runs were computed along with the standard error of the estimates. So here the expected T is equals to ARL plus 100. So first 100 observations are from the in control process, and then the observations until that control chart gives the signal. So total observations are ARL plus 100, that is equals to expectation of T. So these are the simulation results. So here average change point estimates and standard errors with P naught equals to 0.0005 are considered. So here P1 is considered from 0.0006 to it is increasing. So this is the average change point estimates when genuine signal from a geometric Kusum control chart for increasing process fraction non-conforming. So here expectation T, that is when the control chart signals at 560 on an average, and for that P value of P1, the MLE change point estimator detects the process shift at 150. So for all the values of P1, we can see the expectation T is more, and the tau hat bar gives the signal earlier before the control chart gives the signal. So this table shows when the this table shows average change point estimates after a genuine signal from a geometric Kusum control chart for decreasing process fraction non-conforming. So here again also expectation T, that is the geometric control chart gives signal at for P1 0.0004 is 198, and on an average the MLE detects that at on an average at 110. So here again the MLE detects that change point earlier before the control chart gives the signal. So here the precision of estimators is considered. So here the tau hat estimated MLE is in between the M observations from the actual change point. So here actual change point tau is considered at 100. So the first probability that the change point identified at exactly the observation or subgroup 100, these probabilities are here given. So we can see that as M increases from the true value, the probabilities are also increases. So this table shows that when the P1 is less than P0, when there is a decrease in the fraction non-conforming level. So here also we can see that the probabilities are increases as the M increases from the true value of the change point. So here we concluded that using this maximum likelihood estimator, using the change in the process can be identified before the control chart gives the signal. So the non-conforming units will not be produced and the process will bring back on time in the statistical control. So the results of simulation studies show the proposed estimator is effectively works in detecting the true time of the process change point. So these are some references. Thank you.
Yes, Rupali. Any questions, Rupali? So, as Rupali, can you tell what is your limitation of your study?
Actually, in some cases, binomial is not using, but
It's not audible, ma. It's not audible. You're muted. Yeah, now it's okay.
Hello, sir. Hello, sir. Hello, sir.
No, you're not audible. Okay, anyhow, we move to the next one. Sharika Power, are you ready now?
Yes, sir, I'm ready now.
Yeah. Share your screen.
Is screen visible, sir?
Yeah, visible.
Okay. So shall I start my presentation?
Yes, continue.
Good afternoon, everyone. I'm Sarika Pawar from Punyashlok under the University of University Solapur. I'm presenting my paper titled as Monitoring Process Variability Using Auxiliary Information with Runs Rules under the guidance of Dr. V.D. Bhutesar. So this is the plan of my presentation. Introduction, Sheva type AIB control chart, Sheva type AIB chart with runs rules, performance evaluation, and conclusion. Next is introduction. So control chart is one of the most widely known tools of the statistical process control, which is extensively used to monitor changes in the process parameters. So we all know that there are two types of control charts, location chart and dispersion chart. The location chart is used to monitor the process mean and dispersion chart is used to monitor the process variability. So it is a standard practice to use Sheva X bar chart for monitoring the process mean and R or S chart for monitoring the process variability. A major disadvantage of Sheva type control chart is that they uses only information of large sample observation and completely ignores the past information of the process, which makes it insensitive to small shifts in the process parameters. Memory-based control charts such as Kusum chart, EWMA chart, and moving chart are also developed in the literature as alternative to Sheva chart for detection of small shifts in the process parameters. In order to increase the sensitivity of the traditional control chart, many new modifications and improvements in the control charting procedure have been suggested in the USPC literature. One of such modifications is the development of auxiliary information based, that is AIB control chart, which have an excellent speed in detecting shift in the process parameters than those based without it. Such control charts are based on a statistic that utilizes information from both the study and the auxiliary variables. The information on auxiliary variable is generally known prior to the sampling procedure and it assists in estimating the study variable with increased accuracy. Due to outstanding performance of the auxiliary information-based control chart, many researchers have paid attention to design the auxiliary information-based control charts to improve the shift detection ability. For efficient monitoring variability parameters, RIAS proposed the Sheva type variance chart, that is VR chart, based on the regression type estimator using the information of an auxiliary variable and showed that performance of VR chart increases as the correlation between the main variable and the auxiliary variable increases. RIAS proposed the Sheva type variance chart, that is VZ chart, for efficient monitoring process dispersion using the information of an auxiliary variable based on the ratio type estimator of variance and showed that its performances increases as the correlation between the main variable and the auxiliary variable increases. And then later, Riaz and Durs in 2009 proposed the Sheva type variance chart, that is VT chart, based on the regression type estimator using single auxiliary variable and showed that its performance increases as the correlation between the main variable and the auxiliary variable increases. In literature, runs rules are also used to monitor chart, to control chart to increase its sensitivity in the decision of small to moderate shifts in the process parameters. To enhance the effectiveness of the Sheva control chart to detect small shifts, various runs rules are suggested and studied by the several authors in literature. Cham and Ural in 1987 employed Markov chain approach to derive ARL for the Shewhart chart with supplementary runs rules. In literature, M of K chart have been studied by various researchers. The M of K chart signals if consecutive M points of K points lie outside control limit. Hu and Arifin in 2006 proposed to improve the run rules to enhance the performance of the two rules suggested by Klein in 2000 for the detection of the large ship. Zhang and Wu in 2005 studied the design of control chart with supplementary run rule. Acosta Mejia and Pignatiello in 2009 studied the performance of the K of K run rules for monitoring the process standard deviation. Lim and Cho in 2009 investigated the economic statistical properties of X-bar chart supplemented with M of N run rules. Practitioners usually prefer to use the Shewhart type control scheme supplemented with one or more powerful runs rules due to their simplicity in operation and interpretation. The purpose of this paper is to improve the performance of the auxiliary information-based chart proposed by Riaz to detect shifts in the process variability by using the concept of runs rules. We integrate the Shewhart type chart with supplementary runs rules. The average running performance of the chart with supplementary runs rules. The average run performance of the chart with runs rules is investigated using simulation study and compared with originally proposed chart. So Shewhart type control chart. So let an auxiliary variable xi be correlated with the variable of interest yi, and let us denote the correlation between these two variables by rho yx. The observations of variables y and x are obtained in the paired form for each sample, and the population mean and variance of x, that is mu x and sigma x square respectively, are assumed to be known. Also, we assume bivariate normality of y and x, that is x and y distributed bivariate normal with mean mu y mu x, variance sigma y square sigma x square, and correlation between them by rho. The auxiliary information-based regression type estimator of population mean mu y using a single auxiliary variable x is defined for a bivariate random sample x1, y1, and up to. So this is the test statistic. VB is equals to sy square plus rho square into sigma y square upon sigma x square into another bracket sigma x square minus sx square. So this is the mean and variance, and the upper control limit is sigma y square plus L sigma y square into under root 2 into 1 minus rho square divided by n minus 1, where the value of L determines the in control ARL of the AID Shewhart chart. For detecting increase or decrease in the process dispersion, UCL or LCL is sufficient. Now, by using the runs rules, so in this section, we consider the following two run rule schemes alternative to the Shewhart type of the information chart. So, in 2 of 2 scheme, so this scheme gives an out of control signal if either 2 successive points are plotted above an UCL. And second one is 2 of 3 scheme. This scheme gives an out of control signal if 2 out of 3 successive points are plotted above an UCL. And 1 of 1 scheme is a Shewhart type chart. Now the performance evaluation. So traditionally, the performance of a control chart is evaluated by average run length, that is ARL, for a specified control chart and given shift in the process average. ARL is the average number of points plotted on the chart until an out of control signal is obtained. The ARL value associated with the zero process average shift is called in control ARL, which is denoted by ARL naught. And the ARL value with non-zero process average shift is called as out of control ARL, denoted by ARL1. So in this section, simulation study is carried out to access the ARL performance of the chart using runs rules. Now let us assume that the in control process is a bivariate normal distribution without loss of generality, a standard bivariate normal distribution, that is with mean 0 and variance 1 is considered as in control process distribution. The out of control process is a bivariate normal with the same mean of variable x and same variance of both auxiliary and study variable with change the mean mu y1. That is, we consider the out of control procedure as with delta. Delta means the shift. Simulation study is based on the sample of subgroup n equal to 10, 15, and 20 with various values of correlation coefficient 0.3, 0.6, and 0.9. The lower and upper limits of the ARL chart under the various runs rules are obtained using simulation such that in control ARL of the chart is approximately 200. The out of control ARL values of the control chart for each shift of magnitude delta in the process mean of study variable are then computed using the 12,000 simulations. The chart under various runs rules compared on the basis of out of control ARL performances, where magnitude of shift of the mean of study variable y is changed and is considered as this. So since the ARL as a single parameter is not necessarily very typical value of the run length distribution, therefore the standard error of the run length distribution also given in the parentheses. So this is the observation table. Here we compare all the 4 charts, that is VZ, VR, VT, VV charts, where VR and VV are the regression type charts and VT and VZ are the ratio type charts. So here we can easily see that as the shift changes, these values are taken for the correlation coefficient 0.6 and for the sample size 10. So here we can easily see that all the values for the VB chart are detected earlier than the other 3 charts. And now for this chart, we apply the runs rules. So these are the values for n equal to 10. So when rho equal to 0.3, our shift will come for 1 of 1. 1 of 1 is VB chart, plain VB chart. Then for for shift 1.1, it detects at 46, and for 2 of 2, it detects at 38, and for 2 of 3, it detects at 36.29, means early detection. Then for 0.6, it detects earlier than the 0.3, and for 0.9, it detects earlier than the 0.6. Now these values are for n equal to 10. Now these values are for n equal to 15. So we can see here for 1.1 also the detection of the shift is much easier than the other values than the n equal to 10. And similarly for n equal to 20, the detection is much earlier than the n equal to 10 and 15. So for any range of shifts in process variability, the runs rules chart consistently produces smaller out of control ARL than the AID chart. That means proposed runs rules chart early detects shifts in the process variability. Out of control ARL values of this chart under the runs rules decreases as correlation between them increases, and out of control ARL values of the runs rules chart also decreases as the value of sample size increases. So in this paper, the 2 types of runs rules are applied to the chart for efficiently monitoring the process variability of a normally distributed process. The chart based on the runs rules is easily implemented and have better ARL performance than a Shiva type chart, that is 1 of 1 spin, for monitoring shifts in the process variability. So these are some references. Thank you.
Okay, thank you, Sarika Pawar. The forum is open for question. Any questions? 1 or 2? Okay, there's no questions. So we call upon the next one.
Okay.
Dr. Okay, Sarika.
Okay.
Dr. Lokesh Maran.
Maran. Yes, sir.
Yes.
Yes, sir.
You can share your screen and represent your work.
So, my screen is visible, sir. Am I audible, sir? Hello?
Yes, you're audible and the screen is visible.
Yes, thank you. Good afternoon, one and all. My name is Dr. Lokesh Maran, working as Associate Professor in Medical College, Pondicherry. So, whatever this conference, there are many resource person and everyone talk about the theoretical part. Almost maximum number of people are theoretical parts and this thing. And it's also very important to application oriented type, right? So now my paper is about application and comparison of 2 modalities of treatment or intervention program. So here my title is Kaplan-Meier comparison of effectiveness between 2 type of intervention called pranayama intervention and guided imaginary intervention on labor outcomes among the primary gravida. Only we are considering primary gravida, first time mother, and selected hospital in Puducherry. So here, just a minute, sir. My slide is working. Yes. Kaplan-Meier analysis is one of the effective way to estimate the survival function that we are reviewing. Kaplan-Meier curve is also a visual representation we have, and now we consider in our study pregnancy women who are first-time mothers, and that's what the first-time mothers, and there is no complication with their during their pregnancy period. And we refine the whole population in that way, such a way that there is no complication, only priming mothers, and only the intervention started in the 34 to 37. And we are considering only term deliveries, not preterm delivery or post-term delivery. So we consider only term deliveries. And relaxation techniques we are going to given in the guided imaginary and the pranayama techniques. We are having objectives to evaluate the effectiveness of guided imaginary. What is the effectiveness? We are giving guided imaginary and pranayama technique, and we are going to compare these two effectivenesses with the use of control groups. Right? Here we are considering, as I told you, that we are considering whole OBG department, and we took 42 mothers who are in first time who are come for the first time delivery, and we start with their time onset of delivery time, and we consider their end time, the delivered time. So total duration of time we captured, and we found we need to find is there any significance between the total duration of the time of labor in between the three groups, and is there any complication during the delivery, which means we are considering only normal delivery, vaginal delivery only. We are considering normal or assisted normal delivery we consider. And methods and material, we started we giving a intervention started 34 weeks of gestational till delivery of the time, and we are asking, or the investigator asking, researcher asking the participant to take 2 times in a day, morning and evening, 15 to 20 minutes of the intervention period. And demographic variables we collected, and the second one is the intervention period. The next one is post test, which means delivery outcomes. We are considering only delivery outcome, whether it is a normal assisted normal delivery, and we consider duration of the labor. And we also found that there is a significant difference between the proportion of assisted normal, which is very lower in the group of pranayama group. Using the statistics, statistics, we found that there is a low proportion in pranayama group where assisted normal, which means there are high proportion in normal deliveries in pranayama group. There is well compared to control group and the guided imaginary group. And we also found the mean duration of the labor. The mean duration labor is here it is given in minutes, 641 minutes average, and 690 minutes in control group, pranayama group. And this analysis of variance shows there is a significant difference in the mean values, which means the guided imaginary group having less duration of labor, while pranayama group having assisted normal is very less, which means pranayama group having a high proportion of normal delivery, and the duration of labor in very less in the guided imaginary group. That's what the after post-op test we applied bone parameters. It shows that there is a significant difference in the guided imaginary with the control group, but there is no significant difference in guided imaginary and pranayama group, but considering their duration of the labor. So duration of the labor, when we are giving some intervention, like any intervention, guided imaginary or pranayama, it is reducing their duration of labor by considering as there is no intervention at all, as treatment go on. That is it. Then we go with the Kaplan-Meier estimation. though it is a non-parametric estimation. So we consider only the median estimation of these three groups. Here it is 675, which is very higher than the other two groups, 695, which means it shows the pranayama group and guided imaginary group having almost equal. There is no significance between the guided imaginary and pranayama, but there is a significance in control group, which is giving a higher duration of labor. That's all. The survival function also says that the red line shows a control group, and other two, green and blue, showing that guided imaginary and pranayama. There is no much difference between the guided imaginary and pranayama. As compared to the control group having higher proportion of assisted normal as well as high duration of labor compared to other two. And log rank also shows that there is a significance between these three, which is control group having high duration of normal delivery, and similarly the control group having high proportion of assisted normal group. While giving guided imaginary and pranayama interventions, we are trying to prevent the assisted normal or any other complications during the delivery. So here we consider only the normal delivery, vaginal delivery, and assisted normal delivery. So the final conclusion of this Kaplan-Meier estimation, why we taking this Kaplan-Meier in this thing is, so there is no much data set, and there is no much application Kaplan-Meier with the OBGY, with the duration of labor. Though there is only one application in 2003. There was a total duration from the time of conceive and the end of this. There is one. Here, what we are trying to do is the duration of labor. We are considering the onset of labor to the end of delivery. So here, Kaplan-Meier method estimation is very useful to predicting the median duration of labor effectiveness of between the two interventions. But we couldn't find the duration. There is no significance between the two intervention duration, but that two duration is significantly differ from the control group. Though the in Kaplan-Meier estimation, but the pranayama group having less proportion of assisted normal group. That is the important thing. So pranayama group is a higher proportion of normal delivery while compared to the other groups. That is the thing is conclusion. And here my references. Thank you all. Sir?
Yes, Lokesh.
Yes.
Yeah. So now the forum is open for questions. Any questions? Yes, Lokesh Ramaran. Have you tried any other statistical techniques apart from chi-square and the other thing?
No, sir. Here we consider only two. The whole thesis is different, but the small part of this thing is here we are applied only. We consider only mode of delivery and duration of labor. So we are trying to next level. We are trying to move on the Cox proportional or any other survival model in this thing. We can incorporate other parameters like LSTS, mode of delivery, all other type of mode of delivery, any other sensoring like that. So after this, we are trying to do that.
Okay, very good. Okay, if I think from this we conclude the session. So I think among the 7 contributed paper, 5 present and 2 absentees. And on behalf of the organizing committee, I thank all the presenter for their nice presentation. I also thank the organizer for giving an opportunity to share the session. So now over to the organizer.
Thank you, sir.
Okay.
Thank you, sir, for chairing the session.
Okay.
Hello. A very good afternoon to you all. I think Dr. Prafulla Kumar Swain and Dr. Bindu Krishnan both are present, who are the speaker of this session.
Yes, sir.
Yes, sir.
Good afternoon, sir.
Good afternoon. How are you?
Sir, fine, sir. I'm fine. How are you, sir?
I am also okay.
Yeah.
Okay. So whether we can start the session now or we wait for 2 or 3 minutes. Any organizer is present here or no one?
I think it's let us wait or 1 or 2 minutes, otherwise we'll start.
Okay, okay. Okay, I think we can start now because it is already 5 minutes over from the scheduled time.
Yes, sir.
Okay, so again, very good afternoon to all of you. This session is without any nomenclature, and myself, Professor S.S. Maiti of Department of Statistics, Vishwabharati University. First, I thank the organizer, the Department of Statistics, Osmania University, and ICSDS for giving me the opportunity to chair this session. In this session, there are two distinguished speakers. Dr. Prafulla Kumar Swain, he is in the Department of Statistics, Utkal University, Bhubaneswar. He is a young, energetic man. I know him. He will speak on the title Count Data Regression Modeling, Review with Applications to Endometrial Cancer Patients. Another speaker, distinguished speaker, is Dr. Bindu Krishnan. She is professor and head Department of Data Science, Computer Science and Information Technology, Jain University, Cochin, Ernakulam. She is mainly engaged in application of heavy tail distribution in time series data. So she has a lot of work in this area. She will speak on today on data generating using GAN with heavy tail distributions. So, so in this session, I request the two speakers to restrict their deliberation with 25 to 27 minutes to finish that one, and then there will be the discussion regarding any questions or comments from the audience? So now I call upon Dr. Prafulla Kumar Swain to deliver his lecture on the topic data regression modeling, a review with applications to endometrial cancer patients. Dr. Swain, please.
Okay, thank you, Sam. Thank you, sir. Thank you so much for your kind introduction. And let me share my screen. Okay, I hope it is visible.
Okay, it is okay. Okay.
So, good afternoon, everyone. And so today I'm going to speak on count data regression modeling, a review with application to endometrial cancers. So basically, this is something what I'm going to discuss, the application part of count data modeling and how we can work with count data and what are the possibilities and what kind of regression modeling we can cover using this count data approach. And the application, what I have demonstrated, that is based on endometrial cancer. That is one of the most common cancers in the gynecological cancer among women. So before I start, this is outline what I'm going to speak on today. That is the background on count data, what exactly count data means and how models are available for count data, and with the applications basically in the endometrial cancer patients. So count data refers to the observation that have only non-negative integer values, and that from ranging from some 0 to some greater undetermined value. Sometimes theoretically it is ranges from 0 to infinity. If you see, sometimes this the represent number of occurrence within an event or within a fixed period of time. For example, if you see the number of patients died due to myocardial infarction in the hospital within 48 hours, or number of trades in the time interval, or number of given disasters, or number of crimes, or number of accidents. So basically, you will find number of areas where this kind of count data you will come across. So there, how you can model this kind of data, because this data in order to understand this kind of count data model, we must have some knowledge about the linear statistical model, generally the linear regression model, which is based on normal probability distribution. That can be in the form y is equal to beta naught plus beta 1 x plus epsilon. Here y we call response variable and x is predictor, that is to be explained the occurrence of y. Beta is the regression coefficient, epsilon is the error term, and this error terms, and we assume that is following some normal distribution with zero mean and some constant variance, sigma e variance. But when the modeling, we are modeling count data, we really estimating the parameters of probability distribution that we believe that best represent the data we are modeling. So there are two most common commonly used distribution for count data. We have one is Poisson regression model, another is negative binomial. Here we have considered those the problem of endometrial cancers, which is we are taking into account the number of involved nodes. While we are going for surgery of any endometrial cancers, there are a number of involved nodes. That count we are considering, since this is a count discrete variable count in form of count, with the Poisson regression, it could be the best choice for to start with our modeling. So we have considered the Poisson regression model first, then let I say yi be the number of lymph nodes involved in the ith patient, that is following some Poisson regression with some probability distribution that is given in the equation form this, and assuming that when we are yi, that is the count form that we usually write in the presence of covariates. We write in the mean value, that is lambda I, that can be written as log lambda I is equal to beta naught plus beta 1 x1 plus beta 2 x2 like beta k x k. So here we have considered k covariates, and then we can write a Poisson regression model like in this form of equation number 2. But there is a very Poisson regression model has like unique feature that that mean and variance are the same, that is known as equidispersion criteria. The problem is that when modeling real data, this equidispersion criteria is rarely satisfied. So the Poisson regression model less variability of counts than observe what we are observing in this situation. We have to adjust the Poisson model in some way to account for any over dispersion or under dispersion is in the data. Suppose we have over dispersion, what do we mean by over dispersion? Over dispersion refers to the excess variability in the data. That means the variance of the count response is greater than variance of the predictor. In that scenario, we have an alternative approach to Poisson model, that is negative binomial model, which has an extra parameter that here we are considering negative binomial distribution for this scenario to estimate the number of involved nodes. That negative binomial basically there is an inbuilt provision to account for over dispersion due to some unobserved observed heterogeneity. This model will help us to not only adjusting the standard error of the regression coefficients, but also it will provide a flexible approach. That means in case of this is when we are having a over dispersion in our data that is due to some unobserved heterogeneity, we can go with negative binomial approach instead of Poisson regression model. But in case of we are data is having some under dispersion problem, then this negative binomial will not be sufficient to model that kind of scenario. So there we can go for a generalized Poisson distribution. Generalized Poisson regression model is similar to negative binomial model, but it has a second parameter and known as dispersion parameter. That generalized Poisson regression model can be reduced to Poisson regression model when that dispersion parameter will become 0. The generalized Poisson model takes care of both under dispersion and over dispersion in our data. This generalized Poisson is given in the form of equation that in the 5. Now, so here we can see the dispersion parameter, that alpha is in as a dispersion parameter for our generalized Poisson regression model. And it has that advantage over Poisson regression and negative binomial regression model in the sense that it is suitable for both under dispersed and over dispersed count data. Here the point is the negative binomial model or generalized Poisson model may not be appropriate when we are having over dispersion due to excess 0. That means most of the time in case of when we are having a count data, so there is zeros, but that 0, if we are in our study, if the zeros are excess 0 is there, so it will we will underestimate the probabilities of 0 and consequently underestimate the variability present in our outcome. So we have to think of other alternatives or other situations, other alternative models such as zero inflated or zero hurdle model that will account for over dispersion as well as due to excess 0. That means we need to think about some alternative approach where we can go with having excess zeros in our data. So for that we are going to zero hurdle approach, zero hurdle Poisson model. There you can say zero hurdle approach first was in the way back in 1971. Craig was introduced this zero hurdle Poisson approach. This is an essential idea of a hurdle model, that is to partition the model into 2 parts, and the first part is a binary process of generating positive counts, that is and the second part is generating only positive counts. The first part we can take like yi is equal to 0. That means probability of having the in our problem, this is given in the equation form 6, where we have two parts. One part is like that generalized like zero hurdle Poisson model. That first part is like we have logistic part, and the second part is like zero truncated Poisson that is given in the equation number 7 and 8. And this coefficient of like lambda i's and gamma i's and beta i's are the regression coefficient under logistic and zero truncated Poisson regression model, where we have like patients we want to model this scenario. But the zero hurdle model is suitable in the case where excess zeros arises from the population, where every individual an equal risk of having events. But here one point I would like to mention, that in the count data regression modeling, the zeros can be of two types. Sometimes there are structural zeros or true zeros. The structural zeros of a patient is, a patient is at no risk or very low risk of the event of interest, that reported outcome variable as 0. And sometimes the other type of zero that we call like sampling or false zeros. In sampling zeros, a patient is at high risk of the event of interest and the reported outcome as 0. So this scenario, this is about the zero hurdle Poisson regression model. So same way we can extend this zero hurdle Poisson regression model to zero negative hurdle negative binomial model that is given in the equation number 9. And where here the we can similarly we will have two say part, like one part is due to logistic like part, other is due to like a zero truncated negative binomial part. And this is if the same thing zero hurdle can be extended to generalized Poisson regression model, and this is this will given in the form of like equation number 10, because in the process of zero hurdle model, next thing is if we are having like a zero hurdle model, and sometimes it is noticed that zero hurdle models are more suitable in case of we are having more structural zero. That means we are having more true zeros. But in contrast, when the zero inflated model should be considered when we are having both type of zero, that means true zeros and false zero in our outcome variable. So here we are again considering the other type of model, that is zero inflated model. That zero inflated model is it can be thought of as a finite mixer model, where we supposed to two data generating mechanism, one generating due to zero, other one is full range of counts. That means zero inflated model is again we are having like one part is due to for logistic part, the other part is zero inflated Poisson model. So this is given, the form of equation is given in the equation number 11. And same way here also we will find two parts of zero inflated, and this zero inflated Poisson model can be again extended to zero inflated negative binomial, and this can also be expected to zero extended to zero inflated generalized Poisson regression model, and that is given in the equation number 15. And once we have like right now we have the Poisson regression model, negative binomial, and generalized Poisson regression, and zero hurdle Poisson, zero hurdle negative binomial, zero hurdle generalized Poisson. Similarly, zero inflated Poisson, zero inflated negative binomial, zero inflated generalized Poisson regression model. So we have a very number of competing models for this count data. And how we can get these estimates or the beta coefficient from using some maximum likelihood estimation approach that is being given in the equation number 16, 17, and 18. And this is also using this equation, we can get the values of estimates. And this is given in the form of log likelihood fund. Maximizing this, we can get the values. And this is given in the equation number. Okay, this is all this. I mean, basically, what I have done, because considering all these models and using statistical softwares, R software packages, PSL, and we have like fitted all these models to our data. I mean, the data is regarding from endometrial cancer patients. And we have compared these models, and based on their AIC, BIC, and log likelihood values, we have like selected the best fitted model, and that best fitted model used for our analysis purpose. So basically, the objective here is how we can demonstrate this competing model in case of we are having problems related to count data. That is, since we are giving here the application of endometrial cancer patients, and we know the risk factors involve lymph node, which is an important risk factor of endometrial cancer survival, and we must know the risk factor for lymph node involvement that should be ascertained first to prevent overtreatment and provide the best surgical option for patients with endometrial cancers. And because accurate prediction of the number of involved nodes in endometrial cancer patients helps in grading the severity of disease, avoid extensive axillary surgery dissections, and assist the treatment decisions such as when to start like chemo, when to start like radiation therapy, when to start like both chemotherapy and radiation therapy. That will help to know that this from this model outcome that exactly will help us. And in endometrial cancer patients, a lack of nodes involvement, that means we observe zero because we may the cancer is detected early enough in the disease progression. That means the very start of onset of disease that is being detected. So that's why we got like observed zeros in our data. And basically, I have already mentioned that my objective is to assess and to demonstrate how the various counter data regression models will be beneficial to determine the identify the factors that associated with the extent of nodal involvement. For this analysis purpose, we have studied, like we have included 170 patients who have undergone like a routine pelvic and combined pelvic and para-aortic lymphodectomy during the period of 2011 to 2017 at Acharya Harihar Postgraduate Institute of Cancer, that is Kotak. It is like a nodal center of our Eastern India that caters various patients from Eastern India. And the patients diagnosed with some other malignant or cervical cancer that have been excluded from our study. And we have only included only those 170 cases. And this is regarding their patient characteristics, because this endometrial cancer, this is, because this is a gynecological cancer, most of the time this appears, I mean, this incidences occur to maybe after menopause. I mean, most of the time you will find at around age of 50 and above, this cancer usually the seen in the women. So the mean age is 56 something, 57 years, and plus standard deviation is 9 years. Tumor size that is given, and here I have given that the descriptive idea. I mean, what kind of data we have considered for our analysis. And as I said, I stated there are 9 models we have run for this purpose to demonstrate which is going to be our best fitted model for this particular problem. So here we can see that zero inflated generalized Poisson, which is very less AIC and a BIC minimum value for this model as compared to others. So we have taken as considered as this is our best fitted model, and based on this we have given our findings, because zero inflated generalized Poisson regression model where we can get the two-part results, and the first part is for logistic portion and the second part is for Poisson portion. And this table shows the estimates of regression coefficient of various coefficient of both person of zero inflated generalized Poisson regression model. And because these results of both parts of the model together helps us in understanding the role of the factors on the nodal distribution. Because in the logistic portion, we can see that obstetric history, that means multipara as against nullipara, that is 1.5 times more. I mean, that increased a chance to get a negative nodes in the endometrial cancer patients. Similarly, if you see the grade 2 and grade 3, that is around 2.73 or 2.78 times more likely risk of getting increased number of positive nodes among these patients of endometrial cancer patients. And tumor size of if the tumor size is more than 2 centimeter, that is 3.5 times higher likelihood of having a larger number of positive nodes than in the patient with the tumor size less than 2 centimeter. So it means this way we can say how this results is basically here the same thing I have. The Pearson here I said 170 patients we have found, we have studied, and that the results which here I have not shown, but we started with Poisson regression model, then we moved to negative binomial model, and there we have got the dispersion parameter, that is 2.9, which is significant, and also the likelihood ratio also goes in favor of negative binomial model. Also looking at the dispersion, that access 0 negative nodes in our data, and this is the based on already I have this results I have discussed, and these things I have already, the significant factors which are associated with the nodal involvement may be the result in delay in treatment. Thus, we need to focus on early diagnosis of endometrial cancer patients. Basically, my concluding idea is the number of involved nodes is one of the most important therapeutic and prognostic factors for endometrial cancers. The clinician need to predict the number of involved nodes in endometrial cancer patients in order to improve the health outcomes, and generalize in zero inflated generalized Poisson regression model provide the best fit for predicting the number of involved nodes in endometrial cancer patients. And this confirms the distribution of involved nodes continued over dispersion, not only due to unobserved heterogeneity, but also that excess 0 is there. And finally, many of these significant factors, what I have studied, that associated with the nodal involvement may be a result of delay in diagnosis. Thus, we need to focus on early diagnosis of endometrial cancer patients. And here I should note my limitation of this study, that I have not included, because this data is obtained from with a collaboration of a doctor, and retrospectively I have collected this information, since there are few important covariates that I have not included in my study, and also this is one single center study to while we are generalizing this idea, this results, we need further clarification, further confirmatory study in a large setup. So these are the references I have used. Thanks. I think I am with end of my presentation.
Thank you, Dr. Soin, for your nice presentation. And it is a live data collected from the hospital with the consultation with the doctor. and it's a nice presentation. Now the house is open for any question or comments. I have seen, is this the question related to you, Prafulla, that what city in city and method? It comes from Dr. Rajagopal K. Is it related to your study? I think
No, sir. This is some other.
Okay. Any question or comment from the house? I think if there is no, then again, thank Dr. Schrein for your nice presentation and a big clap from our side.
Thank you, sir. Thank you.
Now may I call upon Dr. Bindu Krishnan for her deliberation of lecture on data generating using GAN with heavy tail distribution. Dr. Krishnan.
Thank you, sir. First of all, thanks to the organizers for the opportunity given me in delivering this session. So let me share the screen. Is it visible, sir?
Yes, it is visible.
Yeah. The title of my presentation is Data Generation Using GAN with Heavy Tail Distribution. GAN, or Generative Adversarial Network, actually a subset of unsupervised learning. In unsupervised learning models that belongs to a deep learning model that utilize two networks along with adversarial training to output novel data that resembles the input data. Or data generation using GAN is actually based on neural networks where two networks compete each other to produce realistic or visually realistic synthetic samples or images. And the main objective of course, synthetic data generation is to provide data that is not real for cases where the use of real data is somehow limited. That is in case where, say, there is a need for large volumes of data, when the data is sensitive to use, or simply when it is hard to get access to the real data. For example, say this GANs can create images that look like photographs of human faces, even though the faces don't belong to any real person. So GANs achieve this level of realism by pairing a generator which learns to produce the target output with a discriminator. Again, that discriminator learns to distinguish true data from the output of generator. So the generator actually tries to fool the discriminator, and discriminator tries to keep from being fooled. Actually, traditional methods of say this synthetic data generation uses techniques that do not intend to replicate important statistical properties of the original data. Say, for example, properties such as distribution or patterns or correlation between variables are usually omitted. So moreover, most of the existing tools and approaches require a great deal of user-defined rules and do not make use of advanced techniques like machine learning or deep learning. While machine learning is an innovative area of artificial intelligence and computer science, and of course that uses statistical techniques to give computers the ability to learn from data, deep learning is a closely related field based on learning data representations. that may serve useful for the task of this synthetic data generation. Definitely this GAN is a deep learning, deep neural network technique. So that's actually the importance of this generation, or why data generation or data augmentation is required. So let me move to this. This is actually the objective of my study, that is to design a new generative adversarial network with heavy tail distribution as random noise, and to implement this training, this GAN training, the loss function, weight update, etc. for these models in practice. And finally, to establish the superiority is this new model or new method over other traditional GAN methods in generation of heavy tail data. So let me start with an introduction of GAN, generative adversarial network. Is, of course, this GAN have emerged as a powerful framework for learning complex data distributions and produce samples that are as close to real data as possible. This network is proposed by Ian Goodfellow and team, a team from Google in 2014, and it's a framework for estimating generative models through an adversarial process. Or at a high level, GANs are neural networks that learn how to generate realistic samples of the data on which they were trained on. The ultimate goal of this network, this GAN, generative adversarial network, is to learn the distribution of real samples to generate virtual samples that's mainly used for, say, image generation, then text generation, sound generation, and so on. GAN actually consists of two main components, generator and discriminator. The generator learns to generate the realistic samples, and the samples generated by the generator are usually considered as negative training samples for the discriminator. So why we say this negative samples? The reason is that actually the goal of discriminator is to minimize the loss from misclassification between real and fake samples, but the goal of generator is to maximize discriminator's probability of being real. So during the training process, actually we alternate the training between generator and discriminator to ensure their skill level is similar. Discriminator actually learns to distinguish between generator's fake samples and real samples, and thus penalizes generator for producing unrealistic samples. So both generator and discriminator act neural networks, no doubt in that. GAN simultaneously trains two models, a generative model that captures the data distribution and a discriminative model that estimates the probability that a sample comes from the training data rather than the generative model. Or in short, the model that is used to generate plausible examples from the problem domain is the generator, and the model that is used to classify examples as real, of course, real from the domain, or fake from the generated one, is the discriminator. Now, GANs are based on a game theoretic scenario in which the generator network must compete against an adversary. So this can be treated as a minimax game where the discriminator is trying to minimize its reward and generator is trying to minimize discriminator's reward or maximize its loss. Mathematically, that expression is given by minimum with respect to that generator, then maximum with respect to that discriminator of this reward. Now, how to train a generator? Sorry. We start with sample the random noise, then produce generator output from the sampled noise, then get the discriminator as a real or fake classification from the generator output, then calculate the loss from discriminator classification, then backpropagate. Usual network procedure, we are following the usual network procedure here, artificial neural network procedure here, backpropagate through both discriminator and generator to obtain gradients. Finally, use these gradients to change only the discriminator. Or let me explain with this diagram. This is actually the architecture of GAN, or the newly introduced heavy-tailed that GAN. So a GAN takes random noise as its input. The generator network takes a random output, say Z, where Z is a sample from a probability distribution G of Z. From a probability distribution, say G of Z, and tries to generate a sample of data. Here actually this generator tries to generate a sample of data. It is then fed to the discriminator. It is then fed to the discriminator, say D or D of X. The task of this discriminator network is to take input either from the real data, from this real data, or from the generator. And then it tries to predict. It tries to predict whether the input is real or generated. Or the task of discriminator is to classify the data as real or fake or real. So then through the back, if it is real, then it's okay. If through back propagation, this discriminator's classification provides a signal that the generator uses to update its weight. That is, if it's real, of course, it's okay. We can proceed with that data. Otherwise, if it's fake, then we need to continue this process. This generator again produce this, that generator, that training, we need to continue that training. Now, the main motivation for the design of GAN is, it's very clear. It's the learning process requires neither approximate inference nor approximation of a partition function gradient. Most of the virtual sample generation methods are based on the assumption that now come to the second point, the exact work which I'm presenting here, that is generation of realistic heavy tail data using generative adversarial network so as to augment training data for machine learning models in heavy tail data classification and identification. So most of the virtual sample generation methods are based on the assumption that data are generally follows Gaussian distribution. But however, in many cases, the data set behaves Gaussian as well as non-Gaussian characters. So in such situations, definitely the distribution of samples would change. Generated by the traditional method would change. GAN models usually assume that the real sample data follows Gaussian distribution. But the system may be disturbed by some other noise, particularly heavy tail noise in many data. So data often show the character of heavy tail distribution. So this was one of the reasons why we took a step on this work, especially in this particular context. So heavy tail distribution, of course, just a brief introduction to heavy tail distribution. That is probability density, or if the behavior of data is dominated by large values and the probability of exhibiting huge value is relatively big, then that kind of data is described as heavy tailed, or it's said to follow power law distribution. So the description heavy tails or power law actually refers to the fact that tail probability decays to 0 at a constant rate of the observation value of observation x in contrast to the exponential rate. So actually this is a contradiction to many phenomena that can be easily characterized by the average values. So the commonly adopted assumption that the random variables under investigation follows Gaussian distribution is not appreciable in many situations. And also the probability density curves of heavy tail and Gaussian distribution are similar, bell shaped, but the tail of heavy tail distribution is thicker than that of Gaussian distribution. So modeling using power law distribution instead of normal distribution actually generate a much higher probability of larger values, and this capture the important feature of heavy tail distribution. Now, this is a mathematical form for checking whether a distribution is heavy tailed or not. Either we can use this one, that is limit of e power minus tau x by the survival function is 0, or as, of course when n tends to infinity, or we can use this one. Now, the commonly used heavy tail distributions are Pareto distribution, Weibull distribution, Cauchy distribution, log normal distribution, student distribution, there's an asymmetric Laplace distribution, and so on. Now, the main challenges actually in this work are the existing GAN architecture do a poor job of matching the asymptotic behavior of heavy tail distribution. So while dealing with infinite moments and large distances between outlier points that are characteristic of heavy tail distribution, the common loss function may produce unstable or non or near zero gradients. So these problems with heavy tail GAN will be addressed in this study. So this is a brief review of literature on the studies for heavy tail distribution with GAN. Generative adversarial network was proposed by Ian Goodfellow and team from Google in 2014, which is a continuous development of deep learning model. And it is used to learn the distribution of real samples to generate virtual samples. Then Radford in 2015 introduced a class of CNN, convolutional neural network, called deep convolutional generative adversarial neural network, and demonstrated that they are a strong candidate for unsupervised learning. Then in 2018, Cheng, Bao Li and team proposed an improved generative adversarial network applied to the oversampling of time series classification, and realized an OGAN application for this for the same unbalanced discharge voltage of lithium-ion batteries. Then 2020, Ensign et al. Introduced a dual autoencoder GAN for the generation of fraudulent data, where that model detects actually fraudulent transactions through neural networks trained on enhanced training networks. Then again in 2021, a study on extending the representation of power of GAN to heavy tail distribution using classical Pareto was carried out by Hester et al. 2021. Then Oriol and Mio 2021 demonstrated that Gaussian prior distribution cannot be used to simulate heavy. This is another motivation actually for just an extensive study of traditional GAN distribution, because in traditional GAN actually it is assumed that samples are generated from Gaussian distribution. So in 2021, actually these two authors demonstrated that Gaussian prior distribution cannot be used to simulate heavy tail distributions. So this is the proposed GAN. So here we use this heavy tail distribution. Then the generator produce that samples from here. It will pass to the discriminator, real data. So this discriminator will distinguish or try to predict whether those data that comes from here or here will be real or fake. So the distribution of actually hidden variable Z in GAN is changed from Gaussian distribution to one of the heavy tail distribution. In this study, actually, I have used T distribution. So using T distribution as the student's T distribution as a prior distribution can increase the probability of network learning to the tail distribution. Yeah. So, so this heavy tail GAN generator and discriminator actually are improved version of deep convolutional neural network. The generator adopts full convolutional neural network. That's why I use convolution and pooling. So this purely based on that neural network training is exactly same as that of neural network, but here I have used that convolution neural network. The generator adopts full convolution neural network that is composed of 5 layers. 5 layers of CNN or convolution neural network. Then the convolution kernel size of the first layer is this n star 1, where that n is the sample dimension. Since there is a strong correlation between each feature of data, so that is why we use this one. Of course, that activation function used is ReLU function, rectified linear unit, leaky ReLU. By default, of course, in Python, usually by default also we are getting that ReLU function. So here actually we have used leaky ReLU function. So the HT GAN, that is heavy tail generative adversarial discriminator, adversarial network discriminator, does not use the same 1 star 1. So does not use the same 1 star 1 convolution kernel as a generator, because that convolution kernel will lead to that first convergence or in poor sample quality, that results in poor sample quality. So the discriminator network adopts the discriminator structure similar to deep convolutional neural network or deep convolutional generative adversarial network. And of course, in that data analysis part, actually, I have compared the traditional deep convolutional network and this proposed accuracy of this proposed heavy tail GAN. So this is the continuation of that convolution neural network. We can see convolution 1, convolution 2, 3, 4, 5. So this one, that is 1 star 1. This is actually real or generated one. So this is a loss function used here. That is which is same as that min max gain. Same format. Now come to that data generation steps. So here actually considered that industrial fault data of complex systems. Of course, that industrial fault data are often heavy tail, and we have say a few samples here. So see, this is the data generation details of that is TE process data. Here, this data set is downloaded from this Harvard website, and this contains the issues and advances in anomaly detection. For anomaly detection evaluation for joint human automation system, or simply say T process data. The data set includes 20 kinds of fault data. Each sample has 50 variables and each fault has 960 samples. And it's named as fault-free training, fault-free testing, because of course we require training and test data for a neural network training. So fault testing and faulty training corresponding to, and it's downloaded through our software. And this is a histogram. Or here actually I have considered only 2 features because even though 50 variables and 20 kinds of fault data set are here, so I have considered only 2 features here. So this is a histogram actually, which clearly shows that the data set is heavy-tailed. So actually the generation that results of this heavy-tailed GAN is evaluated from 6 aspects: sample mean, sample standard deviation, skewness, then kurtosis, then histogram, QQ plot, or this correlation coefficient. So it is very clear from these pictures. This is actually I have plotted, I have computed or considered these aspects for 2 things: the newly proposed heavy tail GAN with the T distribution and the deep convolutional GAN in literature. Because here actually I use that convolution network, that loss function from that particular GAN. That is why I have made the comparison with this. So from these pictures, of course, from the data comparison, it's clearly we can say that the generated sample quality of heavy tail GAN is better than that of this deep convolution GAN. And including that features includes that variables or analysis includes that sample mean, sample standard deviation, sample skewness and kurtosis. Also, the generated data of heavy tail GAN will retain the retains the kurtosis of original data better than the deep convolution GAN, which is an important index to measure the characteristics of heavy tailed data. Heavy tail. Now, the comparison of regarding the comparison of generated samples of column vectors of two typical heavy tail distributions. So the generation effect of heavy tailed, and of course, it's better that is closer to the distribution of real samples. Moreover, the samples generated by heavy tail GAN retain the heavy tail of real samples. So that is the crux of this particular analysis. It is closer to the, of course, this heavy tail GAN retain the heavy tail of real samples, because that role of discriminatory is to distinguish between the real and fake samples. So the samples, but the sample generated by deep convolution GAN is closer to Gaussian distribution, not heavy tail distribution. That is another measure to prove the superiority of this particular model. Then the third case is that it's a histogram also here, real data, this is HT GAN, deep convolution GAN, and this is case. Then that QQ plot is shown here. The samples generated by HT-GAN, both HT-GAN, this is a real data, then HT-GAN and deep convolution GAN. Then, yeah. So this is the final table actually, which clearly shows the difference between the F measure values. F measure is actually this accuracy, this classification accuracy is the total number of correct predictions divided by total number of predictions made for the data set. It's very clear that here it is for DC GAN, deep convolution GAN, it's only 71%, but for HT GAN, it's 98%. So that accuracy is that much difference between the 27% difference between the accuracy. Then other than that, this F1 measure, of course, F1 measure is the harmonic mean of precision and recall, where precision quantifies the number of positive class predictions that actually belong to the positive class, and recall quantifies the number of positive class predictions made out of all positive samples in the examples in the data set. So F measure provides a single score that balances both the concerns of this precision and recall in one number, or it's a harmonic mean of precision and recall. Here that F measure is also 0.96, which is near to 100%, or near to 0.9, which is near to 1. So the highest possible value of F measure, of course, it is 1. That indicates the perfect precision and recall. And the lowest possible is 0, of course, that either precision or recall is 0. So from this, actually, we can say, or we can conclude the superiority of new model that heavy-tailed GAN over the deep convolution. Why I compared this deep convolution GAN? Reason is that while comparing with the traditional methods, already in literature it has been proved that this outperforms the other models. That is why I have focused on only these models. So that of course in this particular paper, actually particular study, in this study, the traditional GAN is upgraded by a heavy-tailed GAN by assuming the heavy-tail distribution as the distribution of random noise, and this can well learn the distribution of original data. Then tail of a distribution can retain the tail of data distribution, and also correlation of real data. The superiority in heavy-tail data augmentation or heavy-tail data generation over traditional GAN method is demonstrated by applying the new method to a heavy-tailed data set. So these are the references. Thank you.
Thank you, Dr. Krishnan, for your nice presentation of application of this heavy-tail distribution for generating samples. Now the house is open for any question or comments on this lecture. Is there any questions or comments? Okay, I think there is no questions from the audience. Okay, again, thank you, Dr. Krishnan, for your nice presentation. And I know that you engage in started your study by heavy-tail distribution, application of heavy-tail distribution in time series. Now you are applying your neural network and information technology criteria for generating the samples. It's a nice work. Thank you.
Thank you.
And I also thank the two speakers and all the audiences, those present here, for helping me to conduct this session nicely and within the time limit. So thank you once again. And there is 8 minutes remaining also. So we are before time. So thank you all, and thank you thanks the speakers also. Thank you. And may I wind up this session now? So we will wind up this session and we may leave. Right?
Thank you, Sudhanshu sir, for chairing the session.
Thank you. Thank you.
I request to the participants, please wait another 8 minutes to start the session, because the chairperson is already in the talk in another hall B, in hall C, Dr. B.G. Manjunath. So once the talk is over, then we will continue this session. Just wait 5 to 10 minutes. Thanks. Huh? Satya sir? How many participants are there? Participants. Huh?
Yes, sir. Myself.
Meanwhile, that we'll check it once the. The serial number 125, 184 to 192. And please check it once the members that what we have listed already present.
Myself 125, sir.
125.
25.
Okay. Inventory model with exponential iteration and shortages.
Yes, sir. Yes, sir.
And the next 184. Yes. 184 to 192.
185, sir. Shikhar Tyagi. 185, sir.
185, okay. 186 present. 187. 188.
Good afternoon, sir. 188 present, sir.
Okay. Kumar Swami.
Yes, sir.
189. Jilamshu. 190. 190. 191. 192. And the
Good afternoon, sir. 193. Present, sir.
190. One
193.
Management.
Harshita, your number is 198. Please note it. Shall we start the session, sir?
Yeah, sure, you can start.
Good afternoon to all the delegates and participants present here. It is an honor to introduce Dr. B.G. Manjunath, sir, as the chair of the session. Sir published 9 research papers, 5 working articles, and 2 authored books. Sir is the member of Indian Society for Medical Statistics, International Indian Statistical Association, and Indian Society of Probability and Statistics. I request Sir to occupy the chair and conduct the contributory papers session.
Hello, can you hear me?
Yes, sir. Yes.
Yes, sir.
Okay. Thank you, sir. Yeah, so I think I was calling, but my audio was okay. Anyway, so this is Dr. Manjunath, and so now the current session, I am chairing this session, and so we have a couple of talks in this session, and one by one we'll go. So the David Chris Raju is present. Okay. Ajit Kumar, Aziz Kumar, Shahu, Neha, Lakshman Rao.
Yes, sir. Yes, sir.
Okay,
Yes,
so yeah, so you can share. So you can share your screen, and we'll start from you.
Okay.
Yeah.
Please
So
begin.
yeah. So and the talk is on inventory model with the exponential deterioration and shortage of for several levels of
Yes, sir.
production. Okay. So introduce yourself, and so and I invite so Lakshman Rao for the talk, and
Yes,
please
sir.
share the screen, and your talk will be of time 10 minutes, and make sure that you finish it in 8 minutes, and 2 minutes
Okay.
we'll have for the question and answer. Okay. So welcome.
Okay, thank you.
Yeah, welcome, and please.
Thank you. Thank you.
Yeah.
Thank you very much for giving the opportunity. Yeah, myself, Dr. Agatmudi Lakshman, Professor of Statistics from Aditya Institute of Technology and Management, Tech College, Srikakulam District, Andhra Pradesh. I am audible, sir?
Yeah, clearly audible. Yeah, go ahead.
Yeah.
Thank you. So my talk is going. I want to go for the deliver by inventory model with exponential deterioration and shortages for several levels of production. Actually, the main motto of this paper
mainly the inventory models play very dominant role in the manufacturing of the inventory management. So there, I will focus only on this paper by EPQ models. These EPQ models are mathematical models which represent the inventory situation in a production and manufacturing systems. In production and manufacturing, the EPQ models is extremely significant and also utilization for the scheduling the optimal operating policies and market yards, warehouses, and godowns. In this paper, we provide the multiple levels of production. Consider to the deterioration follows the exponential distribution. After a specific period of time, it is feasible to switch over production from one rate to the another, which is an advantage in the sense that by starting with a low rate of production and large amount of manufacturing items is avoided at the outset, resulting in the lower holding cost. Yeah, so this is very important point. Earlier models, maybe I will focus this point only. After specific period of time, if feasible to switch the production and will increase the production. So when we will increase the production, so that is an advantage in the sense that the starting when the demand is more into the particular commodity. So we will keep the items, large number of items. So such a cases, we will get the more benefit, potential profit, and the customer happiness also very much required for such a situations. That's why I was considered this multiple levels of economic production quantity models, and deterioration follows the exponential distribution, and demand is the time dependent demand. Time dependent demand I was considered. So yeah, this is some introduction point. Of course, just I was giving some brief idea about the inventory systems. Inventory systems play a dominant role in many practical situations at places such as a production process, manufacturing units, transportation, market yards, warehouses, assembly lines, etc. One of the main stream of the operations is inventory management, which is used to determine the optimal ordering policies for the inventory management control. Inventory models provide the basic framework analyzing several production systems. The inventory models are generally inventory models use a dominant role in the production manufacturing units in the inventory management. So inventory models can be classified two types: economic ordering quantity models, economics production quantity models. But this paper belongs to the economics production quantity models. Mainly inventory, if you we will discuss the inventory model. So mainly we are concentration on the deterioration or decay. So that is very important for particular items or the commodities of the commodities. This is very important. Deterioration is a natural phenomenon of several commodities over time. For commodities like glassware, hardware, and steel, deterioration can be quick manner at the times, causing deterioration to be taken into the account when the determining the economic plot says. In general, some commodities decay is the faster phase than others, such as medicine, gasoline, strawberries, fish, food, and food grains, which is must taken into account when determining the size of the production lot. And the decay is the please. One minute.
So I think time is.
Yeah. The screen is not moving. That's means. Okay. Yeah. So, some different authors, maybe they are collected the different literatures. Yeah, for this model, I'm concentration to the work improvement of the work of the Karthike and Vijay. They are developed the economic production quantity models, inventory models for a constant iteration productions and takes into the account into the three levels. Just I was considered the multiple levels of multiple levels of production. This is the main advantages when we can switch into the production of particular time. such a cases, the production will be, we will get the more production, so then only we'll get the more profit. Automatically, the customer will also happy. So that's why I was consider this is the main multiple levels of production. Yeah, all these are the assumptions of my model. Yeah, multiple production rates into the take into account, demand rate also considered, production rate also considered, shortages are permitted, exponential the exponential iteration I was considered, and instance rate of production, hazard rate also I was calculated using the exponential distribution, H of t equal to f of t by 1 minus f of t. Yeah, so these are the notations I was considered, and this is the symmetric diagram of my this paper. Yeah, totally this is total multiple levels of production. Then from starting the production from 0 to capital T, during 0 to T1, the production will be reaches the level of T1, or like that T1, T2, T2, T3, T3, T4. The production will be reaches Q2, Q3, and Q4. And the growth was considered when it reaches the quantity of Q1, Q2, Q3, Q4. I was considered the growth K minus R. K is the production rate, R is the demand rate. K minus R is the Q1 growth, A1 into K minus R, Q2 growth, A2 into K minus R, Q3 growth, A4 into K minus R, Q4 growth. And then after the shortages are allowed, and then maybe the production will be declined, then we will consider that this is the shortages period, the production is decomposed. Okay, so all these are the differential equations of my model. So there are 6 differential equations I was developed from using the symmetric diagram. I was developed these 6 differential equations. Solving these differential equations using the initial conditions. So I was considered these initial conditions according to that figure. I was considered using these initial conditions. I will solve that differential equations. So all these maybe the difference differential equations, maybe linear differential equations. So we'll get these all these I of t inventory level we will get, all inventory levels we will get. So then after we are getting the inventory levels for all the differential equations of our my model, then we will finding the optimum order quantities Q1, Q2, Q3 using some initial conditions. I of T1 equal to Q1, I of T2 equal to Q2, I of T3 equal to Q3, and I of T4 equal to Q4. Then we will get that Q1, Q2, Q3, Q4. We will get that shortage levels also I will find out. And also I will finally, what is our requirement? We want to find out that the total cost. So what is the total cost equation? The total cost is the sum of the production cost, ordering cost, holding cost, decorating cost, and shortage cost. So we want to calculate all that cost individually. So production cost per unit, production cost is the R is the production rate and CP is the production cost. Then production cost per unit is the RCP. Ordering cost per unit is the C3 is the ordering cost. Per unit means the T is the total cycle, C3 by T. Holding cost also I will calculate. Holding cost C1 is the holding cost. C1 by T is the C1 by T times when it is the holding cost is applicable up to we will keep the production. So when we'll according from the diagram, we will keep the production up to the T5 level. So that's why I was calculated the holding cost between 0 to T1, T1 to T2, T2 to T3, T3 to T4, T4 to T5. Then you can already have equations, all the equations I of T1 during that 0 to T1, T1 to T2 like that. Then substitute all I of the inventory levels into this, then simplified. We'll get the holding cost. The trading cost also we are calculated between the all the during the times we are calculated the trading cost. And
sir, last 1 minute, sir.
1 minute, okay. Finally, I will go for the So this is the table parametric variations of the optimal values. I was considered the different parameters C1, C2, C3, CP, theta, alpha in my equations, and we will get the optimal values of total cost Q1, Q2, Q3. So now I am observed that the following I am observed that the table shows that when the rate of deteriorating increases, so thus the cycle time and ordering cost and total cost increases, and cycle time and ordering quantity and total cost is also increases. So some sensitive analysis also I carried out. So that from that above table, I was analyzed that sensitivity analysis when for what values of the parameters are increased, the corresponding total cost and optimum order quantity, whether it is decreased or increased, I was identified. And finally, we will conclude that in this paper, we are presenting the inventory model for deteriorating items that takes into the account many levels of manufacturing. We assumed that the demand rate is time dependent and which the linear and rate of deterioration follows exponential distribution. The proposed model is inappropriate for newly introduction production that have a consistent pattern up to the certain point of time. Yeah, that is very important. That gap I will fill up this model to compare the previous model. We will keep the production in particular specific period of time. That will be we will get that when the production, when the demand is more, we will when the demand is more, we will so automatically the items will be sold out more, or the customer also will happy. We will get the more profit. So compared to the previous model, I was fill up that gap only. Thank you, sir. Thank you.
Yeah, thank you. So any questions?
Hello. Hello, sir.
Yeah.
Is there any idea for selection of a deterioration rate is the exponential? What is the idea to select the exponential distribution?
Yeah, generally deterioration, some of the distributions characterize the deteriorations. Maybe hierarchical distribution, exponential distributions. These are the characterization about the about the deterioration. Fixed. See these distributions to characterize about the deterioration. So that's why I was selecting exponential distribution.
Sir, one more, please, sir. Sir, one more. While calculating the inventory at time t, okay, we are considering the deterioration rate is the exponential. Is that while calculation in inventory, is that integration is a convergent, or you applied any another method to solve that in inventory at time t?
So the general for mathematics background, so we are applying the difference, solving the difference equation. I think you are asking how we will solve this equation.
Yes.
Yeah, using the linear difference equation method, I was solve all these equations.
Then this differential equation will be sir non-linear, no?
Linear, sir. These are linear differences. Linear differences.
Okay, sir.
So here the variable is there. I of t is the variable, sir. I of t is the variable. Yeah, these are the linear differences.
So communication we can have, so time is running up, so
okay, sir. Okay, thank you, sir.
Yeah. Okay, so next presenter Ashish Kumar.
Thank you very much. Thank you very much for giving this opportunity.
Yeah. Okay. So Ashish Kumar, Pragya Gupta.
Sir, it should be Shikhar Tyagi, not Pragya Gupta.
Shekhar Tyagi. Okay, so there are three others. Okay, so you are present. So
Yes,
so Ashish Kumar and Monica Singh are Nivedit Gupta. So they are presenting one article, but no one is present, I think. Okay. So if you're not present, so now Shekhar. So I invite Shekhar Tyagi for your presentation. Comparison of multiplication.
What, sir?
See, I invite you to for a talk on comparison of multiplicative fatality models under generalized log logistic.
Okay.
Distribution for counter heterogeneous life sensor data. So please share your screen.
Okay, sir.
You have 10 minutes. Yeah.
Okay, sir. Thank you, sir.
Sir, please unmute, sir. Hello, sir, please. Sir, Lakshman Rao, sir, please unmute. To mute, sorry. Sir, okay.
Okay,
so
sir.
you can continue.
Okay. Thank you, sir. First of all, I am thankful to the chairperson and the whole ISPS community to give me a chance to present my paper in this conference. So today my topic is topic is that comparison of multiplicative frailty models under the generalized log logistic type 2 baseline distribution for counter the heterogeneous left sensor data. Okay, so these are my outlines that I'm going to cover in my presentation. So first of all, whenever we are going to present the, we are going to talk about the frailty models. The first question is that why we need it. So actually, sometimes what happens in the data, whenever we analyze any survival type of data, there is a assumption is that the data is homogeneously distributed, but in a real life situation, it is not always possible that the data should be homogeneous. There are some heterogeneity present in the data that can either can be presentable or hidden heterogeneity. So to counter these things, in 1972, Cox presented a Cox proportion Hazard model to handle the covariates and the heterogeneity. But in 1979, Weapon and et al. Introduced the frailty models, that is the extension of the Cox proportion Hazard model given in equation number 1.1, where your exponential e raised to the k dash beta naught is your k dash is your vector of your known covariates, and v dash is showing the unknown covariates. So, and here in equation 1.1, W is showing your frailty effects. Okay, in the literature, Hogarth gave a wide range of frailties in this in the area of frailty models. He introduced several distributions as a like gamma power Poisson distribution as a frailty distribution, and Flynn and Heckman gives the log normal distribution as a frailty distribution. But in the last decade, Hungel and his scholars gave a numerous frailty models based on the gamma and inverse Gaussian frailty models. In this paper, we are going to introduce another new frailty distribution named as the generalized Lindley frailty models. So for that, we consider under the reverse hazard rate setup. First of all, we are going for the generalized Lindley frailty models. It's nothing but a mixture of two gamma densities with parameter mu and theta and eta. Its density function is given as in the following equations, and the corresponding mean and variance are given as well as. After the applying the identifiability condition, we get the relationship between the parameters, that will be the eta equals to theta 1 plus theta minus mu. That after that, our density function reduces as follows, that given in equation number 3.2, and the Laplace transformation and variance is also reduced as given in equation number 3.3 and 3.4. So after that, after putting the Laplace transformation, we got the CDF function under the reverse hazard setup under the frailty effects given in equation number 3.5, and in the absence of frailty effects, we got the distribution function given in 3.6. For the comparison purpose, we also include the gamma frailty distribution given, and its Laplace transformation is given in equation 3.7. For the baseline distribution, here we consider the generalized log logistic type 2 distributions. Its CDF reverse hazard rate and cumulative reverse hazard rate is given as in the PPT, as you can see. So after that, we propose this model for the generalized Lindley frailty model given in equation number 5.1, and in 5.2 the model is given in the absence of the frailty, that is for the model 1A and model 2 respectively, and the model given in 5.3 is called as the model 1B. That is the model under the gamma frailty model, and under the, because we have the several number of parameters here, so maximum likelihood estimation cannot be applied due to the convergence problem. So we applied only the Bayesian analysis under the reverse hazard, under the left censoring data, and the density function is given in equation number 6.1, and the corresponding likelihood function is given in equation number 6.2. So it is also not possible for us due to the high number of high dimension of the parameters to get the posterior density function in a closed form. So here we are assuming that all the parameters are independently distributed, and after that we got the joint posterior density function as given in equation number 6.4. So to estimate the parameters, we here assume the Metropolis testing algorithm and the Gibbs sampler to get the convergence, and to check the convergence of Markov chain, we applied the Gavagitash and Glamour-Rubin statistics. So after that, we have applied for the simulation studies. In a real life situation, there can be more than one variables can be available. So for the simulation study here, we only consider a single covariates that say K naught, and we've assume that the frailty is following the generalized linear distribution, and we follow the following steps to generate the random numbers. And after that, we run the chain for 1 lakh times, and after that we find that our Glamour-Rubin test values are close to 1. So that provides us our parameters Markov chain reach to the stationary state. And for the real life data analysis, we assume the Australian twin data that was given by Duffy et al. In 1990. Here we because we are assuming only a univariate case, so we just consider only the first variable T1 for the that one, and here we are finding the estimation under the only the flat priors. So that's why the covariates follows the normal distribution with mean 0 and variance 1000, as well as the baseline parameters and the frailty parameters are following a gamma prior with the very small parameters with value 0.0001 for both parameters alpha and beta, and we are taking another prior distribution that is uniform prior for as well as. So after that, we in the final assumption we find out that the model age for the value of the frailty parameters are quite high for both models 1A and 1B. That is showing that our model is performing, there is a heterogeneity present in the data, and on the basis of the values of AIC, BIC, we found that our model 1A is better than model 1B and model second, and there is the tables for the simulation for the simulation study, and this is a table of case statistics, and this is the table of posterior density for the data analysis. And thank you.
So thank you. Any question? So no question is there. Let's thank the speaker, and our next speaker will be. So next speaker is so Sharma, Uksana Sharma, Ramanpreet Kaur. Okay. So but it's a reverse supply chain models with fuzzy stochastic remanufacturing capacity. Anybody present?
Yes. I am here, sir. Maruti Bhosle, sir.
Yeah.
Yes,
So,
yes.
I invite you for the
Yes,
talk.
yes.
And so the title of the talk is Reverse Supply Chain Model is Fuzzy Stochastic Remanufacturing Capacity. So
Yes, sir.
please
Yes.
share your screen and
Yes, sir. Yes, sir.
yeah. So you have 10 minutes.
Yes. Is I am audible, sir? Please.
Yeah.
Yes. The respected chairperson of this session, this work is under the guidance of Dr. Rao Sahib Ledpade, sir. The topic of the research is reverse supply chain model with fuzzy stochastic remanufacturing capacities. The outline of the presentation is Newsboy vendor problem, supply chain, forward supply chain, reverse supply chain, closed loop supply chain, mathematical model, result and discussion, and conclusion. So what is the newsboy vendor problem? Early in the morning, newspaper boy buys the paper from the wholesaler, and during the one day he sells all the papers. If some papers are left in his hand, the newsboy having the lost. If he purchased a maximum number of papers from the wholesaler, and at the end of the day, if having the some paper, he having the lost. And another way, if the newspaper boy purchased a minimum number of papers, and at the end of the day, if there is a customer but there is no paper, here is also, on the other hand, there is also loss. Therefore, how much paper should buy the newspaper boy, buy the wholesaler, such that he satisfy the customer's demand and maximize his profit? Here, how much quantity will we buy? There is uncertain. Therefore, we are using here fuzzy stochastic. Okay, the main newspaper vendor model is this. This is where D is the demand, Q is order size, then makes profit is equal to Q into selling price minus cost price. If demand D is less than order size Q, then D minus Q newspapers are left unsold at the end of the day, and he will get the salvage value SV for each of these newspaper. The net profit is this equation D into SP. And finally, here we are using the fuzzy technique. Therefore, we don't know how much quantity are already purchased. Therefore, we are using the fuzzy, and for fuzzy technique, we are optimizing its expected profit. And where FD is the probability density function and capital FD is the distribution function. Now, what is the supply chain? The process of supplying, the process of processing, supplying the finished product from the wholesaler to the customer. During this process, there are the number of components are included, like wholesaler, manufacturer, retailer, customer, there will be the maximum, less or maximum number of the component. Sometimes all the components are communicating to each other, and they cooperate to each other and maximize total profit of the supply chain. If cooperating to each other, then we say that centralized supply chain. If sometimes the number of entities they are communicating to each other, they take the decision on its, and they are increasing the profit itself, then that supply chain is called as the decentralized supply chain. The process of supplying the product from the source to the retailer is called as the forward supply chain, and the process of supplying the absolute product from the retailer to the manufacturer is called as the reverse supply chain. And the combination of the forward supply chain and the reverse supply chain is nothing but the closed supply chain. These are the types of the supply chain: forward supply chain, reverse supply chain. Closed means combination of the forward and reverse. Decentralized means their number of entities do not cooperate to each other, and centralized means they follow the rules given by the boss, they cooperate to each other and maximize the profit of the supply chain. In our model, we are using this assumption: one retailer and one customer. This is called a single stage or newsboy problem. Now, when the manufacturer sold the item to the customer, and at the end of the product. If the customer found the defective item, that defective item will be collected by the retailer, and retailer transfer this defective item to the manufacturer, okay, and manufacturer reproduce that item, and that item will be sold to the market. Okay, and when the defect item found to the customer, retailer gives some amount or some reward to the retailer, such that that defect item will comes in the process, and the environmental pollution decreases. Okay, now how much demand, how much cost, or how much reward will given to the retailer? Our duty, our main problem is, what is the cost or what is the reward given to the retailer by the customer, such that the total supply chain profit will be the maximum, total cost will be the minimum, and with this product or this model will helpful to reduce the pollution of our country or pollution of our world. Okay, remanufacturing capacity is the stochastic and unlimited. All the remanufactured product will be sold in the market. All the collect absolute product from the customer transfer to the manufacturer. Remanufacturing capacity infinite and uncertain. And we are here developed one reward function which is given in equation 1. We are developed this reward function W is equal to FC DC divided by DC max raised to R. When R is equal to 1, then above function becomes the linear, otherwise that function is the non-linear. We are using this notation: recycling fee, CRA cost of inspection, acceptance rates, inventory storage cost, Q sales quantity, W is small w is the recovery rate, P selling price, remanufacturing cost for item, C my inspection cost, CMD disposal cost, remanufacturing capacity, FC PDF and distribution function. DRD means optimal reward for the decentralized, and DRC means the centralized for the optimal reward for the centralized process. And we are optimizing this expected total supply chain profit. Okay, manufacturing, and we are calculating retail profit and manufacturer retail expected profit. We developed this model, which is given in equation number 2. This is our new model, assuming that probability function FC for remanufacturing capacity, the expected profit function for the remanufacturing is, which is given in equation number 3, where C is the remanufacturing capacity, which is continuous and which having the infinite capacity. We want to optimize the reward function W. We are differentiating equation 3 and equating to 0. We use equation number 4. After solving equation, we get here equation number 5. After solving this equation number 5, our duty is to calculate the reward function such that the total manufacturing cost will be minimum, total supply chain profit will be the maximum. And after solving, we get this equation. This is a large equation, reward function. This is continuous, sir. And up to equation 6 is the up to slide number this slides, and next slide is the one equation. And we are equating to 1 minus this S into this 1 upon W, WR, CMD. This is the total all is one equation. From equation 6, we can calculate the reward function by using Newton-Raphson method. And for sensitive analysis, we set the parameter P purchase price for 4,50,000, salvage value D1 and D2 the depletion rate, Q is the optimal order quantity. For a simulation study, we set the analysis, we set the parameters. R is equal to 2, that is number R is equal to 2, that is the non-linear. As recovery rate W increases, manufacturer profit goes on increasing, and the profit is strengthened for maximum recovery rate. Also, we can observe that DC reward decreases, manufacturer profit increases for high recovery rate, as profit are equal for R is equal to 0.5, R is equal to 1, and R is equal to 2. And this is a sensitivity table for DC reward function, profit and reward. As this is a recovery rate, R is a DC this manufacturer profit and reward function. This is again, okay, sir. Okay. As recovery rate W increases, the reward function W goes on decreasing, and it is almost same for all values of R0.5, R12. Thus, from table 1 and DC increases, reward function also decreases. And figure 2 this shows impact of recovery rate and reward at different non-linearity on profit. This diagram shows that impact of recovery rate W on reward. This diagram, figure number, this shows impact of acceptance rate and reward at different non-linearity on profit. This is impact of acceptance rate, tau on reward. And these are some references. Thank you, sir. Thank you.
So, thank you. Any question? If no question is there, I
Okay.
thank the speaker.
Thank you, sir.
Yeah.
Thank you.
So next is Raman Kaur or Upsana Sharma. So another is Kumaraswamy. Kumaraswamy.
Yeah, good afternoon, sir.
Oh, yeah, you are there, right?
Yes, sir.
Okay, so then please share your screen, and so your talk is on note on stochastic behavioral models in the consumer behavior, right? So you have 10 minutes. Please go ahead.
Is it visible, sir?
Not yet.
Yes,
Yeah,
sir.
okay.
Yes, sir. Yes, sir.
Yes.
Yeah, very good afternoon, sir. Myself, I am Dr. Kumaraswamy. Today, I am going to present on stochastic behavioral models in consumer behavior. This work is done under supervision of Dr. N.C.H. Bhattacharya from Osmania University, Department of Statistics. This is the outline of the presentation today. As we know, all we are consumers, and consumer behavior is a study of how individuals, groups, and organizations selection, buy, use, dispose of goods and services, ideas, or their experiences to satisfy their basic needs and wants. The behavior of consumer refers to the accession, utilization, and disposal of goods, services, ideas, and time by determination of units. Brand. Brand is an overall experience of consumer distinguished from others, identified by the symbol, logo, mark, and word. Next one is the brand loyalty. Brand loyalty is a tendency of continuity purchase of the same particular brand among the competitors, and it is measured on the repeat purchase occasions. Next one is the consumer brand switching. It is a difficult task to determine how the behavioral preferences are changing over the time, and this is a very crucial task to the managers in formulating the policies, developing new products, and sustaining the market to show their unique existence in the competitive of the market in the world. This is a brief review on this current topic. Several researchers have contributed their work towards a study of consumer behavior. These are the list of authors. Basically, Ehrenberg is studied the consumer behavior of repeated purchase consumers initially, and this work is carried out by the several authors. And in this work, we are proposing 3 behavioral models to assess the consumer behavior. First one is the distribution for repeated purchase consumers. This model, we proposed an alternative to the stochastic distributions, traditional stochastic distributions, in place of geometric, negative binomial, and hypergeometric distributions. And second one is a statistical linear model for brand repeated purchase. This is a Markov chain approach. And third one will be the hidden Markov model approach. This is the Poisson-Weibull distribution. This is an alternative to the existed distributions. The basic definition of this will be the X be a random variable denoting the number of repeated purchases made by consumers over the period of time. And assuming that the consumer purchases in a given periods, the mean purchasing rate of lambda follows a Poisson distribution, and this purchasing rate is varying among consumer to consumer the long run, and this purchase rate follows a variable distribution with parameter A and C. The resulting distribution will be the compound Poisson variable distribution. This is the probability mass function of the Poisson variable distribution. These are the graphs for the varying parameters of the Poisson variable distribution function. This is an example. We consider a particular data on the repeated purchase of consumers during the period of 26 weeks. This is the frequency of the data, and we estimated the theoretical frequencies by using Poisson variable distribution, and the frequencies are displayed over here. And we tested for the goodness of it by using both chi-square and Thales U statistic. But here I am showing Thales U statistics, and this value, the statistic value lies between the 0 and 1. When the value is indicating 0, that gives the best performance, and here we are getting the value around 0.008. So that is therefore the Poisson variable distribution predicts the number of purchases in a specified interval is good. And second one is the statistical linear model for brand repeat purchase. This is a Markov chain approach. In this model, the model is constructed based upon the Dirichlet parameters, Dirichlet distribution parameters. Those parameters are repeat rate and market share and polarized index. Repeat rate means the proportion of buyers of particular brand at the last purchase occasion, and also buy the same brand in the next purchase occasion. The market share will be the proportion of total purchases of that particular brand, and the polarized index is the measure of loyalty, which is a repeat rate standardized for market share. And this is the TPM construction of TPM model where when I equals to J, this
Hello. 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 Sir, we are not audible. Tomorrow, Swami. Hello. Hello. So 1 minute we'll wait. So presenter is not available. So then, yeah, any issue, then we go to the next one. So the next is Tirupati Rao Body and Jailam Sur. So is that so the talk is on post COVID-19 share market prediction through Markov models. So anybody? Okay. So next is a new mode matching composite regression model and its application to motor vehicle insurance claiming data. Girish. So is Girish is there? So next is measuring predictive efficiency of Indian private sector banks, a slack and based measure of data development analysis approach. Vittal.
Yes, sir. And
Yeah. So you can share your screen and start presenting.
Is it visible, sir?
Yeah. So somebody has to go for it. I can hear some noise.
Measuring protecting.
Is it moving, sir?
Yeah. I can see. Yeah. Moving. Yeah. Start.
Thank you, sir, for giving this opportunity to present my talk on measuring productivity efficiency of Indian private sector banks using SLAC-based measure of data envelopment analysis. So data envelopment analysis is a non-parametric test. It is branch of the operations research. Using data envelopment analysis, we are measuring the productive efficiency of Indian private sector banks. Efficiency is the key parameter which is used to measure the efficiency of the given DMU. DMU is nothing but here decision-making unit. Whatever participated bank from private sector banks we consider as a decision-making unit. So whatever decision-making units are there, so using given decision-making units of input and output variable corresponding parameter, we are going to find the efficiency. Using efficiency, we are going to segregate or we can compare. So which DMU is most efficient than the other DMU. So here various methods are available to find the efficiency of the DMUs and to compare the efficiency of one to another DMU to identify the most efficient DMU from the given set of DMUs. So based on the topics, I'm going to talk on the RBI and Ministry of Finance focus and equal importance to public and private sector banks. The development of bank sector plays a major vital role in the economic development of a country. Capital or funds can be considered as one of the essential components while measuring the growth of a nation. Banks help in capital formation, promoting industry bloom and generate the employments. Banking industry strengthens the government and balances economic development. Besides contributing to the information of initial capital requirement for investment, the banking industry indirectly assists the government in handling several problems, namely shortage of savings, rising prices, unemployment, unbalanced development, entrepreneurial blocks due to the capital limitations. Public sector banks are those where majority of the stake in the banks is held by government, whereas in private sector banks, majority is held by shareholder of the bank. In private sector banks, most of the equity is owned by private bodies, corporations, institutions, or individuals rather than government. These banks are merged and controlled by the private promoters. In this empirical study, efficiency is the score which deviates the private sector bank's performance. Performance evaluation is the key source of customers in banking, which helps to compare the banks. Public and private sector banks can be differentiated in terms of size and growth parameters, profitability and soundness of business, indicating robust growth prospects for the banking industry. The objective of this study is to study in detail the theoretical basis of data envelopment analysis model using Kahns, Cooper, Rode, Bankers, and Tone models to select the appropriate variable, including input and output for the DEA analysis, to obtain the efficiency scores, ranking of decision-making units, and carry out projection analysis through data envelopment analysis for banking industry in India. To assess the performance of private sector banks, to identify the best worst performer decision-making units of private sector banks, to test the significance of efficiency scores of private sector banks. To run the data envelopment analysis, we need to have some input and output variable. At least we require to identify one input and one output variable to run the DA analysis. For this analysis, I'm using 2 input variable as well as 4 output variable. So identification of input and output variable is major task in run the DE analysis. As we know that input is depends on the maximum utilization of the DMUs, and output refers the benefits generated as results of the DMU. For the DA analysis, I identified 22 private sector banks, and these banks I'm going to analyze the data. To run the DA analysis, the basic DA models are CCR model and BCC model. So these are the basic and old model to get the good amount of efficiency from identified private sector banks. I used advanced model in DA for the analysis, that is slag based measure of efficiency under CCR and BCC model. So this is the mathematical function of CCR model. CCR is nothing but Kahn-Cooper Road, given in 1978, formulated as a fraction programming problem to assess the technical efficiency of decision-making unit, which is combines multiple input to produce multiple output. To find the efficiency of a DMU, we can take the ratio of the quantity of output by quantity of input, which gives the efficiency. So this in CCR model, we can use all the input and output variable to measure the efficiency of the identified DMUs from the private sector banks. So this is the projection score of efficient decision-making units. They have taken A, B, C, D, E, and F are the decision-making units. From this graph, we identified that the CCR model follows constant return scale. Constant return scale means the CCR model identify a DMU as efficient when the amount of output and amount of input variable is in proportional way. When amount means the output variable is increasing, the same amount of increment if we get from the input variable, then we can identify as that particular DMU is an efficient DMU, and other all DMUs are inefficient DMU. From the given set of DMUs from the graph, we identified that C is an efficient DMU and remaining are the inefficient DMU. So this all efficient efficiency score will have between 0 and 1. 1 indicates the efficient DMU and less than 1 indicates inefficient DMUs. Inefficient DMUs having the chance to improve their efficiency scores if they attain the and follow the rule and regulation of how they maintain a particular bank. That bank has efficient. After a certain period of time, they become the efficient DMU. So according to this, the efficient, the DMU C is the benchmark to the other inefficient DMU. To identify a DMU's efficient means in CCR model, the lambda is the parameter and used to find the efficiency. If efficiency score lambda is equal to 1, then that particular DMU is said to be efficient, as well as so whatever input and output variable we are using, at least one input or output variable must be greater than 0. If CCR is inefficient, if lambda is less than 1, or if even though lambda is equal to 1, if input and output quantity of variable is 0, then we can call it as, even though the DMU is lambda equal to 1, it is inefficient. And a DMU is said to be efficient, it must be lambda value equal to 0 and the slacks must be at 0 level. But this method fails to measure or identify a DMU is efficient when in various economic and business data are often subject to scale difference due to increasing, decreasing, or constant return to scale. But CCR model fails to minimize the non-zero slacks while projecting scores on frontier line of production possible set. CCR approach fails to identify the scale differences. It follows constant return to scale instead of variable return to scale. Corrections can be made by explicitly introducing influencing variable as additional factor. In addition to CCR model, if you use one influence variable or factor, that is summation j equal to 1 to n lambda j equal to 1, then this parameter can identify a DMU is efficient at increasing or decreasing on constant return to scale. So the addition of the CCR model is BCC model. BCC model identifies a DMU is efficient at increasing or decreasing and constant return to scale. So this is the projection score of scores of the variable return scale. This is the mathematical model of BCC model. And same parameter and DMUs we are taking here, what we discussed in CCR model. But CCR model is identified only DMUC is efficient, but BCC model identifies 3 DMUs out of the given set of DMUs are efficient. So this model is better than previous model CCR model because of it identified 3 DMUs are efficient. The previous model identify only 1 DMU is efficient.
So 1 minute left, sir.
Yes. But CCR and BCC model can find only efficiency of the given DMUs, but those methods are fails to control the slacks of the input and output variable. In addition to those models, slack-based measure of efficiency is mostly concentrate on input excess and output shortfall, which results as non-zero slacks. This is the drawback from the this model. To eliminate the non-zero slacks presented in the CCR BCC model, Carver Tone introduced a new methodology, is slack-based measure of efficiency. Slack-based measure of efficiency is concentrate on the measure should be invariant with respect to the unit of data. A measure should be monotonical decrease in slacks of input and output variable. So this is the mathematical model of SBM under CCR model. This is the mathematical model of SBM under BCC model. And BCC model is, we can say a DMU is efficient if its parameter theta is equal to 1 and all slacks are 0. Whatever efficiency we are getting from the private sector banks at SBM CCR model as well as SBM BCC model, those efficiency we are going to test using a non-parametric test, that is Mann-Whitney U test. Because of this data envelopment analysis is a non-parametric test, and which is based on ranking of the data. So ranking of the data itself, we can use the non-parametric test to test the efficiency of the given ranks. So these are the results from the identified banks. We identified out of 22 banks, 4 banks are efficient and remaining 6 banks are inefficient. Just I am showing efficiency score of efficient bank, but these 4 banks are efficient, but we can't identify which is a more efficient. So to identify that, we can go for the peer score. Peer score is nothing but reference set. So which DMU having maximum peer score, that is the most efficient bank compared with the other efficient bank. Remaining 16 banks are inefficient. Out of 16 inefficient banks, poor performed DMUs are according to ranks. IDFC, Yes Bank, Bandhan, and RBI banks, their efficiency scores are given. And next, under BCC model, these banks are efficient, and as per P score is concerned,
please conclude, sir.
Yeah. Jammu Kashmir is most efficient than other banks, and we identified that 4 bottom banks are inefficient bank, so they can improve using this statistical data in which variable they are poor, so that they can improve, and how much percent they are they need to improve, and how much percentage they need to decrease, so that they can improve after a certain period of time, and they are become the efficient DMU. So as per 2 models is concerned, if you observe the averages, 0.4185 and 0.5061, both are more or less equal. But this one we are going to prove using non-parametric test. P value is 0.30772 compared with alpha value. So P value is more. So we accept the null hypothesis. It indicates that there is no enough evidence to claim that the efficiency score of private sector group at SBM, CCR, and VRS model differs significantly. So this is the summary and conclusion of the measuring efficiency of decision making unit using slack-based measure of efficiency.
Okay, any questions?
These are the references. Thank you.
So if no questions, thank the speaker. And the next participant is Vittal. B. Vittal, are you there around?
Me only, sir.
Okay, sir. And Avinash Sharma.
Yes, sir. This is Hariom Pachwali. Yeah, disparity.
Yeah. Dipanjan, right? Dipanjan Bhattacharya.
Yes.
Okay, so you can, So disparities in the mental health services village brother caste and the gender. A statistical study from the Central Institute of
Psychiatry.
Psychiatry Ranchi.
First of all, thank you, organizer and chairperson, for giving me opportunity. Topic of my presentation is disparity in mental health services utilization across the caste and gender, a statistical study from Central Institute of Psychiatry. Before going to my presentation, I want to tell you important things because nowadays mental health is going to play important role because now it is said that next pandemic will be on mental health. So nowadays we need to more focus about the mental health. Due to COVID, many people, they are affected from anxiety, depression, so many disorders. So I'm going to deal in that. So introduction, this study was carried out at Central Institute of Psychiatry, which has been operating under the aegis of Directorate General of Health Services, Ministry of Health and Family Welfare, Government of India. The Central Institute of Psychiatry is located at the city of Ranchi, Jharkhand, capital of Jharkhand. In the year 1918, this institute was established by British government to cater the mental health needs of the British and European civilians working and residing in India. Till India gained independence from the Britishers in the year 1947, care at this institute was restricted to those of the British and European stocks, while Indian themselves were excluded. When it was established, the institute was named as the Ranchi European Mental Lunatic Asylum, and all the European and Anglo-Indian inmates of the Bhawanipur and the Behrampur Lunatic Asylum were transferred to this institute. As a result of this efforts, the tag of lunatic asylum was removed, and it was termed as mental hospital in 1920. Tertiary care is understood because this hospital is one of the tertiary care. Tertiary care is understood as specialized intervention delivered by the highly trained staff to individuals with the problems that are complex and refractory to primary or secondary care. Tertiary care has emerged as a pivotal factor in providing universal access to healthcare in the 21st century. In the low and middle income countries, very few mentally ill people receive mental health care at their doorstep, primary care level. As primary mental health services in India is still somewhat underdeveloped. Therefore, existing tertiary government mental health establishment end up addressing the mental health needs of a large section of the population. However, many of the patients could be treated at the primary level itself, as their mental health condition does not warrant specified treatment at the tertiary center. Coming to the literature review, the National Mental Health Program of India was announced nearly 4 decades ago in 1982 as an integrated and comprehensive mental health care approach to meet the mental health needs of common people. Past community-based epidemiological study on mental health and behavioral disorders showed varying prevalence rates in India ranging from 9.5 to 102 per 1,000 population. As per the report of the National Sample Survey Organization, overall population prevalence of mental illnesses was 14.9, nearly 15% per 1,000, which was found to be higher in the rural areas, 17.1, than the urban area, 12.7. Between 1990 and 2013, the estimated burden of mental disorders in India increased by 44%, along with the neurological and substance use disorder, and it is expected to increase further by 23% in India between 2013 to 2025. Coming to the material and methods, this study is retrospective in nature, and the annual statistical data related to patient care and mental health services given the institute was used in this study. Last 10-year data related to the services were used to present this study. This study is based on the retrospective analysis of routinely recorded patient-related clinical data collected from 2012 to 2021 at the institute. Data was collected in between 2 years. So now coming to the results, you can see that in the year 2012, OP attendance was 70,827, and in year 2019, it went to 98,789. In the year 2020 and 21, due to COVID, that figure came down, but in terms of percentage change, you can see that admission, discharge, emergency services, community services, that was going to increase day by day. Arrival of new cases and follow-up cases. Here you can see that because the study is all about the see the gap between male and female. So here you can see that because female they are 50%, but they are due to their gender, people are discriminating them, and they are not giving them proper mental health treatment facility. You can see that in terms of new cases, figures are there. In terms of follow-up cases, figures are there, and you can see that figures are less in the follow-up, because one time they are coming, but in the mental health you need to give follow-up for many years. So they are visiting one time, but afterwards they are not continuing their treatment. So next one, again you can see that there was a gap was very small, 1:2 and 1:3, but here you can see that 1:5 gap is there in terms of male and female, in terms of admissions. Whenever it is coming to admit any patient, people are more resistive. They don't want to admit their patients. They are generally seeking mental health care through OPD basis only. This is regarding the diagnosis. Here also we can see that nowadays substance abuse, that is also enhancing day by day. That is F10.10 to F19. So that is also enhancing day by day. Nowadays we can see that community people, they are abusing alcohol, they are abusing various substance. Next, you can see that in terms of caste also, there is variation because Jharkhand is a tribal state, but you can see that in terms of service utilization, that is only 10%. So that is also one of the major concern. Here you can see the age-wise breakup, and because in India, in coming year, we are going to face a severe problem regarding our senior citizens, geriatric mental health. So there also you can see that very few people they are availing the mental health care facility. So coming to my discussion, there continue to be surge in mental health, number of mentally ill people in the community, and as we know, in India there are serious dearth of mental health professionals and institutions to cater the mental health related needs of the people. Primary mental health care has not yet developed uniformly across the country. Therefore, people tend to rely on the tertiary care for seeking help of their psychological problems. This phenomena has been reflected in the statistics of the institute too. In the year 12, that was 77-29, it seems to be significant increase in the span of 10 years. This institute is not only example of the tertiary care. Other institute like AIMS, PGI, NIMS, these are also tertiary care centers. The number of admission and discharges from the inpatient wards of the institute have been found to be increasing as per the increase of the OPD registration. It might be attributed to various factors of the variables, significant increase in sharing of mental neurological substance use in global burden of diseases, considerable increase of people with mental and neurological substance use. In the present study, it was noted that the case of new as well as the follow-up cases, males have been constitutively an overwhelming majority than females. In the context of new cases, the number of male patients almost doubled during 2012 to 21. This suggests that females do not avail treatment for their mental illnesses at the tertiary level as much as the male, neither do they come for the regular follow-ups. This might be attributed to the various illnesses related as well as the socio-cultural factors, that is possible impact of gender on the age of onset of the symptoms, clinical features, frequency of the psychotic symptoms, social adjustment, long-term outcome of the severe mental disorders, social interpretation, attribution, and acceptance of the mental illnesses in the women, forms of social support available and accessible to the women with the mental illnesses, and most importantly, anticipating social rejection in the form of stigma, stereotype, and the prejudices of the mental ill women in their caregivers. In terms of availing the mental health facilities, studies have shown a ratio of one woman for every 3 men attending the public health psychiatric outpatient facility in the urban India. This clearly point out the underutilization of the services of the suffering women. There is likely greater stigma attached to the women mental health that negatively impact the help-seeking behavior for the public mental health services facilities. Lesser importance is given to the mental health issues pertaining to the women in general. Gender can escalate the discrepancy between the prevalence and utilization. This low attendance can also be explained by the lack of ability of the specific resources meeting women's need appropriately at the hospital settings. Most mental hospitals seems to be preferentially allocate health facility to the males, as it can see in the sex-based discrepancy in the available of the beds. The male-female ratio of allotment of the beds in the government mental health facility is 73% and 27%, while those with services, research, and training 66% and 34%. This way, predominance of the male in the utilization services, which was observed in the parent study, this consistent with the previous observations. This can be attributed but to the very nature of the institute, this institute being a tertiary or the referral one, hence people with the severe okay, sir. Okay, sir. Disorder like 3 mentioned subject tend to out here for the receive the intensive treatment. In terms of age, the category of the admitted patient in the last 10 years, that was from 16 and above. As per the survey conducted by National Sample Survey Organization, OBC constitute 41% of the population. 20% ST is 8.63%, while rest of the continue to the discharge list can be explained by demographic information. These are my references. Thank you very much. If you have any question, that is also welcome.
So, any questions, right? Sorry, no question is there. Let's thank the speaker. Thank you for your presentation. So now we'll go back to the
Thank
first,
you.
yeah. So from the order. So now next person I can give Ramanpreet Kaur. Are you around? Okay.
Yes, sir. Yes, sir. Arun Kumar, sir.
Arun Kumar is different now. So I am asking the 6 now.
Sir?
Yeah, so Ramanpreet Kaur and Upsana Sharma.
Sir? Not audible.
So can you hear me?
Yes, sir.
So Arun Kumar, wait. So what is your number? Series number, top?
192, sir. I think
191. 191. B Vittal. So it is B Vittal it is showing. Where is Arun Kumar?
Sir.
Presentation is over.
Sir, my title.
So okay. So wait. Who is next? Another person. So Vamshi Murga is around. Vamshi. So in this session, who is missing for the presentation? Who didn't?
So may I continue, sir, my session?
So
Kumar Sam, sir.
Yeah. So yours has to be continued. That is why. But anybody present over here?
So may I share my screen, sir?
Yeah. So that is the only option. I think no one is from this list. So you are the last present. 186 Ramanpreet Kaur.
188, sir. Kumar Swami.
Yeah, no, that is okay. But Ramanpreet Kaur. 186. He messaged.
Sir, 193.
One.
Sir, 193.
193 is not in this session. Yeah, in this session. Okay. So you finish it up, Kumar Swami.
Yes, sir.
Okay.
So 5 minutes I will be to finish it up. So next session has to start.
Sure, sir. Sure.
Yeah.
Thank you, sir. Sorry for the inconvenience, sir.
Yeah.
The second model will be the Markov chain approach. Here the Markov transition probability matrix will be constructed based on the Dutch model parameters. Those are the repeat rate, market share, and polarized index. When I equals to J means that is the loyal consumers who are convinced by the market pressure. They stick to the same brand. And when I not equals to J, that means those are disloyal consumers who switch the brand from I to J. And we consider the two brands cases. That is the market share will be 0.6 and 0.4, and the purchasing pressure with the polarized indices will be the 0.4 and 0.3 for the two brands. And the transition probability matrix will be the 0.76, 0.24, and 0.42 and 0.5. And we will estimate the long run behavior of the purchase probabilities for the two brands. Those will be the 0.63 and 0.6, and remaining the 0.36 and 0.3636. And also we estimated the some Markov in characteristics. Here we showed the mean recurrence time for each brand purchased repeatedly. And the second model and third model will be the dynamic hidden Markov model. And assuming that the data is observed over a T period of time to analyze the consumer behavior, the consumer purchase decisions relied on the attitudes of the consumer. Basically, these are some factors of the consumer which are affected to purchase the brand, which are hidden in nature, and transition between hidden states will be identified the relationship as a consumer attributes AIJ matrix, and where this RIJ will be the association of preferences among the hidden factors, and SIJ will be the level of saturation per factor associated with some random disturbance epsilon ij. And the second process will be the observable transition from hidden state to the visible states. This is the equation giving the visible sequence probability matrix, where Pj K denotes the probability of purchase of kth brand associated with the jth factor, and Dk will be availability of the brand when it takes the values of 0 and 1. When it is available, it takes 1, not available 0. And Wj will be the weight of the factor j, and Fjk will be the observable probable association of purchasing kth brand with the influence of the jth factor load. We consider two brands case here with the 4 factors at 4 time periods, and the hidden state probability will be the P, and visible state probability matrix will be the Q. To evaluate the best observable sequence, we estimated all possible sequences, that is order of n square of t. Here we use forward and backward algorithm to estimate the probabilities. In this hidden Markov model, we consider two cases, that is the not repeating case and repeating case. When the product is when the consumer is likely to purchase consistently, that means loyalty, the observable sequence will be the initial period B1, second period B1, third period B1, and fourth period will be B1 with the probability of 0.00, with the initial state probability of pi100, with the affecting factors will be factor 1, factor 1, to factor 2, and factor 1, and the rest of 2 will be the switching cases with the different scenarios. And these are the we present only two characteristics here. The first one is the characteristic function of the Poisson-Weibull distribution, and second one with the estimation of repeated. Second one with the stationary probability for the Markov chain process. And the conclusions are the these Poisson-Weibull distributions are generalized hypergeometric distribution. This is not in a closed form. When we are restricting parameter C, we are getting closed form. When C equals to 1, the Poisson-Weibull distribution leads to the geometrical form, and when C equals to 2, the Poisson distribution will be the hypergeometrical form. And the next conclusion will be the brand performance indicators of the Dutch model are used to construct the detailed statistical model of the transition probability matrix. The brand switching and repeat purchase analysis are the model is used to investigated with the Markov chain characteristics. And the last conclusion will be the transition probability matrices derived with the considering the prime factors which influence the consumer behavior with the help of the two brands case, the repeat purchase and brand switching sequences probabilities derived over a period of interest. Hidden Markov model is a significantly helpful determining the leader of market brands in the long run, and also giving it a bird's eye view to the manager in decision making circumstances.
So,
references of the current presentation.
So
thank you.
Yeah, any question? Okay, if no question is there, let's thank the speaker.
Thank you, sir.
Yes, Arshita, are you around?
Yes, sir.
Yeah, so start your presentation, share your screen and start.
Okay, sir.
Sir, my name is also Harshita.
Huh? Who is this guy then? Hey, Arun Kumar, what is this? Your name is, I did not call your name, man.
Oh, okay, sir.
So which session you are? You are not in this session, I think. So please check.
Yes,
Sir,
sir, I have this section morning. Madam told me, Jayashree madam.
So told to present in this session.
Yes, sir.
Okay, so we'll see that last. Okay, so now, so madam, so Ashita can present, share your screen, start presenting.
Okay, sir. Sir, is it visible, sir?
Yeah. So 10 minutes.
Yes,
is
yes.
Yeah. So start.
Very good afternoon, and thank you, sir, for providing me the opportunity to present my paper on role of statistics in disaster management. India is prone to various disasters. It includes natural hazards, which are cyclones, tsunami, heat waves, landslides, floods, earthquakes, and in the recent year, we have also seen the locust attack on the agricultural produce. There are also disasters which are chemical, nuclear, and biological. The UN has categorized the COVID-19 under the biological disasters. Initially, the approach towards disasters was relief-centric, that after the disaster has taken place, then the actual execution took place. But a paradigm shift took place with this approach, and from relief-centric, we started pursuing proactive culture of preparedness. The 1990 at the international level was observed as the decade of international decade for natural disaster reduction. In India, after the independence, a scarcity relief division, which was renamed as Natural Disaster Management Division, was set up in the Ministry of Agriculture. Later on, a Center for Disaster Management was established in 1995. There was a Latur earthquake in 1993. Then we saw the 2001 Gujarat earthquake, and then the tsunami of 2004. These all disasters highlighted the urgency for a central legislation on disaster management in India. And as a result, a number of international and national events led to the Disaster Management Act 2005 in India. Disaster management is a continuous and integrated process. It involves planning, organizing, coordinating, and implementing the measures which are necessary for mitigation, preparedness, a prompt response, magnitude assessment, evacuation, and reconstruction. Here, the statistics plays the very significant role in analyzing the existing risk, informing the public about future risk, and planning actions to prevent disasters. In a disaster management cycle, the role of statistics can be seen at every stage, at the preparation level, at the response level, at the recovery, and as well as at the mitigation. The availability of key data forms the basis for planning. Statistics can help in assessing the risk and vulnerabilities and It also helps in assessing the level of stakeholders' capabilities and state of logistics. Thus, the database can be very helpful in future planning. Moreover, during a disaster, the timely supply of relevant information is very critical for rapid and synchronized response by all the agencies involved. Because in absence of any key data, such response can be delayed or won't be effective in addressing the needs of the distress situation. This study is qualitative, exploratory, and descriptive and empirical in nature. The area of study covers the Rohtak division of Haryana, which involves 5 districts, namely Bhiwani, Charkhi Dadri, Jhajjar, Rohtak, and Sonipat. It includes 30 blocks. 200 government employees are taken, 40 from each district. The employees who are the part of the study works at the district and the block level. They are mainly from different offices at the mini secretariat at the district, irrigation department, power and works department, education department, blocks development and panchayat officer, education department, sports and youth affairs, etc. This study also involves the trainers from National Institute of Disaster Management, from National Disaster Response Force, Haryana Institute of Public Administration, and the Haryana Institute of Rural Development from Nilo Khedi. There are other government personnel who also provide related trainings as a part of this study. This study inquires into the attendance of government employees regarding any disaster management related training. It involves not just the training program, but any workshop, seminar, or even first aid training, which have a significant role when it comes to the disaster management. According to the response from the respondents, only 30% employees have received such training. 87% didn't get any opportunity to be the part of such training program which are related to disaster management. The given data reveals that such a low percentage, which is 13%, highlights the lack of disaster preparedness efforts. This study further highlights the issue for such low participation. The issues which were highlighted by the trainers were that there is lack of trainees' interest, participation, and engagement. Somehow departments were sending the same employees for the training program, which restricts the opportunity to be trained to only few government employees, which find as their personal interest or which were forced to do so. Heavy workload was the reason cited by the potential participants for their absence from the training programs. And a very important point which was noted that after the training, the feedback submission was the issue which was not taken seriously by the trainees, in the absence of which trainers can't improve the training program for the future participants. On the other side, the trainees also highlighted the issues faced by them. Sometimes the language became the barrier in the better understanding of the subject, because many times the English was used as the medium of communication, which was not understandable by many of the participants. At times, the participants were not able to relate to the content of the training. They are not able to make out the relevance of the content of the training to their area of work. Follow-up and refresher courses are not taken up on time, and this leads to the loss of interest for the even interested participant itself. Too much workload leads to their absence from the training or half-hearted participation. Now, this study presents the relevant facts and information concerned to the disaster management training of the government employees working at district and block levels. Here, the statistics has made it possible for us to know about the reach of the training program regarding district administration in the Rohtak division of the state of Haryana. Further, this study gives insight into the issues concerned to trainers and the trainees. This information has a very important role to play for future planning and preparedness measures. Training is vital for developing a resilient society. Through the training needs assessment, which again involves the support of the database and statistics, there is the need to identify the problems of the trainees and helps in preparing comprehensive need-based plans. For TNA itself, the support of relevant data can be helpful in use of limited resources and precious time in a judicious manner. A well-maintained data in hand can go a long way in saving the numerous lives and resources, and also to avert the years of development from going waste. There is a need of dedicated personnel and funds with regard to database management concerning different offices, activities, logistics, and as well as stakeholders. A proper database should be maintained regarding the list of participants from different departments who have attended the training, who is eligible for further refresher course, when action taken report on the sharing of knowledge gained with the colleagues and the initiatives taken at their work, as well as in personal life regarding disaster management after the completion of training can be reported. All this highlights the role of statistical database for the purpose of the disaster management. During the COVID also, we have seen that while the issue of transporting the migrants from to their respective states arose, first the registration of these migrant workers started by the district administration. Only then the further execution was possible. These are my references, and thank you very much. If there are any questions, you are welcome.
So any questions? No questions, let's thank the speaker. So Vittal, are you around? Vittal.
Sir, I finished my presentation, sir.
Yeah, but you messaged me, na?
Not me, sir. That is.
Okay, so Arun Kumar. Arun Kumar.
Sir, yes, sir.
Yeah, okay, you are the last presenter. So present it, and so nobody is left, right? Okay, so Arun Kumar, share your screen and present as soon as possible. So what is your number?
191, sir, I think.
191.
He is referring old data, sir.
Okay, so your 191 is Vittal, man.
Yeah.
Oh. So what is the number? So anyway, Arun Kumar, okay,
yes.
Share your screen. I will note down.
Okay, sir.
Fast.
Sir, visible, sir?
Yeah. Fast. 10 minutes is left.
My name is Arun Kumar. I am doing PhD Annamalai University under the guidance of Dr. R. Ilangovan. Thank you all for the given this opportunity to present my article. And then my title is length-based Quasi-Shankar distribution with time-dependent covariate and estimating its parameter. My abstract is, in the study, we present the length-biased Quasi-Shankar distribution, which is a length-biased form of the
Your slide is not moving.
Oh, 1 minute, sir. Now, sir?
Yeah. So, pause.
Okay. In the study, we present the length-biased Quasi-Shankar distribution, which is a length-biased form of Quasi-Shankar distribution. A detailed case of weighted distribution is a length-biased distribution. Various statistical properties like order statistics, moment generating function, entropies, and likelihood ratio test are addressed in this proposed distribution. The suggested distribution of parameter is estimated by using the maximum likelihood estimation method. Finally, the newly proposed distribution is presented using two different data sets, demonstrating its utility to superiority. The keywords as weighted distribution and the maximum likelihood estimation and Quasi-Shankar distribution and order statistics, reliability analysis, and time-dependent covariates. And then introduction part. When an investigator proceeding of a report of overlapping of a stochastic regression model, weighted distribution are useful. Weighted distribution or useful distribution is theory because they deliver a fresh accepting standard probability distributions of approaches for extending current standard probability distribution. Modeling lifetime data due to outline of an additional parameter in the model which permit the model to become more flexible. In some situation, appearing in numerical practical disciplines, for example, medical science, engineering, and so on. Weighted probability model performs a significant role. These distributions emerge when observation from a sample are gathered with the unequal probability, and they contribute unfilled method for problems and encompassing non-experimental, non-replicated, and non-random observations. When the recorded statement on the event cannot be random for actual distribution, weighted distribution are compulsory. This is occurs when the original observation spoiled and the event occurs that is not noticeable. The resulting overvalue or decrease or outcome of the improper scenarios, and the unit or event do not take the equal probability of occurring as they followed the exact distribution. Weighted distribution are applied in the biomedicine, ecology, reliability, and branching process, and many more fields. Modeling and interpreting lifetime data is critical in many practical fields, including engineering, medicine, behavioral science, finance and insurance, and others. A continuous distribution such as variable, gamma, Lingley, and exponential, log normal, and Lingley. These distributions are used to comparing the my distribution. Okay, the next slide. We present the length biased version of Cauchy-Shankar distribution. This is known as a length biased Cauchy-Shankar distribution. In this paper, the Cauchy-Shankar distribution, a new two parameter probability distribution expressed by Shankar 2017, who discussed several structural properties such as moment based measures, stochastic model ordering, hazard rate function, stress exponential, and reliability, and Bonferroni and Lawrence curve. The two parameter Cauchy-Shankar distribution is a subgroup of one parameter Shankar distribution. The proposed two parameter Cauchy-Shankar distribution excels the one parameter Linley exponential distribution in the term of the data processing facility. And then this is I give the length biased Cauchy-Shankar distributions probability density function is shown here, and then cumulative distribution function is coming here. And then next slide. Let W of x is a non-negative weighted function of the probability density function of random variable, where x is between a non-negative function, and the equations are shown here. Then 1 minute, and we can get the PDF of length biased Cauchy-Shankar distribution by substituting the equation 1 and 4. We get the graph like the probability density function of length biased Cauchy-Shankar distribution. The PDF plot is here, and then CDF plot is here. Probability density function. Then the reliability analysis. The proposed length biased Cauchy-Shankar distribution is a reliability function, hazard function, and reverse hazard rate function have all been computed in this section. The reliability function. The reliability function is a survival function of the length biased Cauchy-Shankar distribution calculated as the given equations are shown here. And then hazard function. The hazard function is also known as a hazard rate, defined as intensity. Okay, sir. Reverse hazard function equation is shown here. And then,
so please wind it up in 1 minute. So next session has to start.
Oh, okay, sir. I finished. And the survival model with the time-dependent covariates equations is shown here, and the moments and associated measures, and then the equations bars also here. Harmonic mean of my distribution, and then MGF moment generating function is shown here, and then likelihood ratio test. Bonferroni Lawrence curve, and the entropies and Brownian entropies. Patient parts also here. States maximum likelihood estimation of Fisher information matrix. So data evaluation. In this paper, we investigated whether the length-biased Quasi-Shankar distribution fits better than the Shankar exponential Quasi-Shankar and Lilly distribution. The data sets are shown here. The data set, first data set is this, and then second data set is this. Then my result of the comparing first data set output is here. It's better to fit for the comparing Quasi-Shankar distribution, Shankar distribution, exponential and Lindley distribution. And then this is data.
Yeah. So, okay. So any question? Any question? So if no question is there, let's thank the speaker, and this session is ending and next session will start. So overall for the next session, please be there, and overall finish this lab order. So thank you guys.
Any more are there, sir? Any
No,
more speakers?
everybody. Yeah, Arun Kumar was from morning session. He presented here, sir. Everything is finished, sir. Okay.
And what about 186 has given, sir?
So 186, 186.
He
Yeah,
gave, sir.
Yeah. 186 has given presentation.
Given, sir?
Yeah. Yes, sir. He has given 186 has given.
So what are the numbers who have not presented, sir?
So the overall presented is 125. So 125.
185, 186, 187, 188.
Yes, sir. Yeah. So 125 is
91, 192, 193, and 198.
Yeah. So 184 not presented.
186
also not presented. 188 also not presented. 189
not presented, sir.
Yeah, 188 not presented.
Presented your name.
188 yeah, present, sir. Sorry. 188 present. 189 not present, sir.
189. Okay.
Yeah. After that,
191.
191 not. So Vital is also finished. Yeah.
Sir, me presented, sir.
191 present. Yeah.
190.
191, sir.
191 also present, sir.
191 is Vital. I think he's presented.
Yeah. So 190 also presented.
192 is presented.
Yeah.
193, 198 are presented.
Yeah.
Okay. Thank you very much, Dr. Manjunath, sir. Please.
Thank you, sir.
Thank you very much for your kind cooperation with a short notice.
Okay.
And
thank you.
Sparing your valuable time.
Yeah, sir.
Thank you, sir.
Thank you, no problem. Thank you, sir. Okay.
Thank you very much.